Check 1, 2.
Port for a workspace. And larger projects are still going to have to put in a fair amount of effort in order to upgrade to modules. And this means that there's now a larger barrier to entry to upgrading to new versions of Bazel. And this is a dangerous situation to be in. It's a little bit like the Python 2 to 3 transition. It's very important that we get through this transition quickly to avoid fragmentation in the ecosystem. The good news is that all major rule sets now support modules. So there's very little blocking migration. I'd like to thank the rule set maintainers for their hard work in getting this to happen. This wasn't easy. A lot of people are submitting feature requests, and a lot of changes have been made in Bazel from 6, 7, 8, and now 9. A lot of good stuff has landed. I'd also like to thank my colleague Mike Bland for writing this excellent series of blog posts on migrating to Bzlmod. So this outlines all the problems that you might run into, and it provides a lot of good advice. Much of that was informed by his work with Rule Scala. They completed their migration to modules and released version 7 in May. So congratulations to them on that release. Documentation doesn't need to stop with the written word. Sometimes face-to-face training is best. And yesterday we had our training day with 6 different free trainings from our sponsors at Twig, Aspect, Build, and Engflow. And this worked really well. We've usually done a community day either the day before or after BazelCon with a few extra tech talks. But I think having a training day, a training focused day, was really good. This welcomes a lot of beginning and intermediate Bazel users through things like bootcamp, writing rules, Bazel management. There's a lot of good stuff in there. And this is one of the ways we really grow as a community. If you miss these training sessions, don't worry. I know there were limited slots for sign up. They're not one-time only, so several of these are open source. You can find the materials online, and you can also follow our speakers and sponsors to find out when their next trainings are. We also have meetup.build, which is a site that lists upcoming events. You can register there or propose your own new session in your city. So Engflow is kicking off our world tour. We're calling it Build, Scale, Investigate. You might see our t-shirts around. So we're organizing trainings and meetups around the world. And we went to the Bay Area in September. We went to Sydney and New York in October. And you'll see we have an event here in Atlanta. That's actually our game night. So head over to meetup.build and sign up for that and join us at Skull Brewing tonight. I'd like to extend special thanks to our hosts at Apple, Asana, Canva, and Databricks for making these events possible as well. One last topic, this is near and dear to my heart. Gazelle is our build file generator tool. If you haven't used it, it reads your source files, generates targets for you, resolves dependencies, and writes out your build files. And you can write an extension for it to support whatever language you like. And there are extensions for several popular languages already. I believe Gazelle is going to be increasingly important for Bazel adoption. We're seeing AI agents write more and more of our code for us, and whether or not we're comfortable with that, sometimes a fast deterministic tool is the best thing to use. So something like Gazelle, wielded by either human or robot, I think is really the right thing to have here. We can automate most of the work for generating build files, but we still want them to be consistent and readable at them ourselves. So to this end, we're strengthening Gazelle for the coming year. Engflow and Vertis Labs are working together on a C++ extension. C++ has been a notable absence in Gazelle's functionality. So that is nearing production readiness, so please check out Wojciech Mazur's talk this afternoon if you'd like to know more about that. We're also improving performance, so check out my lightning talk later today on that topic too. And finally, if you're interested in writing extensions, we're proposing a 2.0 release, which will simplify the extension interface and make that easier. So that's on GitHub discussions, or come find me anywhere around the conference. And with that, I'm going to hand it over to Alex Eagle from Aspect Build. Thank you.
I won't give away the first slide. Hey everybody, it's awesome to be back at BazelCon. So excited to see you're all here. You managed to get through your flights. At least, you know, if you're in the room you have. And sorry to everyone else who's still trying. So I'm here to represent the Bazel community today. I'm one of the founders of the Rules Authors Special Interest Group, along with Chuck Grindle, who's been graciously chairing that committee. He's not at the conference this year. And so I want to talk about a few of the things that we've been doing in the community to try to improve the state of Bazel. Google is doing an awesome job of providing the core and staffing the project, and much appreciation to everyone on that team. There's still so much more to do, and there's so much, and Bazel could be so much better, and that's really our goal. So the first thing I want to talk about is, I'm sure a lot of you, this red box with these 2 URLs in it is something that you've had to fight with. When our builds are not reliable because of a CDN that's down, that's really frustrating. And the central registry is, has pointers in this source.json files out to all of these artifacts to download. The artifacts themselves are not hosted on that on there. So there's a new flag in Bazel 8.4 that lets you add mirrors of the BCR, and Cloudflare has graciously stepped up. Patrick Scott from that team did a great job of actually implementing the registry. Igor Minar, I want to thank for championing the budget since Cloudflare is paying for this, and Fabian Murmertheim, who did some prototyping and design for this. So you can add this flag to your Bazel RC. There is work going on to make this the default, so you'll have more reliable downloads. So thanks again to Cloudflare for that. Broadly, there are a lot of issues in Bazel, and we can go back to the survey results. Thank you all for participating in the surveys. It's really important for the community to know where the problems lie. The number one is implementation and learning curve, probably no surprise to anybody. So that's, of course, a place that we want to try to improve. So what can we do to make this better? The first thing is I did some work, thanks to funding from various people who submit to the Rules Authors Special Interest Group on Open Collective. So adding a few things to the central registry to make it easier to see, you can see a link to projects that need sponsorship, so the little heart icon, things that are deprecated. This is a good suggestion from Yun to show this, so you can avoid modules that you shouldn't be using. API docs, which now can be populated automatically via Stardoc, and attestations of provenance. Thanks to Apu at Google from the distrolist team for pushing this forward. So the blue check mark shows you that the module that's been published is provably built from the sources that it indicates, and so that wasn't tampered with. The API documentation in particular, I added a markdown file under the central registry showing how rules authors can do this. So we now have a place that all of the documentation can be hosted for all of the modules. Makes it easier to do a search and find this. I hope that we'll get more and more rule sets that are publishing documentation here. They may still also be publishing it, as markdown files checked into the repo. The most important thing that we've got going on to improve documentation is from another contributor. He's here at the conference, Alan Mond, posted a blog post. Maybe some of you saw this. It came across on Reddit, basically saying that the Bazel documentation needs some serious work. And I agree. I've been trying to find the right next step to improve this for a couple of years. So Alan and I partnered a little bit together to make this work, and I really appreciate him stepping up to lead this effort. So the first thing that we need to do is make it easier for us as the community to make documentation changes. Of course, you can already send pull requests to the Bazel repo and edit the things underneath the site folder, but you can't see a preview of your change. And so if you're making structural changes, you could easily do something that just doesn't look good. And then you have to wait for somebody at Google to see what that change looks like and either tell you how to make corrections or take over the PR themselves. Of course, that makes things slower. So the Bazel team was agreeable to the idea of moving off of the Google Dev site where, like Google Cloud hosts their documentation. And there were other teams at Google had already done this, like Pigweed. So fortunately, we weren't the first to try this. And so I'm excited to say that we've already paid for an awesome documentation platform called Mintlify. Alan and I worked together to slurp all the documentation out of the Bazel repo, and it is already live at preview.bazel.build. Thanks to Florian for helping move things over. The content is identical, but the presentation is better. The search is there. There's an AI, assistant. Coming soon, very excited that there's a feature, either a couple different vendors that provide it, where we can take all of the answers that are going into Bazel Slack, which is kind of the best documentation that there is for Bazel in a lot of ways, and get them turned into PRs against the documentation automatically. So that would be really exciting. And so that means it's now your turn, because the documentation doesn't just write itself. So please, we will hopefully by Wednesday of this week, we'll have pull requests to the Bazel documentation actually show you a link to the preview right there on your pull request. And the Bazel team has agreed to deal with the volume of PRs that we're likely to send them. So the call to action here is if you see wrong docs, please send the PR. Just hit the pencil button right there on GitHub. If the right answer is on Slack, it would be great if that answer was more discoverable. Although, also thank you to Salesforce and Slack for giving us a free paid version of Slack so all of our messages are findable. All of this I really think is not quite enough, though. So what I've described so far is community efforts by individuals who are passionate about spending nights and weekends to make improvements. Documentation is a great example of something where a project of this size and scale probably deserves some sort of staffing for technical writing. And so for this, I'd like to invite Gunnar to the stage, and my apologies to the AV team for bringing somebody on that we hadn't planned, but it's important that we get an announcement from somebody who's, I represent a vendor, and Google, of course, represents themselves, and what we need is a third party. So thank you, Gunnar, for stepping up.
Thank you. So I am a long-time Bazel user myself. I work for an organization, and also I worked back in the time I worked early on. I worked for an organization that is really heavily adopting Bazel, and it's very important that I think we will be able to continue building on Bazel. So I think it was in Munich a couple of years ago. I reached out to a few people and told them we need to do something. Right, we need to. I would like to see Bazel move to, or Bazel get a foundation around Bazel, so that we are able to secure, build a sustainable ecosystem around it with contributors, and making sure that there's funding for conferences and also for future development, for the rules, for the extensions, and maybe for Bazel itself. So I was involved early on in these discussions. And we settled on the Linux Foundation, and they did a very great job last year organizing BazelCon, and I think this year it looks great again. There are 3 initial members which already committed on funding the foundation. We are looking for 4 more. So thank you for the 3 that already signed up. If you want to participate and contribute to the foundation, send us an email at foundation@bazel.build. There will be an initial meeting on December 4th where we're discussing and brainstorming on the rules, the bylaws, what the foundation is going to provide, etc. Thank you.
Hi, you've met Toby. I'm John Field. I manage the whole spectrum of Bazel and Blaze work at Google. Toby's going to start out with some updates about the State of the Union Bazel.
Okay, it's tradition by now that we give an update what has happened with Bazel in the past year, what will land in the next Bazel release. But before we go into the technical details, we want to celebrate our contributors. Virtually everything that we do is either influenced or relies in other ways on your contributions. And we want to highlight a few of them. And the first one is Chuck. He has been tremendously helpful in BazelCon planning and other things. Unfortunately, he cannot be here, but we still want to thank him. I brought these Bazel rubber ducks again. We will ship you yours, Chuck. I hope you're tuned into the live stream. Thank you for all your work with BazelCon planning, rule author sig, renovate bot, and what else? The next person was already mentioned, Alan. Thank you for your dog's work. This is your duck. Alex already showed the blog post that kickstarted this. I think I want to highlight the way how you did it. You recognized the problem, you made actionable suggestions, you put a lot of work in yourself, and you showed the top of the blog post. I think the bottom was even more interesting, where you conclude, I quote from the blog, "This isn't just another rant post, it's a roadmap. The Bazel community is full of talented developers who have figured out very complex things already." Thank you, Alan, for that, and thank you for the dog's contributions. Third one, Daniel, I don't know where you are. I have a duck for you. Daniel has been super active in the IntelliJ repository in the past year, supporting the Bazel plugin for C-Line. The number of commits is really impressive that you did, and you basically kept it going by yourself. Thank you for your work. And I thought I saw you earlier this morning, but I will put the duck here, and you can collect it later. Thank you. Okay, now into the technical details. Let's start with Bzlmod. Bzlmod is the biggest thing that's going to be delivered with Bazel 9. We are saying Bzlmod is now feature complete. Workspace is gone. The whole journey started 5 years ago. We wrote a design doc called Bazel External Dependencies Overhaul, with the mission statement, figure out the best way to use third-party dependencies in Bazel projects. It took us these 5 years to implement the 40-page design doc. So it took us a while to get there, but I think we're declaring victory now with Bazel 9. And we were able to remove all workspace-based code. A nice side effect for us, deleting 10,000 lines of code always feels great. On the feature side, I want to highlight the addition of new local and remote repository caches, where the local cache allows to share generated contents by Bazel workspaces on the same machine. It's not 100% bug-free yet, so please test it out and tell us what bug remains so that we can land this in one of the Bazel 9 minor releases. We have also added the experimental remote repository cache. This is backed by regular remote caching and supports build without the bytes, hopefully speeding up a lot of builds in the future. The new Facts API allows to store immutable data in the log files. These facts come from outside of the build, such as the internet, and can then be used in subsequent evaluations for smarter caching and checksumming capabilities. Speaking of the log files, we also made them more human readable, even more than last year. We already said this last year. Next to those bigger things that we did for Bzlmod, we did a million smaller things. For example, the Bzlmod command became richer and addressed a lot of bug fixes and feature requests that you guys had. Keep them coming, that we ship an even better version of Bzlmod next year. As mentioned in the community updates, we have now a way to specify module mirrors, and Cloudflare is hosting one. You can also host your own if you want to do this in your own company. We have added support for SALSA attestations, and pre-submits will verify them on the BCR build, enhancing supply chain security. And finally, one more experimental feature for Bzlmod. We have added experimental WebAssembly support for repository rules that allows to write platform-independent tools. We are not sure whether this will stay, so we need some feedback from the community. There were some people who were really eager to get this in, but now we need to get some usage to know how this is going to play out in the future. What this means for you is it's time to migrate to Bzlmod. Workspace is gone. If you have not started your migration yet, today is the best day to start. Maybe it's a good opportunity to do a show of hands who has finished their Bzlmod migration. Okay, approximately a third, fourth, maybe. I will not ask how painful it was, because I know it has been painful for many people. We know that these migrations are often complex and tedious, and we want to help you making this simpler and easier for you. 2 ways I want to highlight. The first one is the new migration script that we created, which basically reads your workspace file, does some Bazel query to check for your direct dependencies, and then iteratively creates a module Bazel file, runs into errors, parses those errors, adds more dependencies, and hopefully by the end of this, your almost done with your migration to Bzlmod. This is a best effort tool. It's unlikely to deliver perfect results under all circumstances, but should cover a lot of scenarios and should reduce the amount of manual work that you have to do for Bzlmod migration by a lot. An alternative to that is AI-assisted migration. For this, Yun wrote an MCP server for the Bazel Central Registry that you can also use outside of the migration to ask questions in your prompts like, update all Bazel modules in my module.bazel file, and we'll just go and do that for you. Or does the latest rules CC version support or come with attestations? On top of that, we have an interactive Python script that allows you to create a plan for a coding agent such as Gemini CLI, and that uses the MCP server to then run through the plan and help you migrate. Give it a try and give us feedback. As always, send us PRs where you see improvements. Switching topics a little bit, Bazel performance is always close to our heart, especially mine. We want to make Bazel as fast as possible and reduce a little bit the resource hunger that Bazel has. One of the most important data structures that Bazel has are so-called nested sets, or dep sets in Starlark. And we had some sophisticated algorithms to memorize their expansion efficiently. And it turns out you don't need to be so sophisticated all the time. And we could simplify this complex piece of code and replace the inner representation with a weakly referenced immutable list. And with that, we saw great memory savings. In pathological cases, up to 20% reduced retained heap, while even having a low single-digit CPU and wall time improvement. So I think this is great work. Thank you, Justin, for doing that. The other data structure that we rewrote is the Merkle tree, or the Merkle tree cache, that we're using during remote execution. The previous implementation had some drawbacks. For one, we have created a large number of intermediate structures that resulted in high peak RAM usage, especially if you were running with a high number of jobs. All of these were in flight, and on the downside then, the cache didn't properly cache subtrees correctly, making its benefits questionable, especially given the complexity. So we decided to focus the Merkle tree cache and only cache composite self-contained artifacts such as run file trees and generated directories. And after upload, we can drop a lot of unnecessary data and only keep the root digests. We tried out these changes with LLVM, and there we see 30% faster builds that use 70% less RAM at peak, which is really great. Thank you, Fabian, for doing that. In order to reduce cold build times, we have been internally experimenting with analysis phase caching or skyframe caching. Shahan will give a talk this afternoon and tell you more about that. And we continued reducing the amount of disk footprint that Bazel has so that you can put an upper bound on a number of on-disk caches now. A while back, we introduced path stripping. We made that more mature now. The idea behind path stripping is to strip irrelevant paths from actions to increase the likelihood of cache hits. We now added a deeper C++ integration, made it better compatible with other Bazel features, and made it easier to use. One user even reported an 84% build time reduction, where the time went down from 38 to 6 minutes. So I think this is really great. Give it a try and give us feedback. In a similar vein, we reduced reanalysis time when build flags changed, leading to faster builds when switching between configurations, for example, opt and fast build. Now for the second half of the State of the Union, John will talk about the build API.
Okay, thanks. It's always gratifying to put together these accomplishments in one place, because when they come out over the years, it's hard to realize what the impact is. So let's go over some of them. This is mostly more on the analysis, sort of semantics end of the spectrum. So on C++ side, we've made include paths more Windows friendly, particularly for MSVC path link limitations. This should be helpful, we hope. Lots of work on enabling C++ 20 module support, mostly community contributions. Thanks very much to a number of folks who made that happen. On Java side, we've improved header compilation, again, to improve cache hit rates. You can see this is a persistent theme. And then also better incremental performance, so things like certain signature changes, like for certain method signature changes, don't affect downstream header actions as they would have in the past. We've added optional single version enforcement, so if you accidentally end up with two instances of the same class on your class path, you can detect that and reject that at build time. On the side of sort of generic functionality, you're seeing symbolic macros. This was a big change. Macros are sort of very powerful, but also very easy to mess things up. Symbolic macros are a tame form of macros. They add things like typed attributes, so they look more like rules. They're integrated with Stardock, so it's easy to treat them, a little easier to treat them like regular rules if you want. There's visibility controls. So trying to strike a balance between expressiveness and ease of understanding and maintenance. We added a set data type to Starlark. A lot of folks have wanted that, so now you have it, and more. So flags are a pretty important part of Bazel, maybe too important, we'll see. But to try to tame flags, we've added a scoping API for Starlark flags to control the propagation through the build graph so they don't go where you don't want them to go and don't affect things like caching again. One important step towards taming flags is something we call project.scl. SCL is a Starlark dialect for configuration. The idea is it's a canonical place for project owners to map targets to flags. And I say project owners because the idea is ordinary developers shouldn't really have to worry about flags. In the long run, they may need to not worry about flags at all, but until flags are entirely suppressed, project.scl is a way to manage them at sort of the team or project level. An interesting feature for very large builds we added was something called dormant dependencies. The idea is to allow expensive targets to be analyzed only on demand. A common scenario where this is useful is dependency injection frameworks, where a lot of the dependencies are kind of dynamically determined. So this gives more control over very large builds where such dependencies can affect build time. Starlarkification. We're seeing very close to the end of the tunnel in this long journey to move native language-specific logic out of the core of Bazel and into Starlark. So all of the rule sets now live in their own repos. The logic for all rules is now largely decoupled from the Bazel kernel. There's still some vestigial code in Bazel, especially for C++, but that's largely encapsulated in a way that we hope will allow most evolution to continue in Starlark. And this is all about making Bazel more open, both inside Google and outside Google, to allow developers to extend things without needing to update the kernel. So as part of this journey, we've disabled auto load in Bazel 9. So you'll now need to load rules explicitly, but the trade-off is that you don't need to rely on internal rule sets. Sort of the next big chunk of work before we can fully declare victory in this space is native flags. Migration is well underway. Things like --CPU, which is a vestige of a long ago era, is starting to disappear. We're well on the way to making that go away. Moving flags from native to Starlark, also moving certain flags into platforms, which are platform related. So a lot of work there, a lot of progress, and a lot of things that I hope will enable community contributions in a way that were difficult before. New thing that you'll hear more about, hopefully in a Birds of a Feather session later, work in progress to add types to Starlark, a much demanded or asked for feature. The idea is that the type system will be compatible with Python 3 types. Bazel 9 will support type syntax, but not yet checking. So the idea is you can start at least annotating code, if you wish, with type syntax, and then we expect checking support to be gradually implemented over the next year or so to be available generally in Bazel 10. We may, depending on how things go, backport support to earlier LTS releases. Right. Other developer experience things, a big shout out to JetBrains for GAing their Bazel plugin for IntelliJ. I think that's been huge for a number of us, so thanks again, JetBrains, for making that happen. Much appreciated. Slightly more mundane, but for any of you who have had to deal with character set issues, we've improved Unicode and case insensitivity support. This is especially useful for Windows dev drives. Basilisk now supports a latest wildcard, so you can, if you want, automatically use the latest or dev versions of releases without having to manually track them and specify them. One thing I wanted to alert folks who are sensitive to what's going on in the code base, you'll see a lot of changes lately related to work in progress to refactor our internal APIs. And the idea of what we're doing there is to more cleanly separate code that accesses services and OS functionality, services being things like remote execution, but also other things, from the core semantics, the core logic, the things that build rules implement. And the idea is over time to define a stable API that separates those two components. And the reason we're doing this is both to simplify maintenance and evolution of the code base by better separating concerns in the code base, but we're also interested in running older logical bits of Blaze, say older build APIs, against current production services. So this supports certain Google requirements. Eventually, it may be useful for others as well. So if you see changes in the code base along these lines, this is why we're doing it. Hopefully, it will be good for everyone. All right, so let Toby close off with an exciting announcement.
So, well, it's time to create Bazel 9 release. We have created the first release candidate. Now we need your help in testing. We can only test with the code that's visible to us. We have a lot of project on our Bazel CI, but I assume all the corner cases are in your company's code. So please test, give us feedback, what's working, what's not working. You can use Basilisk, for example, with use Bazel version equals last RC to do so. Best is obviously to send us patches, but also file issues on GitHub. Start a discussion on Slack or Bazel Discuss when you find something. So please go ahead and test. With that, we're done, but you can ask questions if you have them. We have an audience microphone over here on the right side of the stage. Happy to answer your questions. If you come up to the microphone. There.
So I've got a question about the workload through this.
Is it on?
Hard things. Yeah, so I've got a question about the Merkle trees. I think like the old implementation had this problem where it can like degrade. Like there was this kind of pathological case when you had like a lot of inputs. And like I was wondering if like the new implementation kind of addresses that, because like, I don't know, I feel like this would be a huge thing.
You want to take it?
I don't know the answer.
Okay, so if I understand correctly, you want to dynamically create actions.
No, it's about the Merkle trees. Like, you know, essentially like what would happen is like those nested sets, I remember like for like actions with a lot of inputs with like very like large input trees, like it would just take like forever, like 20 minutes okay. to like calculate.
So the Merkle tree cache improvements that we made should help with these. Okay. Because the large number of inputs are typically from either run files trees or generated directories. And both of them should be addressed with the new changes. So please give it a try and give us feedback. Okay. What's working and what's not.
Awesome, awesome, thank you.
If there are no more questions, then I will hand over to Son, who will give the next talk on lessons on routing remote actions at scale.
All right. That's good. Mic check 1, 2. Can everybody hear me? All right. So we're going to be talking a little bit about remote build execution today. Remote build execution is essentially a technology in Bazel that helps you speed up your builds and tests. What you see over there is what you typically see in a Bazel profile, where the action counts would typically on your local machine is just gonna plateau out on the CPU consumption that you have. But with remote build execution, you can run a lot more build and tests in parallel, so your total build duration get a lot faster, right? And we do this by having Bazel sending all of the actions to a remote server. The remote server then would distribute the workload to a whole bunch of worker and build farm, so that you can leverage the compute power that you have in your data center, your cloud, to speed up your build. Now, this does come with a set of challenges, especially for the server operator, where the workload are very short-lived, they are spiky, they're very hard to bin pack into your server. And the question is, how do we do this efficiently? How do we do this while keeping the costs relatively low? And how do we still maintain a good developer experience? And that's what I'm here to talk about today. My name is Sun. I work as a solution engineer in BuildBuddy, and I will be talking about how at BuildBuddy we have been building toward all of these over the years. First of all, I will be introducing an overall architecture of BuildBuddy, the constraint of BuildBuddy Cloud. Then I will be introduce you throughout all of the optimization technique that we have been introduced over the last few years to optimize our RBE setup. And finally, if we have time, I will touch on some of the future improvement that I hopefully we can make to both Bazel as well as RBE in the future. Right. I have about 30 technical slides ahead, so buckle up. This talk is only 30 minutes, so if I'm rushing a little bit, so that's probably why. First of all, I just want to briefly touch on the BuildBuddy RBE architecture. Similar to the picture I showed you earlier, we operate a BuildBuddy Cloud where we operate both the scheduler, the server side, the remote cache server, as well as the build event server, and then we have our own set of worker where we manage it for our customer. Our worker operate on different set of sandbox technology, isolation technology we call it internally. Some are compatible with typical OCI image container. We also run your action inside isolated Firecracker micro VM. And finally, we offer macOS as for our iOS customer. Now, obviously, that does not meet all of our customer needs. Our customer have very diverse set of requirements. So for that, we also have to support self-hosted executor, and that includes use cases like Windows RBE, running RBE against GPU and FPGA cluster, and then running our RBE workload against bare metal cluster that connected to Raspberry Pi, Arduino to test robotic use cases. So the key takeaway here is that our executor, our worker, support a wide range of isolation options. These isolation options come with different performance trade-off, so they are completely different in terms of the performance overhead. We have two tiers of executor, the managed one on our cloud, and then the self-host one. They come with total different set of configuration, different set of resources available to the different networking condition. So our scheduler would have to account for all of these when putting out the workload. Our managed executor specifically, they need to be highly available. They need to be for performance. Why we need to be cost conscious, otherwise our customer would not have picked us. And all of these are stacked on top of traditional CI workload where you typically would have to operate in traditional CI like GitHub CI or GitLab CI, where the workload is relatively spiky, so you would never be able to get like really high resource utilization rate. And then it's really hard to bin pack everything effectively to make advantage out of your infrastructure available, and then scale up as well, right? It's really challenging. So to solve all this, the first piece of the puzzle that I want to introduce is our scheduler. Our scheduler is called the Sparrow scheduler. It's a model after a paper out of Stanford in 2013. But essentially, this diagram essentially trying to describe, at least I attempt to describe, our executor over here are organized in different pools. Every single actions coming out of Bazel to our server often come with a designated pool of executor that it want to run on. If there's no pool, then we simply pick the default pool. Out of the default pool, we pick 3 executor to queue the action out of. So notice that the queue don't live on the server side, but the queue actually live on each of the executor. We don't pick the 3 executor totally randomly, but we use a bias randomization based on the resource available on each executor. What that essentially means is that if an executor was configured with a lot more CPU and a lot more memory, then it will get picked more often, right? And that's give us a sense of load balancing when distributing your remote action to these workers. And the idea of this entire setup is to minimize the tail latencies where we execute your actions, as well as to increase the resource utilization rate. So what happened when an executor resource become available? It will start to dequeue your action locally, and then it will call a lightweighted RPC in our server to obtain an exclusive lease of the task. This you can think of this as just a distributed lock, right? And this assure that the executor successfully obtained the exclusive right to execute your action. What happened when the second executor called the same API? It will fail, right? And therefore, it will move on to pick the next task in the queue. In the background thread, we also implement eager trimming of these queue, so that if the next executor has to wait for a while and then come back to a queue, it does not have to churn through a backlog of already claimed remote actions, right? So all these help improve the tail latency of the setup by quite a bit. Now, on top of that, if in case all the executors were quite busy at the time, the queue time will go up, and our monitoring system will catch that case and kick off the autoscaler. The autoscaler will spin up new instances of our executor, and our scheduler is built in a logic where it allows newly spun up executor to steal the action that are being queued inside older executor. We call this work stealing, and this helps us scaling up very effectively to combat a lot of spiky workload incoming, right? But yeah, this helps us improve the queue time for our customer, as well as keeping our infrastructure cost low, because now we don't have to over provision in account for the spiky workload. All right, talking about keeping the cost low, I do want to mention that we do implement action merging. This was actually, there was actually a talk about this given by Kristen Scott. I don't know if Kristen is here. Kristen is from Canva. Last year he gave a talk about action deduplication. So I will not go into detail how this works, but essentially I would just summarize that using action merging, you avoid duplicating the execution for multiple different requests coming, identical requests coming from different CI jobs, right? So this helps you save a lot of compute compared to traditional CI system, as well as compared to local execution of Bazel on those traditional CI systems. So overall, by adopting RBE, our customer usually see a saving in compute resources. Now, Toby mentioned earlier about path stripping, which I think the original name of that feature is path mapping. This feature is very interesting. It does come with a final saving, but in terms of remote execution, it does cause Bazel to send duplicated execution requests. I only draw 3 on this diagram, but realistically, we have seen cases where Bazel sent us anywhere between 3 to 10 duplicated execution requests for every single build. So without action merging, you would not be able to do path mapping effectively when you turn on Bazel 9 with path stripping enabled. And this matters a lot, especially for the C++ crowd, where folks often have to transition between different platforms to test their build differently. So yeah, definitely take this into account before you enable path mapping with RBE turn on. And one problem that Kristen Scott mentioned last year was that when you do action merging and your RBE worker had some sort of issue, then all of your CI pipeline kind of gets stuck, because all of the CI pipeline would be waiting for the execution result coming out of one bad machine, right? That caused a lot of flakiness, a lot of issue. On our end, we experienced this with a few customers last year, and our final solution somewhere, I think middle of last year, was that we would introduce speculative execution, and that's called hedging, right? We introduced two config node. One is hash delay, and one is hash count. And essentially, after the initial execution started, once we pass the hash delay duration, we will start to speculate. So we essentially spin up multiple instances of the same actions, and whatever finish first, we will use that as a result and cancel the others. So this ensure our customer of the reliability of the entire RBE system while keeping the action merging saving alive, right? So not only that we operate internal cost saving, it's also come with a high reliability as well, thanks to the hedging implementation. I also want to call out, we do support remote action canceling. This is surprisingly not every RBE implementation out there do support this, so I had to add this in. We do this currently by catching the build events coming into our server. At the end of the build, Bazel would often send a finish event to our server, and with the finish event, there's an exit code. If the exit code happened to be interrupted, which often signal sigint in Linux or Control-C if you are running on your laptop, then we will attempt to cancel all of the remote action that is related to that invocation, right? Why does it matter? Because a lot of our customers nowadays are doing merge queue, right? You would try to queue up your PR for merging on whatever the code vendor that you're trying to do. With merge queue comes speculative CI running, and because of the speculation, often you queue up 10 CI pipelines speculative at a time, and what if in front of that pipeline one job were to fail, then you would have to cancel the other 9 speculative pipeline, and when that cancel happen, this particular feature would help you save a lot in terms of compute resources instead of keep those action running. So yeah, this seems to be trivial, but I was a little bit surprised that it was lacking. Next, I will be talking about the bin packing challenges. Bazel action do not come in the same shape and sizes, right? A typical CC compile action would consume a lot less resources than CC link. It's just the nature of the beast. CC link is usually the final step of a very big ETL pipeline, right? And it would consume a lot more resources. Taskrunner is a big one, right? Tests come in various shape and size as well, and we have seen a lot of people jam up giant test actions with a lot of test suite inside them, and they can take anywhere between multiple minutes to hours, right? And the special thing about BuildBuddy is that we also support running end-to-end and integration tests in our infrastructure, so those would even consume more resources. So all the actions are being sent to our server are really hard to bin pack because we don't really know how much resources they're going to consume, right? So what do? We implement auto-profiling. All the remote action coming into our server are automatically profiled. On the left-hand side there, you can see what we recorded for each of the remote actions sent to our server. That includes the peak memory consumption, the amount of CPU consumption, this read, this write, and then we also present all of these information onto our UI if you were to inspect these actions, right? I also want to call out, we also record all the pressure stall duration. These are often the signal of overly bin packing on a Linux system. So we do use this to tune our scheduler to be more effective and avoid overly bin pack, because when you start overly packing one single worker, you start seeing test flakiness happen, right? Action flakiness start to happen. So yeah, all these profiling data, our executor will try to capture them automatically, and then in the action result, there's a field called execution metadata, and in execution metadata, there's auxiliary metadata, and it happened to be an array that you can shove anything in. So we shove the entire profiling metadata in there, and we store it into our server. We return it to Bazel so that Bazel can function normally. But for the profiling data, we will store it in a cache, right? All the hot actions will have the profiling data stored in the cache. That cache will later on use to schedule similar actions. In case the action is not in the hot cache of the profiling data, we also store it in our analytical database ClickHouse, and then we train a simple linear regression model to predict the resource consumption of those actions. And the result is that here you can see for every single remote action, we do display the estimated resource usage that our model output and the actual resource consumption. And we use this to bin pack our executor effectively. You can see they are pretty close, right? So yeah, we were able to solve this problem with auto-profiling. Okay, next, I want to talk a little bit about cold start. Remote action are very similar to serverless application, Lambda, AWS Lambda, where they also experience cold start. In particular, with BuildBuddy, before the action were to run, we had to do two things. One is download the container image that our customer want to use to run those actions. And second of all, download the input trees that the action used to run, right? And the input tree came from our remote server, and the container image came from any container registry out there. And in the typical cold start, you can see at the bottom, we have to spend a lot of time in prepare runner, which is essentially downloading the container image, and then we spend a lot of time in fetching the input, and then the actual run of the action command is tiny, right? So how do we solve this? We solve this using something called affinity routing. This is a feature we also built into our scheduler. For every single action coming in, we built a routing key. The routing key consists of the instance name. There's essentially a Bazel flag that lets the user play around. And then it uses the platform information of your actions. There's the execution platform that you have to configure when you use RBE. And finally, it uses a primary output. The execution platform contains information like container image, operating system, CPU, and then the executor pool that you want to target. That's not very interesting, but the primary output is very interesting because Bazel does guarantee a property that the primary output cannot be duplicated between actions, right? So the primary output can be, there can only be one, right? Because inside the output path, if you take a look at the bottom there, we have the platform information, this is the target platform, not the exact platform. So that's very interesting. the target label, the target that you are building, as well as the action that you are building, and then finally the output coming out of that actions, right? So this is guaranteed to be unique within a build, within a single invocation. It's guaranteed to be unique. And we use this to route different actions to different set of workers, right? So, but as a result, similar actions, which essentially, the same target, the same output file, will be routed to the same executor. And therefore, when we have to download container image, when we have to download input, often we only have to download the delta, right? The only stuff that has been changed. And this helps speed up the majority of our action execution. Now, that's not enough. We also support a feature called runner recycling. Runner are essentially the sandbox that we use to execute your action on our executor. Most runner are ephemeral, right? You use them once, you throw them away, we spin up the new one. We're in charge of keeping that efficient. However, there are cases where you do want to have recycle runner. They are not as hermetic as ephemeral runner, but they're pretty good reason why you would want to use them. First of all, persistent worker, right? We have languages like JVM where spinning up a new instance of the JVM process can cost a little bit of time. There are compilers out there like Swift-C compiler use local cache on the file system to speed up the compiling process. We have customer running tests against different level of database, MySQL, Redis, Postgres, etc. We have customer running end-to-end UI tests using headless Chrome. So they spin up the entire browser, and then they try to open their UI element on it. And finally, with our Firecracker support, we offer the entire Docker daemon. So we have customer running Docker Compose, or what you call it, test container, on these recycle runners, right? So the benefit of recycling these runners is like you're still gonna keep those container in there, inside the runner. You don't have to re-download them. You don't need to reseed your database, right? Your database is already seeded with the previous testing data. You only need to clean up the delta between two runs. Now, how is this implemented? On the Bazel side, it's very simple. We give you exact properties that you can add into your platform definition called recycle runner. Or if you were to turn on persistent worker and your rule set does support persistent worker, then it's enabled automatically. Now, if the affinity routing help the action find the executor, then the runner key on each of the executor help the executor find the correct container or the correct micro VM to run your action in, right? So the other one help us select between different VM, different hosts, and then this one help us select which sandbox do we use to run your action on a single machine. And by calculating this runner key, we were able to effectively speed up the recycle runner as well as increasing the hit rates for the recycle runner. All the recycle runner are kept tracked in a runner pool on the machine, and they are evicted on an RRU basis. Experimentally, with a lot of usage of remote persistent worker, we also see a demand in terms of very low latency actions. And to meet this demand, we're currently experimenting with recording the exact list of machines that recently successfully ran those persistent worker in the past, right? So we're maintaining, on our scheduler side, we would maintain a queue of most recently successful used workers, and then we would route the action over there. This take precedent over the previous mentioned affinity routing, and this helps us keep the latency down to several hundred milliseconds when using persistent worker. All right, we also have, so let's circle back a little bit. I did mention that we have managed executor and self-host executor. One of the primary use cases of self-host executors among our customer is to support different custom resources. The custom resources can be anything between custom GPUs, custom FPGA. As I mentioned, we do have robotic customer that are using it to do various different testing that I don't really understand. We have various different iOS customers as well. They have emulators running, right? They have tests running on those emulators. Some tests can use a fraction of the emulator and can coexist with other tests, but some tests require the entire emulator to run, right? So how do we solve this problem? We solve this problem by enable our customer to define custom resources. On the executor side, the self-host operator can configure different string and float value that indicate how much resources are available on each of the executor. And on the Bazel side, they can define in each of their build actions, hey, how much of this specific resource are we consuming, right? And all of these gonna match up in our remote action scheduler, so that we know, where to route the task to. So that's for our self-managed, self-host executor. On our managed executor, on the other hand, we need to solve a different set of problem, which is multi-tenancies, right? We have a lot of customer leveraging our cloud instances to run their build action every day. We need to make sure that we don't run into typical distributed multi-tenancy problem like noisy neighbor. Imagine you have one customer sending you thousands and thousands of actions, and then you have one open source maintainer just sending you a lowly, let's say 5 or 10 actions. You still want to give them a fair chance of running, right? For this reason, instead of maintaining one single queue on each executor, we actually maintain multiple queues, one for each tenant on each of our executors, right? And then we round robin between the queue. Again, the resource consumption is already solved previously by profiling, so we don't have that set of problem. These queue, worth to mention that these queue are actually priority queue, so that we can support the flag in Bazel called remote execution priority. If you have not tried this out, I definitely recommend you checking it out, because it allows you to set up multiple set of different builds with different priorities. Typically, what we see with our customer is that they would have 3 sets. One is background cron job that spin up some build. One is CI, and one is user kickoff build. And usually you want to give your user the highest priority so that the build feels very responsive. And then the cron job builds the lowest priority so that if there's any resource contention, then they can wait a little bit more. How am I doing on time? Am I over time? Anyway, I have been rushing a little bit, I know that. All right, thank you. Yeah, with that said, that's all the features that I just want to walk you through today. I do want to mention what we want to accomplish in the future. Today, what happens when Bazel try to schedule these remote action to the server is that you have a build graph. Bazel would have a certain set of worker, which usually map to your local CPU, and then those worker would just walk through the graph. Every time it sees something that needs to be built, it will send it over to our server. It will wait for the result. The result came back. It used the result to calculate the next node in the graph, and then so on, right, until it finished building everything that you requested for. The problem with this is that there's a lot of chattiness between server and client, right? Bazel always have to wait for the result before it knows if the next node in the graph existed or not. There's no opportunity for us to know what the shape of the graph gonna be, so we cannot co-locate actions that depend on each other next to each other, so that we can avoid cache transferring between different set of worker. We can. There's also no opportunity for us to speculate in terms of scheduling, right? If we were to know, like, hey, there are 3 nodes ahead of time after this action complete, then we can speculate to spin up those sandbox earlier. So one of the future items I think we do want to work on is a graph API in remote execution, where Bazel can just send us the entire shape of the graph without knowing the intricate details of like, hey, which input hash to what, and then let us figure out how to handle the entire graph, right? We also have various different items that we do want to improve in our existing product. So definitely, if you're interested in working on any of this, come talk to us. We will be in the booth over there. And we are hosting Buildbuddy happy hours. So do sign up, right? That's it. That's it, my talk. Any question? And the mic is over there, if anybody. If there is no question, Toby? Yeah?
If there's no question, then we have a 15-minute break. Check out the solution showcase next door. Yay. And if you're talking after the break, get ready and get your microphone set up. Thank you.
window won't like fill everything. It would just like be.
What is this, Google Slides?
Yeah, it's Google Slides. Do you happen to know how to do it?
Yes.
Yeah. 1, 2, 3. Yeah, I've run this. Yeah. See?
No, not minimize max.
Okay, let's start again. Next talk by Alex, deploying high-performance remote execution setup in multi-region topology. Thank you, Alex.
Cool. Well, hello, my name is Alex. I'm from Dropbox, and I want to talk to you a bit about how we deploy remote execution with clusters all around the world. A bit about myself, I'm the TL of a team called Build Toolchain, so we essentially maintain the health of our monorepo, which is essentially a Bazel shop. And then obviously we...
Main use case is in the invocation and root cause analysis, and also you can track that over time as well. Worth noting that the last BEP event called build tool logs actually will tell you where you can find other data produced by the build, like where to find exec log. You may be familiar with the terms BEP and BES. So to add to confusion, BEP implementation actually has a term called build event stream, which is not to be confused with build event service. So build event service protocol is a generic gRPC service for publishing build events. The BES protocol is independent of the BEP, and it treats BEP events as opaque bytes. Internally at Google, BES is used not just for Bazel events, and also if you're working with other build systems, that may be a way to ship events to your other internal analytics tools. The BEP upload mode is another important concept to consider some of the nuances and implications of. So build event protocol events are uploaded in a continuous stream, hence the build event stream terminology that I talked about. BES upload mode is a flag that controls BEP events and how they are uploaded to this BES backend. When the flag is set to fully async, Bazel uploads BEP events asynchronously, so that means that the Bazel command can return to the user, and the build events will continue to be uploaded while the build is running in the background. The build itself is not delayed by the upload process, which of course is a win for performance and for interactive builds, but not so great for CI. So it's a reliability versus speed trade-off. At Google, BES upload mode equals fully async by default. But not everyone has pristine CI infrastructure, and it can cause issues, as we noticed. So since the upload is asynchronous and the command exits without waiting for acknowledgements, there's a possibility that some events might be lost in the background. And upload process, especially if it encounters issues, there's a higher chance of that happening. Many Bazel users use ephemeral CI instances, and as such, the daemon dies after the run. So changing to fully async by default would cause things to break. During this talk prep, Toby asked us if we should set this by default for all Bazel users, and so we said, not just yet, let us work within the community and figure out how we can avoid breaking things and ultimately implementing better tools to control the client side of Bazel. So just to wrap this up, fully async prioritizes build speed over guaranteed delivery of the BEP events, and if complete and reliable BP data is critical, set the upload mode to wait for upload complete. In BP, action executed we found is also very instrumental in root cause analysis, but only for the failed action. So it does not have the data on everything else because it would be overwhelming. Instead, you will find it in the execution log. There is, however, because Bazel is so flexible and configurable, a way for you to do that, and you can actually set this flag, build event publish all actions default to true, but should you? So one of our customers, could probably be in the room here, tried this. They adopted Bazel in 2017, so they weren't as familiar with the execution log that was added later. And so when setting that flag to true, they've seen their binary files produced went from 8 megabytes to 480 megabytes. For a single indication, a 60 times increase. So don't do that. Instead, go look in the execution log, which Eloise will tell you more about.
Perfect. So the execution log. This is Bazel's black box. It's a protobuf-based log that provides a complete and faithful record of what was actually executed during a build. Unlike other data sources, like the BEP or Bazel profile, the execution log shows exactly what happened. It captures every external process that Bazel runs, like the command line, environment variables, inputs and outputs, execution strategy, timing, and cache hits or misses. If you want to understand why Bazel behaved the way that it did, this is where you look. It makes it a highly reliable source for debugging unexpected Bazel behavior. Now, here's the catch. It's not produced automatically, so you have to explicitly enable it with a flag. So execution log binary file, execution log JSON file, or the newer and more recommended exec log compact file if you're wanting to gather the exec log more regularly. And this one was introduced in Bazel 7.1, so make sure you're on 7.1 or newer. Because the compact format is significantly more efficient. To make sense of exec logs, Bazel also provides a parser, but you have to build it from source. So you can then use this to convert logs into a human-readable format, and the parser aligns actions between two builds, making it great for comparing two different builds. The log format is extremely verbose, and we have actually learned that the hard way. Like I mentioned before, Canva has started the journey to understand a little bit more about our build performance. And when we first tried ingesting some of the exec log data internally, it actually completely overwhelmed our observability system in a day, causing an incident. And this was due to the high cardinality of the data. So these logs can grow from a few megabytes to even gigabytes, depending on how many actions your build runs. That said, it is an extremely rich source of telemetry. And now that we are ingesting the data a little bit more thoughtfully, we have been able to look at spawn-related data from the exec log, like Bazel spawn duration, Bazel spawn cache hits, and some other tracing data. And we can aggregate this and slice and dice it in a matter of ways that we see fit. It has allowed us to start answering questions like, which targets could be broken up for better parallelism? Where are cache invalidations happening and why? Or where in the build process are developers spending most time waiting? It's one of the most powerful tools that we have for diagnosing build performance. But it's also a reminder that more data isn't always better. You need to sample selectively, store it thoughtfully, and know where you're looking. Otherwise, ingesting this data can become a bottleneck of its own. So let's take a look at putting the exec log to the test. So as a DevX engineer, we often get questions from other engineers like, why did I get a cache hit here but not there? And this one from Rush is a perfect example. Hey, I was expecting a cache hit between my DevBox and CI on this build. Why is it rebuilding? Now, that is a reasonable question because at Canva, our RBE cluster is shared between CI and our cloud-based dev environments. So if the inputs are identical, we should be seeing a cache hit. When we don't, it is a sign that something subtle has changed. Maybe an environment variable, a timestamp, or even a flag. The problem is Bazel's caching depends on determinism. It assumes that the same inputs always produce the same outputs. So when that assumption breaks, caching breaks too. And we start seeing unnecessary rebuilds. So let's take a closer look at the target Rush was actually running. Here we've got a simple looking Go test called paths test. And at first glance, to the naive engineer, nothing about this target seems overly suspicious. So let's dig a little deeper. Rush mentioned that she was getting a cache hit in CI. So the first thing we'll do is reproduce that build and capture its execution log. To do that, we temporarily override our CI build logic to upload the exec log as an artifact. Then we can download execlog ci.log. Next, we will do the same locally from our DevBox. We'll run a Bazel clean to make sure nothing is cached locally, then rebuild the same target while passing the execlog flag again. That gives us our second execlog, execlog devbox.log, which we'll then use to compare the two runs. Now, with both logs collected, we need a way to make sense of them. For that, we'll use Bazel's execlog parser. But remember, we need to build it. So we clone the Bazel repo and build the execlog parser ourselves. Once we've got the binary, we can run it over both logs. It converts them into a readable format and aligns the actions across the two builds, so they're easier to diff. And that's what we're going to do. So after running the parser, we can now diff the two builds side by side. This lets us see where the two executions diverged. And here's what we found. Aha, here it is. A clear difference between the two environments. I can see a few sniggers in the crowd because it was pretty obvious what the issue was to us. However, to a naive engineer, maybe not. So the home environment variable has two completely different values, one from CI and one from the DevBox. So even though everything else was identical, this variation was enough to invalidate the cache. And luckily for us, we were able to capture this in the execution log because other data sources, such as the BEP, don't include an environment variable log. And unsurprisingly, there is our culprit, the env inherent equals home line. By inheriting home, this target was introducing a non-deterministic input that changed between environments. The fix is really simple. Instead of inheriting home, we can explicitly set it through the target's env field to a constant value because actually in this test, the home value was never really used. So this was a really easy win for us. But by changing this value, it makes the test deterministic again and ensures that we can share the cache between CI and dev environments. Now, the execution log graph. I think that this is a lesser known Bazel data source. However, it gives us a structural view of how actions actually depend on each other during execution. Each node is a recorded action, and the edges show how they connect. What makes this valuable is that it doesn't just show what ran, but how much each action contributed to the critical path, meaning it can quantify the drag on your build. You can then, for instance, understand how much time you'd saved if you could optimize or remove a specific node. One of the most interesting things that we learned from Google is that they use this data to understand whether the critical path is unique or one of many. So if you're optimizing an action that sits on one of several near critical paths, you might not actually be moving the needle much, as another path could immediately become the new bottleneck. Internally, they ingest this data, the execution log graph, on every build and analyze it to figure out which optimizations are truly worth it. And then throw away the data after a day because its value is in guiding decisions, not long-term storage. Moving on to another use case in optimizing builds, we can talk about adding a new dependency. And for this, often the real question isn't how long it takes to build, but it's how far the impact spreads. So, to assess the impact of dependencies in the build graph, we advise first use a Bazel query to find your most dependent on targets. These are the ones that are central in your build graph. If those change, they can invalidate a large part of the repo. Then you can combine that with some analytical data, like cache miss rates or execution frequency. And with this, you can then see which of those targets are actually triggering rebuilds. And finally, remember, a new dependency might not slow execution, but it can increase invalidation risk or fetch overhead, especially if it's large or non-hermetic. So impact is not always about runtime, but it's also about reach and build frequency.
Eloise talked about Bazel query as one of the tools also worth noting when investigating. There are actually 3 of them. Billy covered these in his Bazel training this Sunday. And to give you a sense of when to use which, we created this chart, which you can reference notes. We'll share notes from this talk as well. These queries are helpful in doing performance debugging. So you can use Bazel query to understand targets and their dependencies. It will query everything and go fast. You can use configuration query, cquery, to debug dependency graphs, and action query, aquery, to get the fine-grained details of every build for the actions for that build. Given Bazel has evolved over 10 years, so its data outputs. And so you can find similar data, but with different granularity in different data sources. When investigating cache misses, BP will give you a good high-level data, but it may not be actionable. Cache writes, for example, are useful in understanding cache miss analysis, but they're not in BP. You can find them and more other granular data in execution log. So you can combine all these tools, or you can look for other solutions. And so to make things simpler for ourselves and our customers, eventually we created the RBE profile that has more consolidated and richer data for interactive and time series data analysis. So how do we construct it? We collect events which are processed while like various remote execution API requests are run by our services, and we accumulate that in our analytics store. We've also optimized it for analysis with a single row per action, and we offer this as something that you can load it into your Lakehouse or OLAP tool like Databricks, Snowflake, ClickHouse, or use it in the online environment. And so to show you how this data comes together, our product manager, Jorge, created this game to teach our employees and our customers how to investigate Bazel issues. All right, let's play the game. So build forensics is what we've called it, and you are now all part of our investigation journey. Yeah. All right. So you're investigator on the case, and you have a regression mystery. And over the past few weeks, you're hearing complaints that CI just feels slower. So you pull up the build times, and you look that, in fact, actually, there's P95 times that creeping up a bit. The overall cache hit, though, looks kind of stable. And so let's dive deeper into this analysis. As we talked about Bazel data, you can find different data sets in different places. So, of course, this data set that we can look at is available in the BP, and it is also available in the RBE profile. And so the first rule of forensics is to narrow your suspects. So based on the evidence, which targets will be the prime suspects. So we'll evaluate here, and worth noting that a combination of cache misses as well as the duration is an important thing to note, because you may not be optimizing the right caches. And so as looking here, we can see that some actions are taking significantly larger hits than others. And also there is a more sharp decline in cache hits for a couple of actions here. So any guesses here, any call outs? Which of these may be the culprit and the first action to look at? I heard that there somewhere, model builder, I heard that. All right, let's do this. And in fact, that is the model builder, and it is also the fact that it's subtle because build time is decreasing, but also cache hits are reducing more sharply than others. It is also often helpful to compare based on the additional data sets, so execution duration over time and cache hit rate over time. Again, where can you find this data? This data you can actually find in the execution log as well as the RBE profile. And so, in looking at this chart, you can see quite sharp increase in the time, specifically for CPP compile action as well as general. And then inspecting the cache side of things, you can see that there's definitely much sharper decline in cache hits for general to 0, while CPP compile is also steadily declining. So these are certainly worth digging deeper in for analysis. And so we're going to look into these actions and keep going. So now let's start hypothesizing what is a culprit, at least for one of these. And so input file growth is often blamed for the increase in build times, and sometimes rightfully so, sometimes not. And so in this case, we can see that for general, it actually hasn't changed. So no, that's not the suspect. But for CPP compile, we could assume that there's something for us to investigate further in the input file growth, because there's certainly correlation between cache hit rate and the file growth as well. And so we'll choose this and keep going. And that takes us to a very interesting way to dig into what is actually the root cause for general. This is the data that you can see, the last 10 invocations, and what type of issues are we dealing with here. So I'm actually very curious to see also any kind of like yell outs, if there's any ideas, which of these may be causing a problem here. Any suspects of these issues? Are we dealing with bad configured actions, non-determinism issues, input file dependency issues? Non-determinism. Okay, and I've got that one hand here too. All right, so in fact, this is the culprit. And so we have found the serial killer of Bazel builds, because as you all know, non-determinism is in fact quite significant one. And why serial killer? Because Eloise in prep for this talk told me that she's done extensive research on serial killers. And so now she knows both in life and in Bazel. So you could speak to her about that more. And so why? So Eloise showed you one example of a non-determinism issue that they've encountered at Canva. This example we see often as well. And similarly, feel free to yell out if which of these are the culprits here. I'm definitely curious to see if many of you have seen similar issues as well. Timestamps, yes, the timestamps. In fact, that will explain why the cache hit went to 0. So it wasn't just slowly reducing, it went exactly to 0. All right, so you've mastered the case. Now you can actually play in our analytics playground, which we use an open source Selenium data so that folks can start investigating and running queries, getting their own assessment. We also have this game you can play at our booth as well. And the analytics playground, is just to give you an idea, is going to look something like this, where you can run queries, so you can inspect the query results and look at various charts for experimentation. All right, so now that you've mastered this, you can stop by the Angelo booth and play the game, and also you'll test knowledge of your evidence, and we'll send you Cluzel, which is our custom-designed Bazel investigation board game. Come to our game night tonight to play it, and also sign up to receive one for your office. Of course, because we're relentless Bazel geeks at Angelo. Oh, yeah. Well, we got a few more interesting things to wrap up, so let's see if we can get the slides back up. All right. Where is? Ah, right here. Okay. So wrapping this up and putting it together, there are various data sources. You can use them for a variety of investigations. We pulled this chart together as well, just to have a quick sheet. What data granularity is available in which source? What are the common use cases for which source as well? And so as you start learning more how to do Bazel investigations, you'll be able to use this as a quick reference. And we'll publish a blog with this information as well.
Okay, so most of the people in this room, I assume, would be DevX engineers. We are the ones who can really get into the weeds of Bazel, the build graph, the flags, the logs. But product engineers know their targets much better than we do. And that means that they share the responsibility for keeping builds healthy and fast. So we, as DevX engineers, should be encouraging teams to do a few things. Firstly, product engineers should understand that small changes in a central target can ripple through thousands of builds. And therefore, we should be advising teams to understand what depends on what. This poses the question, could a target be broken up a little bit more granularly? And what is the function of each new dependency brought in? Could we be preventing those costly rebuild cascades by copying a small piece of code from a third-party dependency rather than pulling in the entire library, especially if you're only using one or two functions? Product engineers are the best place to make these trade-offs because they understand the context of their own code. Secondly, they could use Bazel Query to stay informed. Running simple queries regularly gives visibility into how dependencies evolve over time. It's an easy way for teams to catch unnecessary or accidental dependencies early. Thirdly, ensure they are familiar with profiles to visualize performance. The JSON trace profile is a great entry point for product engineers to see where time is being spent. It's visual, it's approachable, and it helps reveal bottlenecks in the build process. And finally, build without the bytes. Flags like remote download minimal help you download only what you need, reducing some overhead and shrinking the download section in your build dramatically. So while DevX engineers can optimize Bazel itself, product engineers play a huge role in keeping builds efficient by owning their dependencies, using queries, and understanding their build data. And that's a wrap. Thank you for listening, and thank you for all of the people on this slide for their help in the research that went into putting this presentation together. Thank you.
Thank you. Next up, we have a series of lightning talks. Our first one is Rahul, who will tell us about how to save money by running CI on Spot instances.
Good to go. This is the clicker, right? Okay. Can I not see it? Notes is fine, I can see that down there. Yeah. All right. Hey, everyone. I'm Rahul. I'm part of Platforms Engineering at Clean. Today, I'm going to present an interesting topic of how we run our entire CI fleet on Spot instances while keeping the reliability and availability guarantees of as if we are running on reserved compute. So just a brief step into what CI at Clean looks like. We are a monorepo, as is the case with all Bazel customers. We are Python, Java, Go, and TypeScript primarily. We are a fully GCP shop, and we run most of our CI on GitHub Actions. So Glean has had an interesting story in terms of our growth. We have grown 5x over the last year and a half. Our engineers have more than 5x from 100 to close to 500 as of today. Our builds have also followed a similar trend. We are growing around 8% month on month in both our engineers and builds. But as you can clearly see from the cost graph, the growth in cost has not been linear. It has followed exponential curves. We have tried to battle these day in and day out, but we have had a hard time taming this down. This is our scale of CI. We run around 60 million tests a month, and our P95 runtimes look to be around 42 minutes. So this is a brief aside on what our CI infrastructure used to look like over the last year and a half. Cut to mid of last year, we were half of our current build graph. We were 1/3 of our developer count, and we were running 1/3 of our current build counts as well. This was a vertically scaled runner pool. Pretty large machines, 32 core, 128 gigs. We were a very naive GCS bucket-backed cache, and as a result of all of this, we saw insane queue times, like around 40 minutes. Engineers would just schedule builds and forget about them. Our P95 build and test times were around a couple of hours, and still our cost was growing 18% month on month. Cut to early this year, in January, we were at 50% less actions in terms of number of targets. We were half of our current developer strength, and half in the number of builds as well. We had moved on to a managed instance group on GCP, which used custom auto scaling signals. We had moved on to build by remote cache, no remote execution yet. We were seeing cache hit rates of around 85%, pretty sane queue times of around 6 minutes, not that great, but still not 40 minutes. And our P95 times had already dropped to half of where they were. Sounded great, but actually the challenge was we were still growing 11% month on month on cost, which made us realize pretty quickly that we were buying bigger boxes faster than we were scaling out inefficiencies in the system. So what we eventually realized was vertical scaling wouldn't really work for us going forward. At some point in time, our projected bill was around $500,000 for just running CI at the current scale. We had upgraded from 32 to 48 core machines, 30% higher, obviously had gains, but we simply saw the bottleneck shift. SQL contention, bad tests, notorious TypeScript Webpack builds taking up or hogging all of the resources. And the most startling observation for us was that we were underutilizing 70% of our node pools. So we were just literally paying GCP for idle resources. And we quickly plotted out what the gains would look like as we bump up to the next higher tier of machines. And we had reached an inflection point where we would outpace the growth in cost by not gaining anything on performance. So further upgrades were just steep cost jumps. So we did what everyone sane in this room already does. We embraced full remote execution for our graph. It had a phenomenal performance in the first month. We had almost halved our build times. Our queue times became pretty much in the order of seconds, and everything looked great. I think we celebrated too early because the next month we received the bill for GCP. So from April to June of this year, our cost almost 2x'd, tracking build volume but not efficiency. So we were scratching our heads, what's going on? Because at this rate, we were projected to hit $1 million CI spend, which was a tough conversation to have with our CEO. The cause, we were over-eagerly scaling our node pools. And since we were running on non-spot workers, we were paying for reserve compute without actually using them well enough. In addition to this, since we ran on GitHub Actions, we needed to maintain a static runner pool for us to be able to run the Bazel clients, which added an overhead. And on top of that, every build-bound pod has to maintain a runner worker configuration, which added a 20% overhead. So our peak monthly spend for the month of May was around $42,000. And with our growth in engineering and build volume headcount, we were projected to hit $1 million. So the question was, how do we solve for this? So we looked at the most obvious cost lever inside of our CI infrastructure, which was compute. And Spot instance has a very great property, which everyone will appreciate. It's 70% cheaper. But that 70% cheaper comes at a cost, which is essentially, it's flaky. You can't guarantee availability, preemptions do happen, so we have to make CI safe for Spot usage, and that is where we ended up investing most of our efforts over the last 6 months. So these are the 4 levers, which I'll talk about in some more detail, around what helped us make CI safe on Spot. So the first one was scaling by intent and not by CPU. Kubernetes usually relies on resource metrics to be able to determine scale up, scale down events, but CI traffic is not really that linear to follow. CI follows developer velocity. At 3 p.m. PST, 100 people will decide to submit a build and go off for the day, and that has CI spikes and surges. So the insight was queue length is the appropriate metric for us to be able to determine when to scale up and scale down. So the solution, our Bzlmod autoscaler now relies on the number of actions queued over the last 4 minutes. 4 minutes is a heuristic which worked for us, may not work for you, but at our scale that performs best. So we would now preemptively scale up CPU as we were growing. And we also leverage platform signals. For example, TypeScript workloads are still notorious for us, so we have to schedule them on larger spec runners. But now we have better signals to ensure we have availability. So the result, smoother scaling, fewer CI bursts, less pages. So next one was phase scaling without orphaning builds in flight. So this is more related to how we deal with our GitHub runner pool, which is not on Spot as of today. So GCP gives us a 90-second shutdown limit where you can execute shutdown scripts, but 90 seconds, as most of us know, is not enough for a Bazel build to terminate. So builds can, compute can be reclaimed, and builds in progress will be lost mid-run. But we built out a custom auto-scaling solution, which runs on top of our managed instance group, which looks at the GitHub queue length and also the percentage of runners occupied, which gives us a good enough signal to accurately predict how many runners can be reclaimed and how many runners need to be brought up. Ensures fair utilization, and we can guarantee that no builds will ever be orphaned. So if a build is running, we will never reclaim that machine. So the impact was obviously 0 stranded builds. So this one was fairly interesting because on our GitHub runner pool, we needed runners to come up quick when there is CI spikes. And this was a problem which we had dealt with earlier when we were running static scale runners. It used to take 8 minutes for a runner to join the pool. Those 8 minutes were broken down into doing a full git clone of our large repo, which used to take a couple of minutes, and then running a full Bazel build because we wanted the machine to be warm enough for the subsequent builds to come up. We quickly realized that we could reuse the state of a runner which is already a part of the pool and make it available for the subsequent runners which join the system. So we added a disk cloning mechanism where a new runner boots from the state of a previous machine and uses the pre-warmed disks. This helps preserve the repo cache, which is notoriously slow to download if your repo has grown to a large enough scale, and also manages to persist the artifacts which have been generated by the previous builds, which essentially means every build can now benefit from a repo cache which is already seeded and from artifacts which are already available on disk. This maintains, so we have to maintain freshness. If we don't, then the Git pulls can go stale, artifacts can go stale, and you would not really see the benefits which are needed at that point. So to ensure that, we only select runners which have run more than one build and have built more than 50% of the build graph, which means majority of the artifacts will still be available on the disk. And also we rotate these periodically so that the older disks are reclaimed and newer disks are created on the fly. We do this around 100 to 200 times a day, and we ensure that our CI pool is always fresh. So this solved our cold start problem and dropped down the cold start to less than 60 seconds at a P95 scale. On average, we see this to be around 30 to 35 seconds. So that directly corresponds to the queue time which a CI build will eventually see. This also had the additional impact of improving our cache hit rates because local disk cache is already seeded with the artifacts of previous builds, so we did see a 30% improvement in our cache hit rates. Okay, so the last one, I think this was touched upon earlier as well, is exec properties. If you're running Bzlmod and you have multiple size classes, you already need to start tagging artifacts correctly because ISCC is not always correct. And this we realized pretty much soon enough as we started rolling out Bzlmod across our build graph. We would see TypeScript Webpack actions getting scheduled on small runner classes and never finishing. So this introduced artificial latency into our systems, and which we had to deal with by manually tagging artifacts which are large enough There is already work ongoing to determine these more accurately and, and have that not be manual going forward. But the solution essentially helped us gain optimal placement of actions on the appropriate runner classes. So a combination of these 4 strategies is essentially what helped us make CI spot safe and guarantee the reliability and availability which reserved compute comes with. But yeah, running on Spot isn't always really free, and people who have done that would definitely appreciate it. Spot capacity isn't guaranteed. We started off with a fairly naive setup where we spun up a cluster, which in a single zone, US Central 1A, and we eventually ran into the dreaded no spot capacity. 12 a.m. pings that CI builds have crawled, nothing is happening. We took a quick fix, at least for now, given that it's only been 3 months once we have started rolling this out. We moved to a regional cluster. I think we'll have to explore more on how we improve the system reliability further, but regional clusters work for us and provide better availability of resources. Next one, preemption storms are a reality. The cloud provider can randomly decide to take down 30% of the node pool, and there's nothing you can do about it. But Bazel has a pretty nifty flag, remote retries, stick a high enough number, forget about it, helps save a lot of pain to deal with this. And thank you whoever added that. Okay, so in summation, from chaos to control, as you would already have seen, vertically scaling static runners, queue spikes, all of this was a lot of chaos in the system. With a 2% team dealing with this, it was projected to hit $1 million. But moving to intent-based auto scaling and relying on Spot instances helps shave off the build, helps shave off the cost, and also made it more predictive and adaptable. So that's all from me. This is us. Come meet us during the conference if you want to dig deeper. Thank you.
Thanks, Rahul. Next up is George. What to remote expect when you're executing?
Very nice. There's a heck of a tongue twister there. Just wait for my slides. There we go. Just like the slide says, I'm George Genscher. I've been doing some Bazeling for the last decade or so. Hopefully I'm going to be able to arm you with a little bit of a presentation today that's going to give you some choices and some challenge for the transcription engine if I can manage to talk fast enough to fit it all in. The goal here is to explain what you should expect, what you could expect, and what is most likely to occur whenever you hit a wall associated with remote execution. So why do we remote execute at all? We remote execute because building everything is slow, even with Bazel. But what that means is that being able to build everything on any machine in any context you want, on this laptop, on that TV display, on the smallest PIC-24 that you can imagine, making that available to all of your engineers at the same time requires money, or at least a lot of money. We're dealing with money here today. If you're confused about whether or not we're actually saving money as a result of remote execution, that's the goal. We want to reduce the costs associated with these things by running on shared resources, because giving everyone every single piece of infrastructure on their desk scales to the tune of the end developers. I don't have that much money to give my developers. As a matter of fact, I don't have any money at all. I just write random open source projects. But the point is that we want to centralize that. We want to spend the money where we can make the most difference, and we want to benefit the most people at the same time. We want to also further reduce the cost of what they're building by not building the same thing over and over again. It's been hammered home. I realize this is a remote execution conference, give or take, in terms of the number of presentations that we've done today. So I've got the graph and the highlight for the flow of exactly how remote execution happens from the original document that we used years and years ago to write out the original open source implementation. With remote execution, we end up with efficiency or correctness, choose to. This is not as common a presentation of Bazel's motto, the fast and correct, choose to, as many people would be able to recognize today. But the point is that time waiting for your build, time waiting for the results, time waiting for any answers associated with how your build process is going is money spent. Debugging the incorrectness associated with your build is more money spent. And what you should expect as a consequence of trying to reach into remote execution, reach into remote caching, is pain. I'll be the first to say that. It's painful. It's a painful experience, just like Bzlmod, just like rules OCI, just like all the other deprecation that we deal with on a day-to-day basis. This is going to be pain. But what is cool about pain is that pain is usually in most cases, necessary from the perspective that it is weakness leaving the build. The ratcheted improvement that you make on a regular basis to alleviate the pain that you deal with is the improvement that you want to see associated with your build, and you will see it every day, and you will see it immediately and faster with remote execution, right? We make smaller changes in smaller places, and we pull the lever back, and we pull our situation tighter, and we get more bang for our buck and more build for our money. The pain that we experience, though, is relative to a pretty succinct function. It's relative to a function of the remote execution limitations, what that system will provide you, but with some of the choices that you've offered into the build. And we'll get to the choices in a minute for what that means. Correctness on the side of the two choices of effectiveness and, efficiency and correctness. Correctness is sort of the easy side of this. The motivation is that developers' machines are swamps. Every one of them has a libz upgrade that they did 10 years ago, and they have no idea why. Nothing associated with this is perfect, but any mechanism that you do, for the most part, solves enough. You will find areas in which your remote execution machine heating up in the data center causes some problem associated with the ability to reproducibly recreate your build, but these situations can be alleviated. A lot of systems work around it and push past it to try and create reproducible environments. So of our efficiency goals, we want to perform an action once per n developers over t. That's the remote execution formula. We only want, for some time horizon of what we want to cache, we only want to do that thing once for all of the n developers that we have, so we reduce that n out of the equation. We get very efficient builds in terms of what we represent. The large, clean central machines that can execute more actions than the clients is also a benefit. If I have a cluster with 10,000 cores, I can probably execute things, or maybe ideally execute things, with more cores, more concurrency than an individual client build with 16 or 25 cores. It's immediately going to date this presentation because next year we're going to have 10,000 cores sitting in front of us. Systemic problems are also more easily solved with money whenever we deal with this. That means that you can hopefully throw money at the problem and fix it. Money is a lot cheaper or a lot less time consuming than 6 interns to solve the problem. And specifically, we can design with a time horizon of t with a single vertical associated with what we're doing. The challenges that go into this are that the client behavior can make the individual build slower. That means that anything that you do associated with your build can cost you time or can result in a bottleneck that you can't scale past whatever client you're dealing with. Bazel, Bach, Pants, Top, Make, I don't care. The point is that every time you push your client, it has to be able to keep up with the level of concurrency that you're interested in. Resource competitiveness, also a factor when the remote system comes into play. If you manage to actually deal with a resource or consume a resource that you don't want, consume a resource that is under contention, you will experience some pain associated with how you're executing. And as has been highlighted recently, non-determinism is a significant cause of this, and hopefully we'll be able to get into just 1 or 2 examples of that given the time. Consider, just as a thought experiment, consider all of the possible universe of build as your space. If we then try to divide it by the number of choices that we've made, we've chosen Bazel immediately. That cuts off a significant amount of the build. We've chosen C++ as our language of choice. We've chosen to do some sort of compliance standard acceptance. We've chosen to do Perl or Python. Well, nobody uses Perl, sorry. We've chosen to use Python as an integration for a set of tools associated with us. And very quickly what you find is that the scope of where your problems lie, or rather the amount of work that you have to do, differs from the rest of the universe of people doing work alongside you, meaning you're going to have a tougher time aligning, associating. We can see that here. Oh, I run on AFS. Oh, I run on XFS. Oh, I run on build farm. I run on build barn. I run on everything else. Do we have unique alignments for all of these things? No, not necessarily. But the point is that this creates the unique environment where when you encounter a problem, you are much more likely to have trouble finding others to review, agree, associate with, and the integrations for this system become extremely custom. The likelihood that someone is doing the exact same build scenario, you are all very, very unique snowflakes is what I'm trying to get across here. The builds that you do are probably never going to look quite the same, and yet we're trying to give you tools associated with remote execution in general where you're all going to be able to use the same API and call it with the same build constructs. Is that always going to work all of the time? No. So what you should expect on the other side is that the remote system, whose job is an incredible management of the number of individual clients that you're dealing with, whether you're dealing with a prem installation with a single company with 10 engineers, or you're dealing with a multi-tenant, multi-instance, multi-regional setup, these things are going to impose limits on you because that is how they are going to continue functioning. They are going to limit your CPU, your RAM, your I/O, and discovering that they don't limit something can be extremely painful. If they don't happen to limit the number of inodes on your system, or the fact that the machine can't really understand 50,000 shared memory segments, it doesn't matter. Like, the ability for your programs doing arbitrary code execution in their systems to affect you, you're going to hope that there's a limit. I had a CS professor in college who just said, you need to be thankful every time you get that seg fault, because if you didn't get that seg fault, there would have been much more significant dire consequences associated with what you're doing. These are implemented per remote execution implementation, so your mileage may vary. Last piece on the non-determinism, and I'm pretty close to time. The environment variables and timestamps examples are great. They're emblematic, and they're very clear in terms of the connection to what you're doing. What gets a lot more complicated is things that traverse the graph, things that follow down through other actions, and especially things where a junior engineer has written in Python their code generator to pump out YAML that something else needs to consume, and it ending up out of order, and you get 500 permutations inside of the build, and your code cannot possibly be deterministic, and you get major cache bifurcation. The short answer is, I don't mean to scare you, but these goals are achievable, but you've got to understand and expect that you are going to hit the wall repeatedly. The likelihood that the changes that you're going to make don't make your build better is very low. This is going to improve your build. This is going to improve your experience on the long haul and make your build a lot more scalable, a lot more adaptable. If you want to switch your remote execution system under the hood, it's very likely that tuning to any number of individual systems, whether it's a vendor system or a prem system, or you wrote it yourself and hosted it in a cloud system, these things are all very likely to improve the capabilities of your build, and the tools that are available for this are extensive. And then my final plug is for the project that I happen to have worked on, Build Farm, the Java open source implementation since 2017. We have a whole highlighted set of tools here just associated with observing your builds and observing your actions and the things that you're putting into the build. More than happy to talk about everybody else, and yeah, go make your builds better in remote executing.
Thanks, George. Last lightning talk, Florian, on IDE support and developer tooling for mono repositories.
All right. So I'm going to talk about state of the art for solutions for IDE support. My name is Florian Berchtold. I'm principal software engineer at Zipline, a logistics company which has just achieved 120 million miles flown in Africa. We're one of the largest commercial drone operators in the world. And we have a small monorepo. We actually call it big monorepo, but you guys, from our perspective, it's a big monorepo. So what do we get with Bazel? We get hermeticity, we get fast builds, we get caching, remote caching, everything is amazing. If we implement everything that we heard today, CI is fast and whatnot. But what do developers do on their machines? They don't have access to those hermetic build tools. They don't have access to all the integration. So what we're missing is the tools, the tool chains, the utilities. They're not straight out of the box available on your developers' machines. Developers don't like to run Bazel, run at AWS, what was it again, the repo, colon, forgot about it. They want to type AWS and do their stuff, right? And also IDEs rely on the tools being on the path. We're going to talk about one way, an amazing way to do this. And once we have that, we still have the IDE support that is not great because IDEs need language servers. IDEs, Bazel supports, I don't know, dozens of languages, and it's often hard to integrate them with our IDEs. And projects such as the build server protocol are in progress, but not fully ready yet. So let's tackle the first problem, the tool support through Bazel itself. There's an amazing project from, he should show up here, Fabian, of course. Thanks, kudos to him. The BazelEnv. So what is BazelEnv doing? It utilizes a, I don't know, 20, 30-year-old tool, which most of you might know, direnv, which will automatically source a .nvrc file once you change the directory into a certain folder. And it's really easy to integrate, and what it does, it will create path entries for all of your tools, for all the hermetic tools that you downloaded. It will make them available for your developers to run through the well-known aliases like Python, AWS, Cargo. And the only thing that your developers need to do is run Bazel run tools BazelEnv, and they get all of the support. How does it look like? The way it's being configured looks like this. This is just a very basic template. You have a few tool chains that you have specified in your module.bazel file. In our case, JQ, Python, and then you have other tools such as Cargo, which is utilizing a wrapper and needs to be compiled, for example. We have Rust format, SHA-SUM, like this is just an example. And then we pipe in multi-tools, which is just the straight out of the box set of tools that come with BazelEnv. So now we have all the tools on the path, right? So your developers will not face issues like, oh my gosh, I'm using Rust C 190 and the CI is failing. Oh, it's using 185 or whatever. So your local development for those use cases where developers need to rely on something outside of Bazel, and then Rust in our case is such a good example because some profiling are not supported by rules Rust yet. These problems will be gone. Developers will not see a huge difference for them once they ran it once. They change in the directory and they have all those aliases available. But the IDE is not supported yet. So how do we get IDE support? Bazel supports the IDEs through Bazel. So let's do that. We chose dev containers. I don't know, many of you might use VS Code / Cursor, all the other derivations of it. And it can help you with automating a lot of this. You start a dev container, you have it automatically set up your BazelEnv, what we had before, and then you install the IDE extensions. Bazel can also support you with StarPLS, a language server for Starlark, and it's out of the box already part of BazelEnv. And there's also a Bazel build VS Code Bazel integration, which will then help VS Code, for example, to find the StarPLS server. C++, how do we do it for C++? We have the compile commands extractor to get your compile commands JSON file, which can then be consumed by most IDEs coming back from CMake. We have ClangD, the daemon to give you language support for C++. and of course the Visual Studio extension. This works okay-ish for most of your smaller repositories, but try create compile commands config.json for a monorepo. And for this example, there's a Bazel compile commands extractor, which can also build it for specific targets or folders. So what this means is that your IDE can now help you by you navigating to files, figure out where is your developer focus right now, and give you that specific scope / context as a C++ completion, like auto completion. And this is kind of the generic recipe how we approach it. You look for a given language. You have to figure out the tool for the language support. Once you have that, could be, for example, ClangD or something else. If you're lucky, there might be an optional language server available. Put it into the Bazel env. You have it on the path. Done. Find an IDE extension that supports the language server or the language out of the box. Python is a good example where you don't really need a huge language server, and you have that interface between IDE and language solved. And for large code bases, try to find a way how to reduce scope, because you can't, I know the big monorepos can't even analyze the whole code base at one given time. Don't even ask your IDE to give me the index for my whole code base. And that's really it. I know it's a quick one, but it's also the last one for lunch, so I hope you're not too bad on me. We have a few examples here. Markus, my colleague, he worked a lot on this. And yeah, quick gig. We're looking for DevOps engineers. Thank you.
Thanks, Florian. Next is lunch. Lunch is next door. Next main stage talk is then at 1:30 here, but there's also a BOF session on IDEs downstairs.
All right. So I hope you all had a good lunch break, and now we continue with Andrew Hewitson from Spotify. They recently completed a migration from CMake to Bazel. So a warm round of applause, and yeah, take it away.
Hi. Yep, that all works. Cool. So, hi, I'm Andrew. I've been migrating a bunch of stuff from CMake to Bazel, as he just lovely said. And this is kind of a continuation of a talk that was given last year from my colleagues Luca and Gabriel, as they were talking about migrating the Android client over to Bazel from Gradle. So we're going to go over a little bit of the technical aspects of how we actually performed the migration, and then talk a little bit about the platform challenges that we had as well. Hopefully there'll be some lessons and takeaways throughout for any of you who are also looking to do some form of a CMake to Windows Bazel migration. And yes, Windows will be involved in the platforms challenges, oddly. So a little bit of context, a little bit lay of the land. We've got the Android and the iOS clients. They're currently already in Bazel by the time that we kind of start this migration in 2023. All of these clients rely on some kind of shared functionality that's written in C++ in a different repo that's also constructed with CMake. So we kind of can't remove CMake just from the desktop clients. We kind of have to go through everything. And so these desktop clients is just C++ with a whole bunch of TypeScript on top, but we're focusing on the C++. And we've got a number of different platforms to consider for desktop, right? We've got Windows, we've got Mac OS, and we've got Linux. We've got a bunch of architectures like x86, 64, ARM64, technically x86 as well at one point, but and then we've also got to think about DARs and like different deliveries that we need to make to like Epic Game Store, Windows Store, Snap, Debian, and all sorts. In terms of size, we've got like 4,200 different targets, give or take a few for like different platforms that need maybe a few extra helpers or a few less. And just about 2,800 of those come directly from this core repository. So it's a lot happening down in that one repository. We pull that in via a submodule, which will become important in a little bit for a problem. So you might be asking why? Why migrate over to Bazel? We've got a build system that's been working for a number of years, pushing out desktop clients pretty regularly. But really, as we're scaling up to the point where we're having hundreds of PRs, hundreds of builds, we really want to be able to cache a lot of the actions between C++. And CMake doesn't really have a native way of doing that. And there are things like Ccache and SCcache, but SCcache we found, I think, to be a little bit fiddly with like sharing across network, and Ccache is just local to that agent. So even though things could be, for example, rebuilt, it could be built once, it has to propagate through all the agents. We've also got tons of different languages, which is perfect for Bazel, right? It's just one place to run all of our Java, Kotlin, Objective-C, protobuf, generated code, all sorts. So that also makes it a perfect fit. And then finally, we do want to bring it into a monorepo. We want to be able to have our users just type one thing and get an iOS client or an Android client out, right? So good reasons to use Bazel. And then in terms of time, I like to look back and see like how do these things start, because they generally, these sorts of migrations don't go very fast. So I looked back and found that there was a commit in this core repository that went back to 2016, just obviously about a year after Bazel actually was released for the first time. So people were already thinking back already in 2016 about how to do this. And I think it was about 2020, 2021, we actually went more full steam ahead across all of our clients. 2023, as I mentioned, end of that, like October, we actually started to migrate things from the desktop side. And then, as you can see at the bottom there, May of this year is when we actually managed to finally remove CMake. So all in all, about 9 years, which is just a little bit of time. And of course, over this time, we've got to have some goals for this gigantic project, right? So we've got to be incremental. We have to make sure that when we're moving from CMake to Bazel, we're doing it in a slow way, because we sadly don't have the ability to just say, stop development for like 8 months and we'll change you over to Bazel. That's not going to happen. We also want this to be automated, because we really don't want to be messing around with parity between 2 different build systems, right, and maintaining those things. So they have to be done automatically if we can. And finally, CMake has to be the source of truth. It has to be, we have to keep up with CMake developments, new versions over this 9-year period. So we really just have to make sure that's the only place that we're touching. So getting into the weeds a little bit, we've got an example here of a pretty straightforward library in CMake, right? We've got some sources, they compose a music library, and that music library has a dependency on some MP3 playback library somewhere else in the CMake graph. And at Spotify, we kind of abstracted this away, so our users don't touch those more base CMake functions. So we end up having this cadre of functions for like spadd library, spadd sources. So this is basically the same file, just now done in that sort of way of abstracting things out using CMake functions. And this lets us have a hell of a lot of like control, and we can start doing validation checking. So things like if you can specify a flag on a particular target, we can say, no, that's a deprecated flag. We don't want you to do that because that might impact our build, or we know it's bad. We can also have things like options that set up debug defines for you, or things like that. And then, interestingly, we can even do like validating dependencies and kind of emulating, even in the CMake side when we were starting out, emulating a little bit of Bazel's visibility mechanics by saying, like, you can't see that target. You're not allowed. It churns a lot. You're not allowed to see it. And because this is applied to basically all of the targets in CMake that we actually care about at Spotify, this makes it the absolutely perfect place to start like writing out all of this information to some other representation. So we added a little function, sp export Bazel library, that really, it just takes advantage of CMake's very permissive configuration step, where you can mutate files, you can mutate the source tree if you want to, you can add templates, you can arbitrarily run processes, and we can just say, like, here's an intermediary plain text file. Just start writing out all the content, all of this context, where we are in CMake, its name, its sources, its dependencies, anything extra that we really want to know about, right? And from that, we get this nice, very simple key value pair system. We could have gone with a more like structured JSON, YAML, but we found plain text to be pretty nice, pretty quick to kind of iterate on as well. And now that we have that to disk, we can again take advantage of the export process, the execute process in CMake to just run this medium-sized Python file that takes that plain text file, ingests it, creates an in-memory representation, does a bunch of transformations, and then writes all of the Bazel files for us. So this isn't using Gazelle or anything like that. And the transformations that this really has to do are things like obviously taking the CMake names, which have to be unique, and then mapping those to exactly where those build files are now on disk. As well as doing things like zlib might be something that we have as a submodule in our repository that we recurse into with CMake, but we don't necessarily want to have that represented in our plain text format, right? Because we maybe want to have a HTTP archive or a Git repo that represents this. We need to map that as well. And then finally, doing something like taking the shared library and saying, right, well, that's the macro that we're going to use when we actually want to compile these things. And so that really just covers the simpler side of taking these like CMake files and translating them into very nice, concise build files that we want to have. But that's really only half the battle, because then we obviously need to have these actual, we need to have the actual infrastructure to build those targets. And I would say luckily, but there's a lot of work from the community that is very wonderful. And the tools and the rule sets that were available got us up running very, very quickly, I would say. We still have some thin wrappers over the CC libraries, for example. But most of the time it's just like a few tags, a few extra little bits, and you're fine, right? And then the vendor dependencies translated very, very well. So instead of having curl in the middle of a configuration step, execute, grab a HTTP archive, expand it out, recurse into that directory, we can just have HTTP archive instead. And then all of our submodules in Git can just be removed and replaced with Git repositories. So that's very, very nice. We still obviously do need some manual build files for these HTTP archives and Git repositories, but those were few and far between, I would say. And obviously, there are some issues. It wasn't all just rainbows. We found that some CMake concepts were starting to permeate over to Bazel, which is understandable considering we are going from a very CMake-orientated build system to Bazel, obviously. So the concepts like release, which don't live in Bazel, were starting to permeate like the names of configs and things like that. So we squashed those pretty as soon as we could. We also found that we had a good couple of build files that were a little bit more of the esoteric variety, where things that either didn't fit into our SP prefixed functions, or they just needed a little bit more handcrafting on exactly how we're going to do this in a nice Bazel way, because they didn't map nicely. Maybe they had some kind of non-determinism in there because they were doing a specific action in a configuration step of CMake that we couldn't replicate in Bazel because Bazel would just not let you do that. And then finally, the way that we decided to go with our incremental approach meant that we had a lot of duplication of our builds. Basically, all of our CMake builds ended up having some analogous Bazel representation. We perhaps could have gone with a slower approach of removing a CMake build and then replacing with a Bazel one. But I think we really wanted that level of validation and like confirmation that everything was always working no matter what. And one big takeaway is that you have to configure everything in the CMake graph. You can no longer, oftentimes we optimize the configuration step when we have large CMake projects by perhaps saying, I'm on Linux, I don't really want an iOS helper, so I'm not going to add that target, I'm not going to visit a Linux directory because I'm on Windows. And when we're using CMake as this source of truth and trying to extract out the whole graph, we just can't be can't have partial graphs anymore. So we had to stay away from those sorts of mechanisms. And things like the top layer here about adding specific sources to our targets conditionally, that also had to be extracted and moved out so that we effectively always add those sources. And for this example, we were using preprocessor macros to basically blank out the entirety of the CMake file, the CPP file. But this will obviously have a massive impact on your CMake configuration times when you do it, because you're now visiting everything. And also it's good to know that because of all of your build files in Bazel are dependent on this particular part of the configuration step, you are going to have a 4 to 5 minute wait time for every Bazel process to begin, which is not ideal, but it felt very good when we finally removed the CMake section and saw all the graphs just shunt down by 5 minutes. It was a nice feeling. So the outcomes from this sort of a migration, I would say that thanks to like a lot of the automation that we had and the work that people had been doing for the years before we started looking at the desktop and migration, we managed to get things going very, very quickly. The macOS client came first. Basically, I think it was a month afterwards. We were listening to music from that. And then a month after that, so Christmas time, we managed to get the first Windows version as well running and playing music. So it was a very, very quick affair, which was lovely. But obviously, just getting executables isn't the entire thing. There was a lot of validation that went in. We needed to effectively look at what we were doing in CMake, what were the rules getting us to do in Bazel, what were the differences? Why, for example, macOS had like binary p-lists, I believe, for their rules Mac, but we were doing plain text p-lists. So it was just validation of those little things of, is this okay? Do we need to make some changes? But then around, I think it was autumn of 2024, we actually started rolling out Windows builds and macOS builds that were built with Bazel, which was amazing that we managed to get this done so quickly with a lot of validation and a lot of packaging. But yeah, migration completed, which is very, very good. Woo. So let's talk about platforms and some of the issues that we encountered. Mac OS was the easiest to running, as I said. A lot of the time it was more down to getting the rules or figuring out what the rule sets wanted us to do. They were far less permissive. They were relying more on Apple guidelines, whereas perhaps the store didn't particularly care about some aspect of the guidelines. I think there was one example of versions, the way that we were applying versions in CMake. Was different to the way that the Bazel rule set enforced. So we needed to make sure that those things were in check, but ultimately it's very, very quick, very, very easy. Linux did have one oddity I remember, which was that we needed, in CMake you can often just call this pkg config and then ask the Linux system where this particular library is, what its linker flags that it needs and things like that. We replicated that with repository rules, and it felt wrong because obviously you're asking in a repository rule, like, where is this thing? And I'm going to then symlink it into the Bazel ecosystem. But it did work, and we ummed and ahed about it a lot. We thought about it, but because we're using Docker to abstract away a lot of the bare metal, the base CI agents and people's machines, we do kind of have a level of hermeticity that's okay, right? We've got this Docker container that changes very rarely, so these things are always going to exist in the same sort of way for all of these Bazel processes, which was nice. But Windows. So we found that there were, when we started getting further and further into Windows, and we started to look at, okay, we've got most of the stuff working, we've got an executable, right, let's have a look at the build speeds, are they comparable? And we found no, they were oddly not. We use a lot of Python to do a lot of our code generation, so each one of these proto-compiles effectively resolves into a Python execution for a plugin. That we want to run. And we had 427 of these, plus maybe an extra 100 of different Python things running. And I worked it out. If we have 24 executors, these 427 things, each wonderfully, each one gets equally shared amongst all those executors. It's about 10 minutes of build time, just waiting for these proto-compiles to complete. And what we found was there was one flag, build Python zip, which defaults to on Windows and off on all other platforms. Lucky when your problems could be solved by one single flag. But what we think is that these executable zips, they are being unpacked on every single one of these executions, or every single action, and then the content of that is being thrown away, and you're redoing the zipping all over again. But so, luckily, because it's a straightforward flag, we can turn it off, and we got down to 1 second, which was much more in line with our Mac OS and Linux setups that we were having. But sad, and also that was also a good one for graph suddenly going very down from one single change, so it was very, very nice. But you'll notice that we've enabled run files there, and that is a bit of a problem, because Windows still sometimes encounters max path problems. For anyone who is unaware, and I'm envious that you aren't aware, and I'm sorry to break that, Windows does have a kind of 260 character limit for paths. That's not super straightforward. There have been lots of patches, lots of changes to it, and we've got long path support now in like Windows 10 and 11. So it isn't as straightforward as that. But we did hit 260 characters and more regularly during this migration. And it comes down to 3 kind of major factors. We have a very structured file system at Spotify. We want things to be like, here's a system, it's composed of entities like APIs and implementations, and those are reflected in the file system as well. But what we found is that oftentimes the names of these parts of directories can get repeated. So this is the length is real, but I have changed the words. But supplementary sessions, you get supplementary again because people like to alliterate or repeat these words. Secondly, because we're running from CMake to Bazel, as I said, all of the target names in CMake have to be unique. So you can't have a really nice short API, impl. Objective-C bindings. You have to be very, very unique. And so people oftentimes, the simplest way is to take the entity name, and that's now the target name. So now we have quite a lot of words repeated. And then finally, the major issue, another factor here is Docker. We do use it at the moment to kind of abstract away the agent, similar to Linux, so that we don't have to care about like the Visual Studio install, where it is, keeping it up to date, badgering the people that run the CI to like update those things and deal with conflicts. If people, for example, still need particular older versions of Visual Studio, we're not the only people using these agents, right? But what we found was that 8.3 name support couldn't be enabled on this container. And for those who aren't aware, 8.3 name support is basically where Windows can take this sort of a long part of a path, shorten it down using this tilde syntax. And then when you use that, Windows will be able to figure out, you meant supplementary sessions. We were just not able to enable this on containers. We tried in the Docker file, we tried while it was running, we tried prepending the command that we were going to run to be able to do this, and it just didn't work. And because of that, we ended up with having our exec root with the system and the entity name, and then the target, and then the system, and then the entity name, and then the target. And that's about 284 characters, which isn't even the longest that we've seen. We were having 300, 310, so yeah. And oftentimes you won't get a nice error that Windows says, this path is too long. It will go, I can't find the file for you. And then you have to rip your hair out deciding, is this a Bazel problem and I've written the rule wrong? Or is this just Windows and it doesn't know what it's doing? And just for context, if 8.3 name support was enabled, it would be 150 characters, which is A-OK. And one extra thing that we ran into with this was because desktop is consuming this core repository via submodule, you have to also add the path for that submodule to every single time that you're doing something in the desktop land, which means that while it ran in core and built and was fine, as soon as you got bumped into the desktop environment, for example, it would break because we had an extra 24 characters that were being taken up by this submodule path. But as long as you're staying away from those factors, and you hopefully won't run into it, but if you do, you can kind of start guarding against it in the CMake stage. It's a very well structured, the run files is very well structured, so you can understand if this is a test and uses run files, I can kind of guess how long this path is going to be. And you can guard that in CMake before you even get to the Bazel stage. And you can also just rename targets. We got very creative. It's impressive how short you can make things if you want to. And then finally, this is my thing, like I would say you need to be aware if you have any very, very old tools that use maybe the old C-style array, max path, that's always going to be 260 characters. You're probably not going to have long path support with that no matter what you do. And then of course, follow the best practices on Bazel. They do work. We have, for example, in our Basilisk, in our tools Bazel wrapper, we make sure that the output user route is exactly what's said in the guidelines to be as short as possible. Every character really does count. And yeah, this was a number of the Windows things that we had. We ran into more, oddly, but these are the two ones that came most to mind when writing this presentation. And I'm around if you want to chat about Windows, and I'm sorry that you want to chat about Windows and Bazel, but yeah, cool. Any questions? There's a microphone there.
During the configure bit, you said that you had to avoid kind of conditional, kind of CMake library includes or something like that?
Yep.
Well, how do you handle situations where you have some libraries that will only build on certain like architectures or systems or similar?
You mean like if I had zlib and that only worked on Linux, for example?
Yes, something like that.
I don't believe that's a problem that we ran into, but I think that if we were to run into that sort of a problem, it would depend on how if no one else had, because obviously at the end of this you have to pick which platform is going to be the one that generates the final build files, and perhaps that could be Linux in your example.
Yeah, I mean, an example of where you run into this a bunch maybe is like in sort of UI type stuff. Yeah, where you're going to get like sort of pretty wide differences in terms of how something might work on different operating systems.
Is this, you said, an external dependency, or is it internal to your code base?
It could be both. I mean,
external dependencies, we found that we could rely on like HTTP archive and Git repo and write those things ourselves. We left out the external dependencies from that because I think we would probably have run into that exact problem.
Okay,
right?
yeah, that makes sense. All right, thank you.
Oh, another question.
Thanks for the talk. My question is about unit tests and end-to-end tests. Typically, Bazel is very hermetic, so like if a test needs a resource or something, you need to be explicit, provide it so it can access it during runtime. Anything that you needed to do?
For end-to-end testing, I think our end-to-end testing, when it came to the C++ side of things, I don't remember running into issues with like resources being. Do you mean resources in terms of like CPU and RAM, or do you mean like data files?
Data files.
I can have a look later and get back to you. I'm afraid I don't have an answer right now, but I think that those are probably the level of things where we would be doing like manual build files to manage things.
Hey, I was wondering if you use any open source components that need to have a CMake component remain for other external users, and how you would juggle having Bazel and CMake together, staying synchronous.
That's a great question, because there have been times where I've thought about or wanted to open source some things that we have like internally that's CMake, and then we've converted over to Bazel. Those things, I think, if they're thin enough, if they're small enough, the maintenance cost of maintaining both isn't as heavy as like running the whole CMake graph. So I don't think we've had to open source anything just yet, but I know that I think we got Chromium embedded framework to start adding Bazel, so I can ask those people and see like what they think about like maintaining both, because I believe they still have CMake integration as well, but I could be wrong.
Hi, I had a question about the package config repository rule that you had up briefly. So normally when you run package config, it spits out some linker flags and some C flags for includes and link paths. And you mentioned that you were like symlinking the required files into some repository. Could you talk a little more about how are you picking which files? Like how granular are you with that? Are you just symlinking the entirety of user include and relying on the
No, I think we were pretty, I wrote this and I think I was pretty, what can I get away with? There were time constraints, so it was very much like, what is the minimum set of things that are required to make this build? I believe it was more like headers. I think I might have left out even some linkers. If things weren't relevant, I left them out as much as possible.
I guess what I'm asking is like, let's say you're trying to build Zlib, and so the include paths are like used to include Zlib. Are you just symlinking that entire directory into that repository and generating?
For PKG config?
Yeah.
I'm going to say probably yes. We are probably symlinking that entire directory in order to get things to work. There are other options like vendoring the whole directory and downloading it via HTTP archive. But given, as I said, given Docker, it was like, this is all right.
Okay, and then for the link flags, are you relying on the toolchain, just picking that up from the local paths? You're not like symlinking the actual shared object in or anything?
I think so, yes.
Okay, thanks.
I can double check though if you would like. Cool, I think I'm out of time. I'm being told I'm out of time. So thank you very much for listening. It's been a pleasure.
All right, next up we have Wojciech Mazur from Virtus Lab. And he will talk about different design considerations when writing Gazelle extensions, specifically for Scala and C++, So yeah, please give him a warm round of applause.
Do we have no? Okay, it should work, but it does not. Okay, something works. That's my screen. Oh no. Anybody remembers the shortcut to mirror? Where is that? I can't see anything. Oh, I have the screen right here. Okay, it should work. Okay, hi everyone. My name is Wojciech Mazur. I'm a Scala compiler / tooling engineer working in Virtuous Lab. I take part in multiple open source initiatives to which I'm kindly being paid for, so it's great. So you can find me, for example, in the ngFlows Gazelle CC. I was invited to help with that recently. Also maintain the rules Scala. And Scala is actually my main language, as you can guess from the title. So like we in the Virtuous Lab do help develop Scala 3, and I explicitly also do the experimental Scala native, which is like LLVM-based version of Scala runtime that is not depending on the JVM. Come on. I had a slide in here, and it's gone. Anyway, here I wanted to tell you something about Virtuous Lab. We are like development experience oriented company. We help companies. We have services to help people to, for example, migrate to Bazel, to introduce tools to increase developers' productivity, and any measures that can make your teams, your people more productive and access your goals. So of course you can find us on the booth. And somewhere in my experience in Virtuous Lab, based on some experience in the Bazel and experience in the Scala compiler, I was once tasked to find out if Gazelle for Scala would be feasible, how hard would it be to achieve. And that's how my history or experience with Gazelle started. The one that exists for the Go is an amazing tool. Like you can just, for example, get any dependency from Bzlmod and it just works. It just like automatically can Bazelify your some dependencies that are not yet natively supported by Bazel. And that's what we sometimes wanted to do, to have in some bigger projects, to maintain the sources, to make them up to date and synchronized. And that's what we wanted to do for the C and C++. So today I would like to share with you some experience that I get from that, and also to give you a quick overview how Gazelle works, in a very quick recap. And later we see which problems might you come up or found when you implement your own Gazelle, something that would be dedicated for your own needs, and something that that we already stumbled upon and need to solve. Yeah. So without any further ado, let's begin. So, as you know, Gazelle is a build file generator. It was initially created for Go. It by default supports Go and protobuf, but there are multiple extensions. It's can easily extend it to either different languages, or maybe if you got some setups with like special configurations that, or some layouts that
repeat themselves in the repository, you can automate creating creating a target that will contain them. So all that basically that you need to do is to implement a single interface, which is a language, and it has one very important method called generate rules. And this one should be treated a bit like a pure function that takes some context of your project inside given directory. You get your configuration, you get access to list of available files, directories, maybe outputs from other languages. For example, you can consume outputs from, for example, Gazelle for protobuf, and that way, for example, create a language-specific implementations for these files. And as a result, you need to produce something. This something might be a potential list of rules to generate, which later would be merged with what already exists in your build files. For a single of these, you need to also create a corresponding imports entry. That's completely opaque. It's something that is specific to your language, and that's completely under your control. And these two are the most important. Of course, Gazelle can also remove no longer used targets. So if you detect something that is no longer used or valid, you can just remove it. Of course, for very simple rules like generating file groups, that might be enough. But for languages, of course, we have dependencies. When your sources include some external symbols, external files. So you need some way to be able to access this. So in Gazelle, there's import specs. This is like a short description of language-specific symbol import that can be provided by your rules and can be imported by some other ones. So in the imports function, you basically take some rule that already exists in some build file or was generated by you and try to figure out what is available inside. So for example, for C and C++, this would be list of headers that are put inside. For other languages, that might be, for example, list of public classes and the symbols that might be reachable inside. And later, at some later phase, Gazelle would invoke the resolve function, in which you need to map from your language-specific imports. These two definitions might be confusing. We have imports function and imports as a value. So imports as a value is something that describes on what you depend on and need to somehow resolve it, right? And then you get some access to some built-in index from which you can actually try to search for these dependencies. Of course, you might also need to configure your program. So for that, there's a configuration which is derived by the subdirectories. And all you need to do is to provide your language-specific configuration in the X map in the below. This might change a bit in the upcoming feature. There's the Gazelle 2.0 proposal. If you want, you can take a look what might it look in the next versions. Okay, so C and C++. So when I first heard that there is a need to create a Gazelle for C and C++, it was very strange to me because at first glance, it seems to be very simple, right? You just get files. This can be easily found. You get Bazel query, for example. You can find where given files are defined. It should be really trivial to resolve that. But in practice, not so much. I mean, if your code base follows some good specifications, some good style guides, for example, only use fully qualified paths they include, or only relative ones, relative to the current file, of course, then it still can be easy. But in practice, if you start to use some additional options, compiler options, includes, strip include prefixes, which are documented as available only for third parties, but are still working in normal code, you get to very strange problems, and it might no longer be that easy to figure out about which header actually you're requesting for. there might be multiple fires that might, for example, might actually be correct from just the sources. And we are allowed to only take a look into the sources and only into the configuration. So at that point, it's getting a bit more problematic. So it's challenging because, of course, we can't really tell how to always find the source. They are not very deterministic. And to work around this, we might need to search under different import specs definitions. So the order in which we would traverse can change how these dependencies would be resolved. Another problem, for example, could be non-idiomatic layouts. So for example, you have some project that's being migrated from CMake, and they decided to have include directory for public headers and some completely different named directory only for the actual implementation. So when Gazelle would enter each of these directories, a very single one of these looks completely valid, because you can have header-only libraries, or you can have just sources with headers. It's allowed. It's maybe not easy to read or understand when looking at the code, but it's correct, right? And this has some problems, because, for example, even if you would create rules for each of these, later we'd, of course, try to resolve dependencies in some way. So now, if you would resolve to the target defined in the include directory, would have only the headers, no implementation. Our code would compile, but it would fail to link. So that's not a real win for us, right? We can use embeds, which can change how these targets are resolved. That's a dedicated function to change to which targets we resolve are given rules. But this one is hard to predict, because we again should focus only on the current context. And here we would need to have something bigger, because we don't know the full layout. So what we actually did inside, because by default originally we had two modes for generating rules. We had either the unit mode, in which you were generating a single target per translation unit, so for CC and header per files, or potentially multiple files if there were cyclic dependencies. Directory mode, so single target per directory. But to resolve this kind of issues, so we actually needed to create one additional mode in which we would aggregate multiple sources from multiple directories and combine them into a single directory. And that pattern actually is not only specific to C and C++. It might be actually visible in some different languages. For example, the Gazelle for Scala has a bit similar issue, that potentially you could create easily some cyclic dependencies. So they also have some similar solutions for this problem. Okay, even if you would resolve dependencies, there is another issue. Like we have macro preprocessor, we have platform-specific includes. And of course, we cannot just easily scrap all the include files, like when using regex, and resolve every single one of these to some target, because of course it would fail to build, because you have target compatibility restrictions for some of this. So we need to somehow evaluate these if definitions. So at that point, we cannot longer use a simple heuristics and take anything we want. We actually need to create some maybe IST, parse our sources, spend a bit more time to actually understand what's going on under the hood. We need to create some environment, which would, for example, tell us which macro definitions are defined for a given platform. This is doable. It can be built in, because there's plenty of well-known platform-specific macro definitions. But of course, user can define whatever they want, right? And can create their own definitions. So at that point, we can't really evaluate something like that by just taking a look at the sources. We need some additional feedback. What we did, what worked for us actually, was some kind of contract. So if you don't use any platform-specific dependencies, we assume there's no platform-specific libraries. If you define some platforms, we would try to check if given include needs to be guarded and provided only in the select condition. So you as a user, for example, provide us with some basic information. For example, the label to the constraint that will be used in the select, some architecture and system operating tuple on which we can, for example, later provide you with some well-known values, the defaults, and you can provide us with your custom macros that are well-known and that you control. So you can tell us a bit more how to evaluate your directives. Okay, so even if you would resolve our local dependencies, there's another problem, because there is the completely different world of the external dependencies. So, and in C and C++ has one big problem. They don't have one centralized way of handling external dependencies. You can vendor them as sources. You can probably use rules for NCC, and probably you're doing that typically. You can use Conan. They have like also integration for the Bazel. Maybe dependencies are coming from the toolchain. Maybe you have something that is very specific to your compiler or your environment. So we don't really know where given definitions can be defined in. What's even worse, we don't even have any guidelines that given symbol might be coming from external dependencies. In Go, they actually, when there is actually a perfect language for the tooling, they very single import has information from which external dependency given symbol is imported from. So at that point, you can easily go, for example, to the Go mode or some other places and figure out where it can be defined. So it's trivial. But for the headers, there's like no hints at all. So for the external dependencies, we have another contract. Yeah? So we can provide you with some built-in index that we have created on our own. We scrapped Bazel Center Registry. We took all the CC libraries that were defined. We've checked which headers are available and created some simple mapping between include paths and which given headers can be made available to targets in which they can be resolved. But this one is not that perfect, especially because it's related to some Bazel Central Registry. You have completely different dependencies that we don't know about. So for example, we have some built-in indexers for rules for NCC, which basically runs Bazel query, search for a very single usage of CMake targets, and tries to resolve all the files that are part of its actions, or its inputs. We have something similar for the Bzlmod, for the Conan, so we can create quite accurately some mapping and resolve it. A very similar approach actually is used by Python. They also have a way of indexing dependencies, which can be done later to quickly resolve which external dependencies are provided by what external targets. Yeah, so we are now in the language of the world of the file-based headers. File-based language. So C and C++ was every single import was identified by a file, and files can be easily found using Bazel query. But other languages, basically almost all other languages, are a bit more symbol-oriented. In that case, symbol can be not strictly a class, for example, but maybe a package, which is still a bit symbolic, but it's still like maybe a bit in the middle. So one other example of symbolic languages, of course, is Java. And Java has one very nice feature. It's very strict. So you have a single definition. It needs to be defined at the very top of the file. All the imports also needs to be placed before first definitions. You cannot put them anywhere. There is a strict place for definitions. There is no relative imports, so they are always fully qualified. So the only really unknown things might be these little things hiding under the asterisk, so the wildcards. That's the only unknowns, but in most cases, only based on the package, we can resolve the jar, the target, that defines given dependency. And that's, most cases, it's good enough. And yeah, we have Scala, and most Scala code bases don't look like that. We also follow good conventions, but if you really want, you can make something like that. You can have multiple definitions of packages, or like partial definitions of packages. You can have fully qualified imports or relative imports to something that you have already introduced to your scope. Yeah, it might be hard to read. Yeah, that's true. You have aliases. You have unimports. Some symbols might be unimported because you don't want to use them. And you can put imports anywhere you want. And what is even funnier, something that looks like a package or import from a package, in fact, might not be a package at all. It can be an object, and instead of importing from a static method, you're importing an instant method from one single instance and add it to the scope. In some cases, it's very useful. It gets, for example, it allows you to create some very nice DSLs or APIs, or some ways to create quizzes. So we can, like, for example, try and test your colleagues if they understand what's going on at all on the screen. So there is, in fact, some illusion of packages or symbols, because anything can be a symbol. What you import actually matters, and where you import might completely change the outcomes. Because, for example, instead of depending on a package, you depend on a local value. And if you would try to, for example, now use a symbol regex to parse all these imports and provide some, for example, some context, it would not be very useful, because you would actually need because every placement of an import makes a difference. It adds something to the scope, or it can be based on some other thing that was previously added. So instead, you would need actually to fully analyze your code. So you'd need to use something more powerful. So like a full parser, like, I don't know, maybe Tricitor, maybe Antler, maybe some parser built into language, so that you have even more information and can actually get more control of what's available and can make some decisions based on that. Of course, not everything that looks like a symbol might be reachable. So at that point, you would need to insert some heuristics to not fail eagerly if you cannot find something, because maybe something can be really imported as a package, because that's a value, and you would need the actual information about the type in which that is defined, and that's a completely different domain. Yeah, so that makes it a bit difficult. However, in practice, like I said, most of these code bases are much more sane. We use normal, fully qualified types. We have linters to enforce that developers don't go crazy. But of course, you still need to choose correctness or performance. For example, if you go with packages, you limit your scope. So the different jars, different targets might contain the same packages. It's allowed, but you would have a conflict, right? We wouldn't really know what to choose. If you go with the symbols, so if you would try to index not at the package level, but on the level of a very single method, for example, or the class, then you have much more things to index and to resolve. So this, of course, would be more difficult to do. Of course, in most cases, package granularity, from what I've seen, is good enough. So it's like if it's like a 95% of all the problems, then the remaining stuff you can just solve with some additional resolves. So it's good enough. So for that, how to actually resolve these dependencies? So we can, for instance, use stuff like Maven log file. So it, for example, has a list of all the packages that are defined in the jars that we used. So we can easily check what is available to us and map to exact jars. Of course, but if you want to have a bigger precision, we might do the same stuff that we did for the C and C++. You might need to actually analyze in some way all dependencies. But in that case, we would, for example, try to extract these symbols from bytecode, tasty, which is Scala specific. But of course, all of these operations are costly, so this needs to be needs to be cached, of course. So the times are manageable. Yeah. So tooling friendly versus user friendly. I would say that Scala for me is user friendly, but I like this language. But in general, if we would take a look at all the languages, we have like two accesses. So we have either strict languages that enforce you some layouts, like Java, Go. We have relaxed ones, which basically tell you, okay, do anything you want. You're the master of the ship. You're in the control. I don't care. And in most cases, from my experience, is that being strict actually helps you, even if these rules might be maybe a bit boilerplatey, might take a bit, maybe you might not like them. They are here to help you. So, in short, the more a language freedom language gives you, the harder it's like for the tooling. So, for example, we or my team needs to sometimes spend more time to actually give you correct feedback or some correct inputs from the sources. But of course, you can help us. Of course, you can make your code stricter. You can lint your code. You can, for example, enforce to use always like a fully qualified types. You can give us hints where things are defined. And of course, you can follow simple style guides, the recommended ones. Especially because it's not only helpful for us, but also for the people that are joining your project, because it would be, it might be more friendly to them. And if you're not yet on the Bazel, but are trying to migrate to Bazel, you might think about maybe make it a bit more Bazel friendly. For example, by disallowing cyclic dependencies, which of course are allowed in multiple languages, but are problematic for the Bazel, basically unallowed for the Bazel. So it would make your migration easier. There's, for example, an compiler plugin that does that for the Scala and enforces that there's like no cyclic dependencies between different packages. Yeah, for here, I'm basically out of time. I'm here for one or two questions, but you have something more, you can come to our booth and we can talk about Scala, about Bazel, or whatever you want. Thank you.
Hello? Okay. Thanks for the talk. Quick question about the dependencies. How do you, or did you figure out that some C++ libraries, or NVIDIA does this quite often, they dynamically load libraries? So did you run into the issue with Gazelle CC that you have to figure out the dependencies of a library being dynamically loaded?
No, not really. And I would say that's not really a scope for the Gazelle, in my opinion. Because Gazelle is based on the scope of the sources. If there is something is not present in the sources, we can't really have any context to provide that. But you, as a developer, if you know that something might be needed, you might create some rules, some hints to help us. But I don't think that it would be really manageable to do it. I mean, if there were, for example, some hints from the, let's say, some comments in the code, some like pragmas or whatever, this potentially can be parsed. We can, for example, analyze them and assume, okay, yeah, we might be using this dependency, but no, there's nothing yet built in like that.
Okay. Maybe a follow-up question since nobody is showing up. For tests, developers also sometimes need some data dependencies. Is this also something a developer should specify manually, or is this something you can parse, identify with Gazelle?
Yeah, so we can identify the sources as a sources, sorry, test as a sources. So we know that, for example, something, if you follow some conventions that you, I don't know, like finish your file name with a test, or it's placed in the test directory, we know that it should be produced as a test target, but we don't set the data. Data is something that is not managed by the Gazelle. I don't think it's managed by the Go Gazelle. In theory, it can be done, but again, it might be problematic to get enough context to resolve data, because this one, of course, yeah, it can be part of the code, especially if that's like a literal path or something like that. So we can deduce something, but you know, as soon as you, for example, start to concat to strings, it's almost very hard to figure out what do you actually mean. So we cannot find this.
Right. Thank you.
Yeah.
Thank you for the talk. It was very interesting. I have a question about the generated code. Mm-hmm. So some third-party libraries or even first-party code might generate config.h, just inspecting the environment. You know, maybe something is available, or I don't know, depending on the day, and you know, that needs to be part of the source code that the compiler then includes, and maybe based on that, it will also take different branches. Mm-hmm. Did you encounter any of this? What's your...
Yeah, that's interesting. We have not yet done something like that. But source generators, that's a problem to resolve. To some extent, you can say that it is done, because we can, for example, can depend on the proto libraries that are generated, but it's a bit different stuff. But in theory, if you, for example, have a use case that you need to index some generated stuff, you can, for example, make it a part of the Gazelle, maybe create some addition to that. And for example, assuming that some rule would be generated, providing the sources, we can base some additional dependency extension, which would take that outputs and produce some additional rules to be generated. But that's not, of course, part yet of the main Gazelle CC. Yeah.
Hi, thanks for the talk. I have a Gazelle extension for Scala, and I have a difficulty with computing the dependencies, as you can imagine. But it seems different. Like, I'm not a Scala developer myself, which handicaps me a little bit. But like, when computing transitive dependencies for a Scala file, it seems that the Scala compiler will only open the jar if it like accesses a specific property. It seems either smarter or more evasive than a traditional JVM compiler, that it will selectively. It's very lazy about like which dependencies it needs, and that makes it harder. And I don't know if you have any suggestions for how to get around that. Like,
yeah, like for example, root Scala by default, for example, have this issue that they follow the Java convention. So the transitive dependencies are not propagated, and that's the main issue, right? They're not like headers, which are basically propagating everywhere. The JVM headers dependencies are like basically just direct ones. So the rules Scala is actually resolved in a bit different way, because we have two additional modes of managing the class path, which might not be the perfect ones, because, for example, we take the full transitive closure or the just next level of dependencies, which of course is not that much under the control. However, what you can do actually do, because if you know on what symbol you directly depend on and what need to resolve the remaining stuff, you can create a simple Gazelle extension that would be run as the last one and would take as the input dependencies added for the existing, for example, Java libraries or Scala libraries, and extend this list by its direct dependencies. So in theory, this graph can be extended, and these additional dependencies can be provided. I think that's what you asked for, right?
Yeah, maybe I'll talk to you afterwards too. So
yeah, we can catch at the booth.
Thank you for the talk.
My question revolved, you talked about like formatting and linting and making Scala source files more strict so that you could make it easier on yourself as a tool author. I'm curious, like, what are you using for linting, and have you taken any steps to integrate that with Bazel?
With like linting Scala sources, for example?
Mm-hmm.
Not directly in the Bazel, but of course we have like stuff like ScalaFix and stuff with custom rules. And in practice, in fact, if you want to take it even a step further, creating a compiler, a plugin, is also doable, especially under Scala 3. Because in Scala 3 you have like this built-in support for patches. And you can, for example, if code already compiles, but you just want to enforce the correct linting, which of course might be a bit more complicated than just doing some static analysis, you can potentially just create a patch to, like, for example, some of these imports. You can just rewrite existing tree representing import, create a full dependency, and the compiler would apply it as soon as the compilation passes. That might be one of the solutions. Of course, ScalaFix rules, for example, and some tools, similar tools for the other languages. I'm not that well aware what's available for like Java, Python, or whatever else, but basically every single one has some tool that basically allows to set up some lints. So I would go with these ones, especially because like ScalaFix, for example, is great for LLMs, for working with LLMs. If you, for example, use the Metals, the latest version of Metals, which has like a built-in MCP server, which allows you to just tell, hey, for example, I want you to create a rule which would enforce this and that behavior, and it's very good at creating these rules. And then you have something that is deterministic. You can easily apply it anywhere you want, and I think that's a great example of usage of the LLMs that can be used right now, and to make your code stricter.
Thank you. I have more follow-up questions, but I'll probably talk to you afterwards to not take up the time.
Yeah.
Hello. I had some interesting things sparked by the discussion. So I have made a tool for our code base that actually finds unreferenced headers, like basically like a file-wide dead code linter, actually using similar techniques to your C++ parsing question, where we actually regex parse out the includes and then figure out which files they map to. So I kind of just wanted to share that as another interesting use case if you know that all of your usage is within the confines of Bazel.
Yeah, exactly.
So just wanted to share. Kind of neat application.
Okay, right. No further question from my side. So thank you very much for the talk, and give him another warm round of applause.
Thank you. Oh, also there's a game night today, hosted by Angeflow, JetBrains, and Virtus Lab. So meet us later and let's have fun.
All right, so there's one more announcement I want to make, which is there's an unconference session today, and you can still vote on the topics or propose your own ones. So head over to BazelCon Trip. There's a discussion where you can add your own ideas. And now we have a short break, and we will be back at 2:45. All right. Next up, we have Shahan Yang from Google, who will be talking about Skycache, a new way to store the analysis results remotely. So please give him a warm round of applause.
Hi, thanks for coming to my talk. And yeah, we're going to be talking about Skycache. What is the problem that we're trying to solve? I'm going to make this talk kind of like assuming very little knowledge, right? So I'll be going over some things that you probably, most people in this room may already know. So when you run a Bazel command for the first time, it spins up a server in a cold state on that machine. And then it does a clean, so-called clean or cold build, which parses all the build files and does all the execution. And this is very, very slow, especially for large builds. It can be like more than 10 minutes. This is lost developer time and productivity, and also, at scale, this is a lot of computations being done redundantly, because every single Bazel instance is doing the same computation if they're working on similar targets, and that does happen in our systems. So what is Skycache? Skycache is a cache that pretty much caches all of the analysis and execution state for a Blaze server, and arbitrarily large targets have build times reduced to about 20 seconds. And then it's way less memory usage, because we're not like pulling the entire state of the build graph into memory, but only like the top part of the graph that is needed to just get the results. It's very similar to, in a sense, to like build without the bytes, like only outputting like the top level run files. And we want to make cold builds obsolete. Okay. To understand how Skycache works, I'm going to have to talk a little bit about Skyframe. This is the internal data structure, so the internal framework that Bazel uses that drives all the computations. Skyframe is actually conceptually very simple. It's a bunch of Sky functions with static definitions. They're functions. There's some concurrency, but it's a bit. I'm going to declare that's an implementation detail. And then there are Sky keys. A Sky key is basically a function name plus its parameters. And then Sky functions can call each other recursively. So you can get these really nice build graphs. Sorry, one more point on this slide. Sky keys and Sky values are serializable. We have custom serialization code that works on all execution and analysis values. So here's an example Skyframe graph. You see sort of the usual suspects here. You see action execution near the top of the graph, and then you may see something like a configure target or a package and a file. Configure targets are the sort of the outputs of the analysis phase, and packages are this sort of phase that encapsulates the computation done when when parsing a build file. So Skycache has three main concepts. One is top-down pruning, and one is this invalidation using sort of the sets of file dependencies of every single target. And then there's a lot of work done to make the serialization of this stuff efficient. So top-down pruning is basically, so this is like a very, very abstract Skyframe graph. Basically, when you get a cache hit from Skycache, you don't have to pull anything from underneath, right? Because the top-level Sky function doesn't directly depend on those transitive dependencies. It doesn't need to look at those Sky values. So you can just, when you get a Skycache hit, you just throw away everything underneath it. So in terms of the cost-benefit, this is somewhat interesting. If you were to deserialize the entire analysis phase, I don't think there would be much benefit because that cost of deserializing is not going to be like much better than the cost of computing it locally. So all the savings you see are from that top-down pruning. Instead of loading hundreds of thousands of nodes, maybe you only load thousands of nodes, right, as remote cache hits. Okay, in order to prove that you actually have a cache hit, you have to be able to sort out the values that are considered fresh in the cache versus the ones that are stale. And for that purpose, for every single target that we cache, we store all of its transitive file dependencies in this sort of nested structure. And then we look at the files in the client that are modified. I'm going to put this in terms of Git. Like, let's say you have a commit hash that you're based off of. Then you do a git diff, and you find which files have changed relative to that baseline, and that's a set M. And then F is something that was previously persisted at that commit hash that was stored in Skycache. And if there's any overlap, then you know it's a stale value. And if there's no overlap, you get a cache hit. These dependency sets have this interesting structure. If you're familiar with something called a nested set, which is one of the foundational data structures of Blaze, file dependency sets have a very, very similar structure. There are two concepts. There's a node, and then there's like a source node. So nodes store the dependencies of the analysis targets, and the sources store the dependencies of execution. And we do track them separately, but they form this sort of nested graph where the data is shared. So because T depends on T1, it means if T1 is invalidated, then T is invalidated. So it has this, it transitively, the set of dependencies of T include the transitive dependencies of T1, right? But they can share memory. So it's a bit more efficient. It's much more efficient than storing all of the sets explicitly in a flattened way. Okay, so a naive sort of Java serialization-like approach to this, which was what we did in our early attempts, proved to be very, very bad in terms of the serialized representation. There was like a 10x blow up. So you're suddenly looking at 150 gigabytes to store this build on disk, which seems like a lot. And in particular, the serialization of Starlark functions was very expensive. We're basically trying to serialize the Java representation of the Python code, serialized Java representation of the Python code, which is just a little bit too much indirection, right? So for the first of these problems, you may have been able to guess this, but basically, if you serialize every single Sky value independently of the other Sky values, then you're going to serialize a lot of redundant data because they share data. Like the providers that are passed between Sky values during analysis, they're transitive info providers. So transitive data gets propagated up to up the graph, gets accumulated going up the graph. So what we do here is we have this is actually, I think, rather unique to Bazel serialization and very different from Java serialization. We have this global memoization layer. So when you think about Java serialization, you're serializing an object graph. If you encounter the same value again, then it goes in some memo table and it writes a back reference instead of repeating the object. This also solves cycles, right? But there's no concept of let's serialize value A and then serialize value B, and they share data, right? If you just naively serialize, you'll get 2 copies of the shared data. So we have this sort of explicit API that says, hey, let's declare this as a shared value, and then we'll serialize it once. The code is a little bit complicated because the serialization of all this stuff happens concurrently. So if two values are being serialized at the same time and they share data, then you have to deal with the concurrency. Deserialization with shared values is much more very treacherous relative to serialization, because if you deserialize a value and you may be in a state where, let's say you're trying to deserialize this value concurrently, this shared value concurrently, you may end up in a state where that value is not yet completely deserialized, and you try to insert it into one of its parents. Then upon seeing that incomplete value, it could try to like compute a cache code or something, and then crash. But it ends up being kind of elegant. This ends up being kind of elegantly resolved. There's a shared value graph, right? There's like this inner normal serialization graph, and then there's a shared value graph, and it's a DAG. It's directed and acyclic. And because it's a directed acyclic graph, it's a normal dependency graph, so we can just do a very, very straightforward dependency graph, parallel traversal going upwards. But we wait until all the children are done before propagating the values upstream. What happened? I lost the ability to switch my slides for some reason. Okay. I just spoke to this. There's a little bit more detail here. The object codecs are the implementations of the serialization code. It's like done on a per class basis. And there's two APIs that we use to allow asynchronous serialization. One is like you can declare a builder, and then the builder has to be thread safe. The asynchronous values can be set at any time. And then there's like this there's this field setter version where the object itself is a mutable builder. You can imagine having an object constructed with all nulls using an unsafe API, and then the private fields being written in. That is a thread-safe operation, but that's going to go away in the future because Java is removing the ability to set final fields. Okay, and then the last piece of the puzzle, I alluded to this earlier when I talked about the serialization of Starlark functions or Starlark modules. So imagine you're trying to serialize a Starlark function, which is like this Python code that's been turned into a Java data structure representation. That ends up being very, very expensive. So instead what we do is we allow that to be represented as a sky key pointing to its BZL load key, and plus like its global name. And that ends up being, it's just serializing a key, which is cheap. And then upon deserialization, our serialization machinery is already asynchronous, so we can do a sky function lookup. We can call the sky function to evaluate the BZL locally, and then pull the Starlark function out of the compiled BZL module rather than trying to deserialize it. Based on profiles we've done of builds running, loading BZL values is a relatively cheap operation compared to everything else we do. So this ends up being an effective mechanism. Oops. Okay. So enough with sort of the nitty-gritty of details of how it works. Here's some results from a dog food. So this is real-world data. It's rather limited sample size, but basically it's a small to medium target that we had asked users to try Skycache with. And so the build times went from 46 seconds down to 13 seconds. And you can see like the reduction in the actions executed, targets configured, and packages loaded. These are for the same target, and that's the effect of top-down pruning. This is a representative bounds for a large target. What I mean by lower bounds is that it's very optimistic. It's when all the caches are hot and everything is clean, right? There's no stale values. We see like a 7-minute, 21-second target go down to 17 seconds. There's a little detail here about how much time is spent in Skycache. It's only 5 seconds. And then there were some actions that are just semantically unshareable, and those are uncacheable, and that takes up the remaining 10.5 seconds. And there's 1.5 seconds of initialization code, 1 second of which I don't know how to account for. I should dig into. All right, so the limitations and future work. In terms of the limitations, it uses considerable RAM. So in the amount of, we're putting all this data in like memcache, something like memcached, and because there's a lot of these indirections, these references. Like you recall the nested structure of the file dependencies. There's a lot of references, so there's a lot of RPC hops. So we use something like memcached to avoid adding too much latency to multiple round trips over an RPC connection. And RAM is expensive. That coupled with the fact that users one of our really, really important clients wants to have very, very old versions and a high version cadence. So that means we have to persist thousands and thousands of images per target that they're interested in caching. And currently that's actually infeasible for us with at the size of those targets and how the number of them and cadence. Things that we're looking into, and this is sort of our main limitation and things we're looking into. So we've done an empirical study where we do observe, I think a lot of you may have heard of like social networks and power laws. Basically, there's a small number of nodes that have, that account for an overwhelmingly large amount of the links or edges. Or in this case, this comes down to like 2.5% of targets accounting for 90% of targets actually built across a very, very large set of data. So perhaps we can do some targeting of our cache based on frequency. We'd also like to look at things like dictionary-based compression or moving caches from RAM to disk. And that I think is challenging because we have to come up with a strategy for reducing the indirection. It would probably not be good to have very, very many round trips to disk, which is what Skycache would require today. So I heard that this was a question on a lot of people's minds, like how do we get Skycache to work with Git? It's built on top of Piper right now. I've identified the classes here that are the exact classes. These are all open source classes that you would have to use. There's this long version getter. You'd have to give each git commit hash an index, and then you can use git diff to find the files that have changed. If you recall how the incrementality algorithm compares the set of changed files to the set of dependencies. You can get that out of Git as well. And there's a service that we implemented. There's an interface. It's the Remote Analysis Cache Client. And the class file dependency deserializer is provided. And that takes care of all the marshalling and unmarshalling of the file dependencies. And you'd have to bring your own fingerprint value store. That's just a very simple key value store. I think if I were in the open source world, I would be inclined to try Redis on Flash for that. Yeah. And that brings me to the end of my talk. Are there any questions? Yes. Okay.
Hi, appreciate for the talk. I really love the update. I tried to play around with the current implementation. And yeah, all the class you have listed out, it was suggested by Codex. So it was really handy to try to implement a Git version of it. However, I did run into problem with the protocol currently. is very binary oriented and is very similar to memcached. Both the key and the value are very binary. There's not a lot of thing we can do with it on the server side. So if we want to like extract some data and visualize the sky, for example, if we want to build some sort of visualization for the sky frame based on that data, currently it's not possible. So is there a version in your mind where we can have like something like protobuf and gRPC for serialization instead of these binary?
That's a really, really interesting question. So the question is sort of around how do you create a well-formed key for these sub-objects? Some of the objects have a natural key, like the sky keys. So you could imagine, instead of having a digest of the sky key, have the sky key explicitly represented, but then there's sub-objects inside the sky values, right? So stuff inside the transitive info providers, for example, that are serialized with indirection, for which there is no very natural key, although it is a very interesting question, and it's one that we're thinking about. There's no current implementation. Thank you.
So you mentioned specifically that the likelihood is high that the round trip rate is significant between the client speaking for looking up what are essentially sky keys and the remote analysis cache. Can you give an order of magnitude of, is it, if I said that we had 1 million actions in our build, what is the likelihood that that translates to 1 million-ish sky keys in use, and or is it reduced by anything, or what would need to be effective for a storage protocol where we would be able to get batches of these things in sequence?
Okay, so there's a couple questions in there. Let me ask. Let me just take care of the easy one first. The batching, we do tons and tons of batching. Everything is batched extensively in our low-level communication protocols. The second, the more interesting question, the more elaborate question to get into is the proportionality between the size of the build and the amount of data, the number of round trips. Because of that top-down pruning property, it may be something like OC, right? It may be like constant order. Maybe you only need 10,000 keys, no matter what. Based on your project, right? Because there's going to be a locality, like some people are going to be working in this section of code, and they're going to make changes there, and then you don't really care about stuff outside, all the stuff outside. So this is just like serialization along that boundary. If that makes sense.
Thank you.
Hi, great talk. Super interesting to see progress in this area. So I was wondering, you were showing before where you had the transform. Can you hear me properly?
I can't hear you. Can you step up a little?
Yeah. So great talk. So earlier in the presentation, you showed the graph where you did the transform from the cyclic graph of action keys into the directed acyclic graph.
This.
Yeah, so I was wondering, how do you resolve because that's not like a, I'm going to put this, it's not like a canonical transform or something. When you get a secondary build, how stable is the shared graphs part going to be compared to the first build, etc.?
That ends up being a super interesting question. Because of the semantics of serialization, what you get is value equivalence, but you don't get structural equivalence. This has been this a couple times. It's believed that, we believe that in all the places where the structure matters and you have value equivalence, we can work around it. Like there's a workaround inside the nested set where the nested set may not have the same structure as the one that you actually serialized, like the same reference structure, but it has the same value structure. Like if you iterate over if you flatten the nested set, you get the same values back. But there's like a little hack in there to make sure that it happens even if the structures change.
All right. Thank you.
Welcome.
You mentioned you do top-down pruning, right, for caching. Do you ever get into correctness issues with top-down pruning? Like, I imagine you use top-down pruning for like caching actions, but you could, because of say like non-determinism, then get, potentially into like incorrect builds because of, yeah, I'm curious.
That's a very interesting question. There is this theoretical edge case where you have two non-deterministic builds that wrote the cache of the same target, and you can get a chimera, okay? So you get like this build that built using one non-deterministic value at the bottom. You get this other build that built the same target with a different non-deterministic value at the bottom. And then they'll merge and they'll become something novel, which is not great. Yeah, that is a theoretical possibility. We've been running a system like this for many years. And it hasn't come up even though, even though it's theoretically possible.
Okay, I see. And then I had a second question about, I saw there were like non-cacheable actions in the build, right? I assume you also don't do top-down pruning for them, but or Skycache for them. But what about like the parents of non-cacheable things that could be cacheable? Like, do you still use Skycache for those as well, or is it like anything that depends on non-cacheable is always also, non-cacheable?
I think the correct thing to do would be to not serialize the stuff that is downstream of something non-cacheable. Mm-hmm. I think it works. I'm not 100% sure. The code is correct.
Okay, thank you.
Yeah, sure.
I would imagine that the impacts of like skyframe caching would be disproportionately felt by super large monorepos where like it's impractical to do analysis on the entire like transitive closure. But for more medium-sized repos, has the Bazel team explored like making Starlark run faster, like JIT compiling Starlark or doing things like that, so that like it's so fast to run Starlark that we don't need to cache analysis?
There's probably people in this room that have a better answer to that than me. But
okay.
Yes, there's definitely work being done in that area. Does anybody want to chime in on that one?
Well, I can say the topic has come up every time we benchmark things. The core Starlark execution isn't the bottleneck, it's everything else. It's certainly been on our list, and maybe it looks like a way we'll come back to it.
I hope I'm not opening a can of worms. I know very little about Bazel internals. I'm just curious. Thank you.
Thanks. Okay. Thanks again for coming to my talk. I think that's all the questions.
All right. Next up, we have Andreas Hermann from Tweak talking about Haskell builds and a comparison between Bazel and Bug 2. So give him a warm round of applause.
All right. Thank you, everyone. It's great to be back at BazelCon. So my name is Andreas. I work at Tweak by Modus Create, and today I'll take you through our journey with building Haskell with Bazel and Bug 2 as well now. So to provide a little bit of background here, Tweak was a place where early on we were interested in Haskell and Nix and sort of functional programming and correctness and purity and hermeticity and all these things. So when Bazel was open sourced by Google in 2015, that certainly caught our attention. And at the time, a little bit later, we also had a Haskell project going on that was reasonably complex, had some C code, some code generation, some other complicated pieces, and was generally just hitting a scale where the native build tooling Cabal was running into its limitations. And so we were looking for other alternatives. And of course, Nix was one of the things we considered, but sort of it's more on the package level, a bit too coarse-grained for what we wanted there. So we started looking into Bazel, and that is how Rules Haskell came about. And there is a blog post that you can read more about that from back then. And before I continue the journey, I'll first want to take you a little bit through the very basics of how Haskell builds work. So there's a bit of a Haskell builds 101. So as many languages do, Haskell has a notion of modules, where a source file corresponds to a module. And then these modules can import other modules, which sort of incurs a module dependency. So here you can see an enterprise-ready hello world, where you have a say module and a hello module with a message, and then a main module that imports the say and the hello. And that gives you this module dependency graph. And now in order to compile this, let's start first with the say module. We take the source file. We pass it to the Haskell compiler, the glorious Glasgow Haskell compilation system, if you ever wondered what GHC stands for. And that produces two outputs. One is an object file. It's the same kind of object file you would get out of compiling C code or something like this. And then you have this .hi file, which is called an interface file. And that is sort of like a generated header file, kind of. It contains like signatures, exported symbols, and a bunch of other information. But it's exported, like it's generated by the compiler. If we now walk through the full compilation example, again, we're compiling the say module, and then in parallel, we can also compile the hello module. But the important thing now is that in order to compile the main module, we need to provide those interface files, because the type checker needs to know what symbols were exposed and what types they have and all that kind of stuff. And then we can proceed from there. We also get our outputs from the main module, and then we can link the objects together and finally get our executable. But the important takeaway here is that in order to compile a Haskell project, you need to compile the modules in module dependency order. Otherwise, that's not going to work. All right. So let's talk a little bit about incremental builds. Broadly speaking, if you have a build action dependency graph like this, and you have some change indicated in red here that impacts this action, then what we want is that only those actions that are impacted by that change are invalidated and rebuilt, and the rest stays the same. We don't have to rerun this, right? Incremental builds. And of course, Bazel provides this with clever hashing and caching and all these good things. Now, if we look at the way that Rules Haskell works, in Haskell, we have this notion of packages, where we take a bunch of Haskell modules and we bundle them together into something called a package. And for the library case there, we have a rule in Rules Haskell called Haskell library, following the common Bazel patterns, that has a name and a sources attribute, and in the sources you pass in the source files for all the modules that make up that particular package. And then the rule under the covers uses the Starlark API to generate a build action, forward those module source files, and invoke the Haskell compiler to build them. But the problem that we see with this approach in Bazel is that now we don't get our incrementality at the module level, right? If we invalidate one of those modules by making a change to it, even if it's just a comment or anything, we're going to have to rebuild all the modules in this package. And the reason for this is that we are nowhere are we exposing the module dependency graph to Bazel, but Bazel would need to know the module dependency graph in order to get incremental builds at the module level. And Bazel cannot infer the module dependency graph automatically for us here. And the reason for that is that Bazel's build graph is completely static. So at analysis time, when all the rule implementation functions run, the action graph is written, and you don't get to look at anything generated at that point. And so you cannot infer build actions at that stage. And of course, there are good reasons for this, right? We want our queries to be fast. We don't want, if we run a query for, I don't know, target determination or something like this, to have to build half of, Google's monorepo or something like this. That would be a problem. And of course, we also want things to be explicit. We want an explicit target dependency graph. And so Bazel decided, no, we're not going to do any dynamic dependencies, asterisk. But at least for the purposes of a rule author through the Starlark API, it's completely static. Okay, so we had this issue. We wanted module granular incremental builds, but we didn't get them. So we explored some other alternatives, and one of them was persistent workers. So Bazel has this feature called persistent workers, where you can spin up a compilation server that is then served requests for build actions and then can reply to those with the build results. And the idea behind this is, let's say you have Java C, spinning up a Java compiler needs a JVM and everything. That's a costly operation. You also want the JVM to be hot and all that. So you want a persistent compilation server for those compilation actions. And so Bazel has that concept of persistent workers for that purpose. And we thought, well, this is a persistent thing that could be a place where we could store the necessary information to get the module incremental builds running within a build. So I see, faces. I know. And so we explored this option, but of course the downside is that we'd effectively have to re-implement Bazel's caching, and there is a whole lot of problems with potential introduction of inhermiticities and whatnot. So we discarded that option. It was just way too complicated. So then the next thing we did was to say, well, if Bazel needs the module dependency graph in order to give us module incremental builds, we are going to give Bazel the module dependency graph in the build files. So we introduced a new rule, Haskell module, that compiles a single module. But of course, you have a lot of modules, and these dependency graphs change relatively frequently. And so that's a bit of a hassle. So we introduced a Gazelle extension that then generates these module dependency graphs and exposes them to Bazel. And that works, and you can use this today. And you get your module granular incremental builds as you want them. But there are some downsides to this. So if we then look at our build files, they get a little bit noisy. We end up having a lot of module targets in there. We have to make sure they're kept up to date. So if we use Gazelle, there's always this Gazelle pre-step that we need to run before our builds or when developers make changes. The diffs get very noisy whenever the module dependency graph changes, and that happens more frequently than that the target dependency graph changes. And Haskell also supports the C preprocessor, and that is often used for cross-platform projects to guard imports. And trying to have Gazelle automatically parse CPP logic is not a thing we were going to do. So you always need a little bit of manual fudging to make this work in many cases. So overall, still not ideal. So when Bug 2 was then open sourced by Meta in 2023 and had a form of dynamic dependencies, we were very interested and wrote a blog post about sort of comparing Bug 2 and Bazel that goes into a few more differences than I'm going to cover here today. And then in 2024, we were fortunate enough that we got to work together and still are working together with Mercury, who are also in the audience, on building Haskell with Bug 2 in an efficient way. And so what does that look like in Bug 2? So Bug 2 also uses Starlark as its configuration language. It also has something like build files. And rules are sort of often using very similar or the same nomenclature. So there is also a Haskell library rule. And that has a name attribute and a sources attribute. And we're going to pass all the module source files of that package to the sources attribute. But in this case, we are going to get our module level incremental builds for that target. And the reason for this is that Bug 2 is able to dynamically infer the module dependency graph just from this input in the build file. And the way this works is through dynamic dependencies. So I'll walk through a little bit how this works. I'm going to give a high-level illustration here, but the idea is that on the very left in this picture, we still have our three source module files, say, hello, and main. And then on the very right, we have our main executable that we want to get out. And in between, we have this big box that takes those inputs and produces that output, but we don't know exactly how yet. And then there is this other special input that I've marked in purple here, that runs GHC-M or like equivalent of GCC-M, some way to parse the source files and produce a parsable file that contains the module dependency graph. And we get to pass that into this dynamic action. And then this dynamic action at build tile in the Starlark code can read the output of that action in, parse it, and then use the regular Starlark API to generate new build actions that take this module dependency graph into account. And then at that point, we're sort of dissolving this big box and placing in a module granular build action graph. And from then on, all the regular build rules apply, and if we make an incremental change to our inputs, then we're going to get the incremental build on the module level for our package automatically at that point. And so if you're wondering, this is what this looks like in the Starlark API. So within our rule implementation function, there is a special action called dynamic output new, and presumably at some point in the future, just dynamic output. And you pass that a dynamic actions object, and you create one of those similarly to how you define a rule. There's a global function that you call, and you give it an implementation function and a set of attributes. And then this dynamic action has an implementation function, and in there, these special inputs, these dynamic inputs, you get to parse them or look at them. In this case, there's the read JSON, and also I think it's called read text to look at the raw text if you want to. And then afterwards, you can issue new actions based on the information that you get out of that file. And now earlier I was talking about how Bazel did not do this kind of thing because they wanted to make sure that the queries are fast and the target graph is explicit and static and all that. And so you might wonder, well, where is this leading? Surely Meta also has those concerns. And they do. And the idea here is, though I hear checks of this are sort of in the works, let's say, but the idea is that the inputs to your dynamic action are statically known. And the outputs of your dynamic action that are generated as part of the dynamics action are also statically known and scoped within the target. And you only get to wire those pieces up dynamically. But the scope of inputs and outputs is statically declared. And then what this is there to ensure is that the target dependency graph is static, so that you still get your fast queries and explicit target dependencies and all that good stuff that you want. But at the target level, you also get the ability to dynamically generate fine-grained incremental actions. All right, so we did that, and that worked perfectly. But then there was another piece that we ran into that I want to talk to about a little bit, and that is package boundaries. So Haskell has this notion of packages, and if you want to think of modules as compilation units, then you can sort of think of packages as linking units, if you like. And these packages can depend on each other. So in this case, we have a package 2, and that depends on a package 1. And what that means is that modules that are part of package 2 are allowed to import modules that are part of package 1. But interestingly, it does not mean that every module in package 2 depends on every module in package 1. It only means that modules in package 2 are allowed to import some modules in package 1. So if we look at this sort of at the level of a build action graph for those two packages, where package 1 is blue and package 2 is green in this case, then we see that some of those actions are going to depend on some of those actions in the other package based on those imports, but not all of them. So not every green box here depends on all the blue boxes, right? Now, if we look at this picture and we imagine that the x-axis on this represents time, sort of how we schedule build actions, then we do see a bit of an issue here. And the issue is that we first have to completely build the blue package before we can actually build the green package, even though a bunch of the module compilation actions in the green package could be scheduled far earlier. And this was indeed a problem that we ran into. And the reason for this was that we didn't have a good way of sharing the module granular dependency graph from the blue package with the dynamic action of the green package. I mean, there were some stunts you could pull. You could like serialize it into a file and then parse that file later on, but there was no fast way to do this. But what we really want, if we still imagine the x-axis being time here, we want the green actions to sort of shift left as far as possible based on their dependencies, right? That's what we really want. So the way we were able to achieve this was by adding a feature to bug 2, which is dynamic values, and then the Meta team kindly improved the API. With that, what we get to do is within a dynamic action, you can, similarly to a rule, you can return providers, and then where you invoke that dynamic action, what you get back is kind of a handle onto those, sort of like a future, if you will. And you can stuff that somewhere in some provider, and then in another targets rule that depends on this, you can pass that handle to a dynamic action. as a dynamic value attribute. And then within the dynamic action implementation function, you get to inspect the results of that dynamic value. Because at that point, you are in the scope of that dynamic action that is being executed right now, and this also tells the bug2 that it has to execute that other dynamic action first to have all that stuff available. And then this way, you can pass forward efficient representations of module dependency graphs and things like this through T-sets, which is Bug's equivalent of dep sets. And with that, achieve indeed this kind of build graph. All right. So let's look at a few cases of what this looks like in practice. So one thing we did was for last year's Haskell Implementers workshop, we took an open source Haskell project called Amazonka, which is a library with AWS bindings. And it's a reasonably large Haskell project with some 3.8 million lines of code and 35,000 modules. And building it with the native Haskell build system Cabal on my laptop with 8 cores takes a bit more than an hour. And building it on my laptop with bug2 in a clean build takes 2 hours. So, okay, we'll talk about that a bit later. But the cool thing is that if we use a remote execution cluster with 100 cores, then we can build it in 15 minutes. And as we can see in that graph there, the utilization is also very good thanks to this module granular builds across package boundaries thanks to the dynamic values. With a dip there, I'm not exactly sure what happened there. That wasn't reproducible. I assume just the cluster was busy with something else in that time. We get that. We get the remote execution and the horizontal scaling. And then also incremental builds work very well. So I tried some different incremental workflows and comparing some of them, like one of them with Cabal took 7.7 seconds and with bug2 1.4 seconds. So we get very nice incremental builds. And of course, we also get to benefit from remote caching. And then, of course, the use case that the project was all about at Mercury is also a large Haskell code base, some 1.8 million lines, 18,000 modules, and growing. And Cabal builds on CI around above 25 minutes, deployment cycles above 1.5 hours. And with the bug2 build there on CI, more than 90% of the actions are cached. And for local developments, typically it's even more than 99%. So a lot of benefits from the incrementality there. All right. There are a few other topics I want to look at more briefly in the interest of time. So persistent workers was something I had mentioned earlier as sort of an initial attempt in the Bazel side to achieve incremental builds. But of course, the purpose for persistent workers is really to speed up compilation by avoiding repeated setup of compiler runtimes and stuff like this. And you saw that the Amazonka case, the bug2 build was twice as slow as the Cabal build locally. And the reason for this is that the way that the Haskell compiler can be invoked in 2 different ways. Either you use it in so-called one-shot mode, which is to just compile one module at a time, or you give it all the modules of a package and it compiles them all at once. And of course, in that mode, the compiler only has to start up once, and it only has to read the information about package dependencies once, and then it can quickly build all the modules out. And with the incrementality at the module level that we want to have in bug2 and also in Bazel, we cannot really have that. Instead, we have to invoke the Haskell compiler once per module. And that's where this 2x slowdown mostly comes from. So it's a penalty on the compiler startup, package loading, and a bunch of other stuff. And so the idea here is to have a persistent worker for the Haskell compiler so that we have a warm Haskell compiler and we avoid all that repeated startup overhead. And bug2 does support persistent workers locally through a gRPC protocol. And for remote builds, we also added support for the Bazel remote persistent worker protocol. And this is somewhat still work in progress, but it's running at Mercury now, and there a full build can go from 97 minutes to 21 minutes with this persistent worker. So it's clearly a big win. All right. Another topic I want to briefly touch on is the idea of recompilation avoidance. So with these interface files that I mentioned earlier, where when you compile a Haskell module, you get an object and an interface file, and then downstream you're going to depend on those interface files. They contain information like type signatures and symbols and things like this, but they also contain some other information that changes more frequently than you would want to invalidate downstream actions. So even if you make a change that doesn't impact the exposed symbols, you might still make a change to the interface file that invalidates downstream actions. And that's not something we want. And that's also something that the native build tool can avoid. And so both in Bazel and Buck2, there are ways to work around this. And the way to do this is a clever trick around unused inputs. So what you do is, the unused inputs feature is there for build action to say, oh, you provided me all those inputs, but that one I actually didn't read. So if that one changes, don't invalidate me, just keep the cached version. That's the idea behind unused inputs. So what we do is we take those interface files and we tell the build system they were all unused. And then we also take those interface files and we project out the information that is actually relevant for invalidation. It contains a field called the ABI hash. And we make that a used input. And so then if that field changes, the action will be invalidated. If the rest changes, it won't be. And that works both in Bazel and Buck2 because they both have this feature. And then no talk of mine would be complete without mentioning external dependencies. So in Bazel, we can do two things. One is if the Haskell compiler installation that you are using comes with its own set of third-party packages, then you can just import those. And we often do that with Nix-provided compiler toolchains and package sets. Or you can use Bazel to invoke the Haskell package manager and resolve and download third-party dependencies and then build them inside Bazel as individual build actions. That is something that we've implemented on the Bazel side. On the Buck side, so far we have only implemented the import through pre-built Nix-provided packages. But one of the reasons why on the Bazel side we really wanted to have the direct package manager integration is that if the package set is provided as by Nix as part of the compiler toolchain, then if you make any changes to your transitive closure of third-party dependencies, you're going to change the toolchain and invalidate all your Haskell build actions in your project, even if you only add one dependency that is only used by one target. That's clearly not ideal. But in the Buck2 case, thanks to the dynamic dependencies, what we get to do is we can dynamically inspect the Nix-provided package dependency graph and then wire the actions up in such a way that they're only invalidated if the actual package they depend on are invalidated. So then we also get package-level incrementality with third-party dependencies. And another neat feature it has is the Buck extension language, which is the Starlark API to add custom commands. And we can use that to query our project for third-party dependencies and then generate the import metadata we need for Nix and the Buck2 targets, sort of the boilerplate, to avoid duplicated manual efforts. All right. So back to Bazel and in particular dynamic dependencies. So what sorts of languages benefit from dynamic dependencies? Obviously Haskell is one of them. I've talked about it at length. OCaml and the family of languages there can also benefit from this. It sort of has similar properties. There are a bunch of other languages as well. But C++ 20 modules also have this kind of property where, you know, when you compile one module, it produces information about the interface that other module compilations are going to need. And I saw that C++ 20 module support, and was also mentioned earlier, was merged into Bazel. And that's, of course, implemented in the built-in C++ rules in Java. And from what I understood when looking at the code, it also uses Bazel's capabilities of restarting actions to achieve a form of dynamic dependencies. For those that remember the build systems a la carte paper, you might remember that Bazel is classified as a build system with dynamic dependencies in there, even though the Starlark API, of course, does not expose this. And well, as rules Haskell authors, we would like to have that, but I've been told that would be very, very, very difficult, so we'll see. All right. That's all I had. So thank you very much. Again, I work at Tweak by Modus Create. We help people with Bazel migration. So if you need some help, let us know. And we have a booth over there, so come over and talk to us. Thank you very much. And maybe we have some time for questions.
Hi, thank you for the talk. So this is probably a very noobish question. why can't we just have Haskell libraries compile individual source files like the module level instead of at the package level?
Right. So essentially, the Haskell module rule would be doing that, right? If I understand the question correctly. So if I find the slide, this one, right?
Oh.
Then you would have. Okay,
oh, sorry,
the pointer is invisible.
Sorry.
Then you have a rule for building a single Haskell module, and you expose your module dependency graph to Bazel in the build file, and then the Haskell library target says, I depend on those modules. And then if you want the cross-package thing, that's where things get really icky, because so this is noisy and annoying, and with Gazelle, you can auto-generate it with the CPP limitations, but it's still noisy in the diffs and all. But now if you want the cross-package module granular builds, then at this Haskell library target here, it's not going to be enough to say that this Haskell library depends on that other Haskell library. You're also going to have to somehow say that module B depends on module J of that other library and so on.
Because this is how sort of, I guess, C++ works right now in Bazel. I guess there's no big difference or distinction between a module and a library. There's kind of just, I guess in Haskell you have these like two layers of concepts, whereas in the current non-C++ 20 module thing, there's only one, which is the CC library.
But in C++ you don't have the issue, because in C++ if you have a CC library target that has 100 .c files as sources, you can compile those independently. And if you change one of them, you're not going to invalidate the other ones.
Whereas in Haskell you might, right?
But if you have a Haskell library target with 100 modules in them and you change one of them and then you have to rebuild the other 99, that's not so nice.
Right. Okay, thanks for the explanation.
Sure.
Hi, I'm mostly curious about the motivating use case behind this work and the evaluating Bazel and evaluating Buck2. Was there a use case here where it did actually make sense to move a project from Bazel to Buck2? What was the size of that? And I assume that is not a reasonable thing that most projects would be able to do.
Yes, so the use case was going from the native Haskell build tooling to something faster. The size of the code base is there, 1.8 million lines, 18,000 modules. And what we did do was we did evaluate both. So we did evaluate a Bazel setup with the automation and the Haskell module stuff. And that was just noisy, and when you do development on Haskell projects, the module dependency graph can change relatively frequently. So that is just not so nice maintenance overhead.
Okay,
and the team is also here if you want to chat.
Cool. Yeah. So it was a Haskell mono repo and trying to get faster builds. Okay.
That's right.
Cool. Yeah. Thank you.
Welcome.
Hello. I was curious with the persistent workspace that you mentioned, how you ensure deterministic builds that you don't accidentally end up using something that was put in there by a different action that you didn't declare as inputs.
Right, so with a persistent worker, that is indeed a problem, and essentially the answer is you have to make sure that your persistent worker doesn't do that.
I know that a bunch of languages have that, right? C++ and C# and a whole bunch of other stuff have that.
I mean, Java in particular has the persistent worker, right? I'm not so sure about C++. I wouldn't know.
I think it's the shared symbols or something, at least MSVC or something has it.
Okay, maybe there is a thing, yeah.
But
yeah, I mean, what you're doing is you're persisting state in memory and potentially on the file system across build actions. That's what you're doing. And you're sharing that state across build actions. Right. And if you're doing that wrong, that's going to produce issues. So yeah, don't do that.
Sure.
Hey, this is a pretty interesting talk. I was interested because it feels almost like you're creating a subgraph over the top level target graph, which is much more finer grained and is dependent on individual components that are contained within the targets themselves. How does a downstream target module know about the existence of other modules? Like, do you expose every single module as a part of an info provider and essentially they all get lazily resolved? Do you run into any issues like if a downstream target tries to do like a list on a depth set, you end up accidentally evaluating and waiting for everything to resolve. Do you have to be careful about things like that? And what's your unit of caching at that point? Is it at the target level or is it at the module level?
Right, yes. So, I mean, the property that there are two different graphs is kind of shared between Bazel and Bug2, right? You have the target graph
One of them
and the
is the
action
sky graph, and the other one is the target graph, right?
Yeah, exactly. And it's just that in this case, you get to dynamically generate parts of the action graph. So the action graph in the beginning kind of has these black box actions in them, and then during the build, they get resolved and replaced by the fine-grained actions that are part of them. But it's still within the action graph.
I see.
And then the way these dependencies are exposed is through the usual providers interface. So on the target level in your bug files, what you're going to do is you're going to say that library has a depth attribute, and in there you list that other target. And that's what it looks like there. And then in the implementation, you're going to look at the providers that these targets expose, and they're going to have the necessary information about the individual module. So like there's going to be some key values list in there, or
right.
dict in there that exposes the module information.
I see.
Then we're using these dynamic values to forward the module dependency graph that was dynamically resolved between the scope of the dynamic actions. So within the rule implementation itself, you cannot inspect that yet,
right.
but you can forward that handle to the dynamic action you generate, and in there you get to unpack it
I see.
and wire things up.
I see. Got
Yeah.
it. Okay.
And the interface for that is then T-sets, which is the equivalent to depth sets, and it works pretty much the same way.
I see. Cool.
Yeah.
Thanks.
You're welcome. All right. Thank you.
All right, another round of applause for Andreas. Yeah, let me remind you one more time that there will be an unconference session, and you can submit your own ideas or you can vote on them.
We already have the schedule now, so I can do the announcement.
Yeah.
So yeah, we already have the schedule for the unconference session. We have build foundation at Cottonwood A and attach non-cache busting metadata to actions BES in Cottonwood B on the first floor. Yeah. And Starlark typing is voted the highest, but to accommodate the facilitator, we are doing it tomorrow. So if you are any of the facilitator or interested in those sessions, please head to the corresponding rooms after the break. Yeah. Oh, it's also being updated on the schedule, so you can also check the information there. Yeah.
And we will be back at 4 p.m. All right. So the break time is over. Please sit down. So next up, we have a sponsored lightning talk by Helen Altschuler, Yuval Kaplan, and Gabriel Rosso about how they manage 1 billion actions a day. So yeah, please give them a warm round of applause.
All right, good to be back here. So as the CEO of EnchFlow, it makes me happy to bring more Bazel engineers on stage who haven't given talks yet. And so this time I'm joined by 2 awesome engineers, Gabriel Russo from Databricks and Yuval Kaplan from EnchFlow. EnchFlow powers world's most complex and critical software with remote execution and caching, observability, and Bazel knowledge. Companies who onboarded into EnchFlow have achieved significant performance and reliability, as well as the cloud cost savings over other options. I talk about how we achieve significant cost savings and performance savings in my sponsor talk at BazelCon 2024. But our Databricks story actually didn't start this way. So this talk is a journey into how we work with our customers, how we give them the value of improved cost, performance, and reliability, and how we use the strength of both companies, scale and data, to optimize performance, cost, and create a great environment. So Databricks runs the largest RBE deployment outside of Google. If anyone here wants to contest that, speak with me after the talk.
All right. So yeah, I'm Gabriel. I work at Databricks. Just to give a little bit about, talk about the scale that we operate on. We have almost 3,000 engineers now. I run a simple line count in our repo, and that gave up almost 100 million lines. Not all of them are human written, but Bazel doesn't care. He has to build all of it anyway. Our code is growing quite a lot. That's the first graph on the top. You can see the very exponential growth of Scala lines, and those are 100% human written. We are a big Scala shop. We also have a lot of JSONet, which is this, or JSONet, I think, which is this configuration language, Rust, Go, Java. Python is growing a lot with all the AI rush. And the bottom graph, you can see the number of actions we are running per day during our builds. We did cross the 2 billion mark at some point as a mistake, but we are about at the 1 billion mark now. And I'm just going to give a quick overview of how our CI works before. So a developer submits a change. We have some fancy models that are running, so we run Bazel queries, we feed that into some machine learned models, we run that against some databases to check against known failures and things like that. That spits out a list of targets that we cannot run in a single machine, so we would actually run Bazel tests in many machines. But that has plenty of problems because we are building the same thing over and over. We are cloning the repo over and over. And even inside those machines, we have noisy neighbor issues. And to combat the noisy neighbors, we actually we actually successfully contributed to Bazel upstream by introducing C-group-based resource isolation on Linux. So you can actually have CPU or memory-based resource isolation today. I think it landed in Bazel 6 or 7. I don't recall. The problem with this, I think there was a talk from Glean earlier today that if you just try to vertically scale, we try to horizontally scale it in a simple way. The cost just grows and the problems keep coming. So if we said, okay, we really need remote execution now. So that's what we did. We partnered with EnchFlow to have remote execution, and we migrated one of our most important CI jobs, which runs like this, the test for Spark. And this graph is a Databricks query, but the blue line shows the runtime, the P90 runtime that developers would have to wait for their CI with remote execution, and the bottom one without. And that's not what we want, right? We want remote execution to make things faster and not slower. So the thing is, at Databricks, we are really good with data processing. So we were actually already ingesting a bunch of Bazel data. For every single Bazel build, we were ingesting all of that data from BEPs and trace files that were also mentioned earlier today. And we can run very simple SQL queries or human Bazel queries, because it's very hard to read those BEP files and whatnot. So we have all of those in tables that we can just query. Even now with AI fancy things, we can just write plain English and it spits out what's going on. And we did the investigation, so we ran a bunch of queries, and then we realized that these targets under //Python were much, much slower in RBE compared to not RBE. And this is the blue line is basically those tests in RBE. So we were like, okay, why that is the case? And it turns out that these targets, they run in Docker, so they are integration tests that require very large Docker images, and they were much slower in remote execution. And because they have a runtime of more than 10 minutes, that's a really significant amount of time for the overall CI job. So I'm going to hand over to Yuval that can explain why those were so much slower and how we made them faster.
Hi. So we drilled down, and the metrics told us that integration tests are quite a bit slower in remote execution. And we know that these are pretty IO-heavy tests. So it's pretty logical, right? We should try faster disks. The original setup that Databricks had used SSDs, and we used EBS. We usually use EBS on machines that don't have local disk, simply because it's a good balance between cost and performance. But in this case, it was clearly not enough. So we switched to SSDs, and we saw some improvement. We saw some performance gain, but now we're running into another problem. We found that we needed really, really large disks for these actions. So here's why. Those tests are running with, they're using Bazel-built Docker images. We build these images using Bazel, and then they get passed on to the action as inputs and loaded into a Docker daemon. Now, this isn't the host machine's Docker daemon. For hermeticity and security, this is the Docker daemon running inside the execution container. And when you have a worker machine that has multiple executors, you end up having n+1 copies. You have one for the input and one for each executor. So when you have ephemeral disks, larger disks mean larger machine types, and these are more expensive by far. So we want to cut back the cost while maintaining the performance. So can we do that? And it turns out that we can. Docker, actually, containerd is pretty modular. And the piece here that's in charge of where the layers are is called a snapshotter. So there's the default snapshotter, which just takes layers and uses overlayFS to provision the file system for a container. There are some fancy snapshotters that implement lazy loading to optimize the loading of large Docker images. And in this case, we needed a snapshotter to fine-tune where we put the images, the layers actually, so we could share them among all the inner Docker daemons. Now, we could do more than that. We could, for example, decide to keep some of the snapshots on fast storage, for example, scratch layers, and read-only layers on slower storage. But we just didn't need to do that because everything now fit on smaller SSDs. And so we achieved the deduplication that we wanted, and we could cut back to using smaller instance types. And besides reducing disk usage, we also saw a pretty significant reduction in test runtime and variance, which you can see in this graph. Now, just to close the loop, we asked ourselves, do we actually need those SSDs, or is the snapshotter good enough with EBS? And it turns out that there's still a small benefit using SSDs. It's not quite as big, but for this specific setup, SSDs were already cheaper, so cheaper and faster, no need to choose.
Yeah, so we don't have time to talk about other optimizations that we've done, but we also were able to ingest all of the RBE server-side data into Databricks, so we can also run SQL queries on those things. And this particular graph shows the overall time it takes for an action to running RBE, the blue line, so the top line, and the bottom line shows the time that the action actually ran, so without uploading inputs and downloading inputs and starting containers and all of that. And we can see that over time we were actually able to basically eliminate the overhead on the P90 level, which significantly improves the overall CI times that our developers have to face. So this was really cool. I think this graph is really cool, that the overhead basically goes away, and we can see that really easily with Databricks.
It's what we live for, to see our customers this excited about their developer environment. So we are an extension of your developer experience team at EnchFlow. So we carry the pager for the clusters. We monitor proactively, specifically across 3 parameters: cost, performance, and reliability. And we alert you and make continuous improvements there. Also inspired by this partnership with Databricks and seeing what they've done with the Bazel data, we've also incorporated some of our learnings and implemented that as part of our platform. And so this week we're talking a lot, and you can see about this product. It's called Build Forensics. So that's essentially an extension to our build and test UI that allows you to run queries flexibly in the analytical environment. It's a playground sandbox that you can inspect your builds, but also it's an environment, it's a package that you can import into your own analytical data store, because we notice many of our enterprise customers actually have quite large analytics environments as well. And so if you stop by the EnchFlow booth today, you'll play the analytics game that I talked about earlier, and also we'll send you Cluzel, which is our custom Bazel analytics game, board game actually. And you can also play this game tonight at our happy hour, along with other games, food, drinks, and good company. Thank you. All right, next up, now I'm announcing. So next up is Alex Eagle with Aspect.
Okay. Hello, everyone. I guess I get to advance past that. So this is my favorite time of year, when I get to come to BazelCon and talk about the awesome thing we've built. And this year it's especially awesome. I'm going to be talking about Starlarkification for tasks, how to go past make serve. And you may know our Marvin character here. He's our mascot. I've got 3 new engineers on his team who are going to help to tell my story today. So their names are Nina, Perry, and Ivan. They are at the end of their Bazel migration, so they've already written their blog post and done their BazelCon talk, and so it's very exciting. But something is still not right, because there's a bunch of scripts that are still hanging out in their repo. They have things to install tools and figure out how local dev is supposed to work and CI/CD. Did they do the migration incorrectly? Like, why did they end up with these things? So let's look at a few examples of the scripts that are still sitting in their repo. So they've got this bash script, and sorry, I know there's a lot of code here, but I'll give you the short version, which is that there's some brew installs going on, because if you don't do the right brew installs, then your build's not going to work, right? So hopefully this is up to date. They've also got another bash script that's checked into a special magical path in the repo called tools/Bazel, right? Which is, as we all know, a naughty place that we can script around Bazel and make whatever things happen that we need to. And so there's some startup options being set, and maybe some AWS credentials and things that are going to bust the analysis cache like we do. They've still got a make file. And this is because they didn't manage to translate all of the workflows yet. So like, there's one team in the repo that's like, no, you can't take this away yet. It doesn't quite work the way we want under Bazel. So like, our linting and deployment workflows are still sitting in here. And then, some of those seem comical, but you've all got one of these, which is your CI YAML, which is also wrapping Bazel, and it's got some logic. And you see some of this is packaging, but it doesn't pass the same flags to tar as the other one. So this is probably where a lot of us end up, okay? So what does this mean to these people? So let's start with Nina. She's the new person on the team, and her problem is that she wants to show up to work and be a competent new employee on the team and not come across as a total idiot, except when she tries to follow the README, like, stuff on her computer is not working, right? Did she follow the README? Well, maybe it was out of date, right, or the wiki. So, and this is all of us are like this person when we go to a different part of the code base, or we switch to a different team at our company and stuff is set up differently. So her problem is often, number one, the CI is green, that's this little Bazel box in the background, but then on her computer, it's not working. So it must be her fault because CI is green. But then on the other hand, after she submits her first PR, the CI is red, but is green locally on her machine, right? So is there some weird interaction happening with the CI environment? Maybe the flags aren't set the same locally and on CI. That's a possibility, right? So let's go on to our next person. So this is Perry. He's a product engineer. He's seasoned. He loves to just like sling features. Now that he's using AI half the time, he's, he gets to take more coffee breaks and be even more productive. But then his AI agent is just like constantly running into workflow issues, and so is he, that slows him down, right? So his velocity is slower because of issues with the way these scripts are set up. And then finally, we have somebody on the dev infra team. This probably represents a lot of us in the room. So this is Ivan, and his task is to improve the developer infrastructure for their whole company. And remember that make file I showed you? Man, that kills him because he can't get that team to get rid of it, but he also can't make changes that break them. And so it's really hard for him to have impact in the organization when there's not homogeneity in how Bazel is getting executed in all these different contexts. Okay, so what did they do wrong in their migration? Nothing. They are using Bazel right, but Bazel is not enough because it's missing a task runner. Okay, task runner is the overall concept I'm trying to show here. And to illustrate that, let's look at what Bazel is good at doing. Okay, it's good at doing only two things. Loading an analysis phase, which gives you a dependency graph and an action graph. It's also good at the execution phase, which populates your Bazel out tree with artifacts. And if I hand wave a little bit, test exit codes are just another exit or another artifact that lives in Bazel out. So like it's good at testing only in the sense that it can build the exit code of a test runner. But then there's a much longer list of things that it's just never going to be able to do, right? So setting up the environment I showed, creating and updating build files. Gazelle does that, but Bazel doesn't. Configuring your IDE, writing files back to the source tree, which Google says you shouldn't do. Performing actions that need the entire repo as an input. You would never want to have like an all files file group that touches the whole repo, and so on. So lots of examples, and I'm sure you have some of these in scripts in your repo as well. Another example is Bazel Run, which seems simple enough. It's actually a workflow around Bazel build in disguise, and it's been broken since 2017 when we tried to get the right working directory. Fortunately, you notice it is fixed in Bazel 9, so like Bazel Run is maybe it's fixed all the way. So what I'm getting to here is if you go to the Bazel website and you look down here at this little section and it says endlessly extensible, I would argue that it's only extensible in the sense that it can accept rules that produce more outputs. We would like it to be extensible also in the sense of running tasks that surround Bazel, that orchestrate multiple Bazel calls. And we would like that to be in Starlark because it's a language that we've all been very happy to learn as we've interacted with Bazel. And so what we want here is a Starlark dialect that lets us run tasks. And so this is what we're announcing this year is what we call aspect extension language, which allows you to do just that. And let me show you a few examples. First of all, we've got this new GitHub org that is just a collection of these extensions. I've written a few. We would love to have others of you write more of these and upstream them to this org, makes them easy to find. We can also tag GitHub repos that live anywhere so that you can let people know if you've got one of these extensions. This is it's still pre-release, so if you look in this org today, you'll probably see some mistakes, and we're going to be working on that over the next few weeks. So there's a couple extension points. One of them I'm glad Jay is right up here in the front. Gazelle is awesome, and if you don't know how to write a Gazelle extension yourself, fortunately a lot of the time there's already one available for you. But sometimes there's not, and rules shell is a good example because if you've tried Bazel 9, you've noticed that all of a sudden all of your SH binary targets fail unless they have load statements. And there's no Gazelle extension for shell, and it's actually pretty short, and maybe it doesn't sort of need one. So in fact, using aspect extension language, there's a hook we can use, Gazelle rule kind, where we declare SH binary to come from a certain location. And then we write, we have a Gazelle extension called Orion, which is really just a Starlark bridge that allows us to specify which are the source files that we want to operate over. And then finally, the implementation function. This looks a lot like Starlark you would write to write a rule, right? The implementation function is just saying which targets you want to create. And then this is just built inside of a Gazelle extension, so the result of this goes back to Gazelle to write into the build files. And so this is the sort of thing that's possible, and in fact, this is from the unit test that we run. So we just generate a shell script, we run Bazel run Gazelle, and then we can run Bazel run hello, like we expect, right? Build file generation works, but we didn't have to learn as many APIs. Okay, the next extension point is tasks, and I'll show several examples here. And sorry, there's a bunch of code. You can look through the slides later. I'll just tell you the highlights. So for one example, I came to BazelCon last year and talked about rules-lint, which allows you to run an aspect over your existing library targets to collect lint results and then display them, which is exactly a workflow. So what we do in this task, we declare the task. Again, this looks very much like if you were to write a rule, right? It takes an implementation, and then it has the command line arguments as instead of attributes. So it says what you're allowed to pass on the command line to lint. Then it has an implementation function, which is essentially some flags, and then some conditionals that look at whether it's interactive. And then magically on line 11, we do ctx.bazel.build, because now we're outside of Bazel, and so in Starlark, we can do builds. Okay? Notice on line 13, we're saying events equals true. And so what that means we can do is listen on the build events as they come in. Still right here in Starlark, like I'm processing if I see a named set of files from the build event protocol, I can grab out the file paths, right? And for linting, those file paths are the output of the aspect that tells me what the lint results were, and so I can print them. And so you have access to standard out, standard error, and so that's how this interacts with the user on their terminal. Cool. A fancier example, let's say that, so obviously we've written some APIs in the Starlark host that you can interact with, but if there's APIs missing from that, you can actually load your own using WASM. So in this example, I want to be able to use Bulldozer. I want to be able to reuse it, right? And a lot of us have written Go tooling because Go is the language in which you can access a lot of these common Bazel utilities like Bulldozer. So we just wrapped it on line 9 there with a Go WASM export, saying that the name of the function is going to be edit. We build it with a Go binary that has WASM as its target. And now in Starlark, I can actually call out to Bulldozer. So this is a function called buildTools that's just going to be able to call Bulldozer. The path to the WASM binary is there. And then the way I can use that, we're all about to hear Malta's talk on rules image. So I could actually make a Bulldozer script to add rules image to my module.bazel file. I could write a whole migration that just runs as a command. I write the migration in Starlark, much more principled than any of the wrapper scripts that you've written. This one's definitely too long to read. This one's very cool, and I encourage you to check out on the run repo under the aspect extensions org. Shaheen put this together. So this is Bazel multi-run. So I made fun of Bazel run earlier. Of course, it only takes one target. In this case, we can pass multiple targets to Bazel run, and it will actually open up like a PTY screen that splits your terminal so you can see all the servers running next to each other, which is really cool. And this one uses another WASM binding to a small little Rust program that he wrote around a crate that provides exactly that sort of terminal experience. We can also re-implement coverage, which all of us have probably looked at coverage and wondered, like, why does Bazel even try? Sorry. There's been a lot of work on coverage. It doesn't work great. It has like an LCOV tool that's built in that runs in Java. You can still use Bazel coverage. I re-implemented it as a task that wraps Bazel test, and now I have much more control over, do I want to have LCOV merging? Do I want to just show the report? Do I want to talk to the version control system, find out which files you've changed, and then only show incremental coverage? All of those things are now possible without having to write an awkward script around Bazel. So that is all the time I have right now. We made a little cartoon book so that those of you with kids at home can go home and tell them all about the aspect extension language using colorful and very, very simple language. Shout out to our sales account executive, Jared, for the text on this. It gives me credit for illustrations, but you all know that's not true. I had AI do it. You can also, on the back of that, it's got a QR code. So we've got these little Marvin characters. He comes and saves the build, and I would love to toss a couple of these if anybody wants to raise their hand and make this. Oh, you're so far away back there. Okay. Oh, almost. Okay,
right.
Can you just pass that back? Okay, excellent. Thank you very much. Please give us a try. Check out aspect.build/AXL, and we would love to host some of your extensions.
All right, next up we have Malte Paul from Twig by Modus Create, and he's going to talk to us about bringing large files to Buck2 and Bazel.
All right. So yeah, welcome to my talk. I'm going to talk about Assetfuse. Assetfuse is a fuse file system that we wrote at Twig, and it allows you to optimize for very large files that you want to feed into Bazel or Buck2. So first of all, I want you to think about this setup. You have your build system, Bazel, and you have a remote cache, and you have remote executors. But you have a CI where the CI runners are ephemeral. So the Bazel output base is not preserved, and the Bazel server itself is also not preserved. You may think that because you use remote execution that this is still fast, but in practice, you will see that things like repository rules still need to rerun in this setup. So this can be very slow if you have repository rules that create large files as outputs. And yeah, in the rest of the talk, I will talk about why this is a problem, why exactly this is slow, and an interesting way of working around this. So this, what you see here is the model that build systems like Bazel and Bug2 are modeled around. So the smallest unit that you can work with is an action, and an action just turns inputs into outputs. In this case, yeah, you have your command line arguments, your environment variables, and you have this set of input files. And the important thing to notice here is that the input files, they need to be hashed to be passed into this Merkle tree structure, which in the end gets included into this action message, which gets hashed again and then sent over for remote execution. So when you want to run an action in remote execution, you need to hash all of the input files at some point. Then there's another concept that's important. In Bazel, you have two kinds of files. You have source files that have no generating actions. So these just exist in the file system in advance. And then you have generated files marked in blue here. And these are the outputs of other actions. And now you may think, so what about repositories that are not the root repository? They also have source files, but they don't have a generating action. Where do they come from? And the answer is they come from repository rules. So you have your root module that just has source files that are on disk. It's pretty clear the source files already exist and Bazel can see them. And then there are other modules and repositories, and these can be instantiated using repository rules. And the important thing to note here is whenever you want to depend on a target from another repository, Bazel needs to actually materialize this repository in order to analyze the build files inside of that repository. And that happens in the loading phase. And yeah, the important thing here is the repository rule is a single unit, and it's not, you cannot break it down. So Bazel needs to run the whole repository rule to materialize the files just so they can analyze the build files so you can use them. So this can be very expensive for large repositories. So if you want to run an action remotely, I already said it before, but just to make this very clear, you need to calculate the action digest, and then you can check in the remote cache whether or not the action was already executed before. If not, then yeah, of course, the inputs need to be in the remote cache, and then you can run the action. But yeah, the important part is you need to calculate the action digest. And if we think about the action message again, we need to calculate the hashes of all of the files that go into the action. And for that, you need to hash the file contents. And Bazel has a very nice trick where you can either just read the file from front to back and calculate the hash, or you can opt into an optimization where you check for a specific extended attribute, and if it is set, then you can just read that instead of reading the whole file. And what this means is, in practice, when you have remote execution, the files from these external repositories, they don't actually need to be there on disk, and Bazel doesn't actually need to read them. Bazel just needs to do this extended attribute check to get the digest. And it will never actually look at the source files in any other way. So from this, we get to a concrete problem statement. Repositories need to be completely materialized in a repository rule. This is bad, and it kills build without the bytes. For the source files in repositories, you cannot just avoid doing it. It all needs to happen on the machine where Bazel runs. The build files need to exist so that Bazel can analyze them, and all of this is kind of pointless because for remote execution, these source files only need to exist in the remote cache. Now there's one more building block. It's the remote asset API. It's part of the remote execution spec, and it defines a way where you can fetch a blob. You send a request to this endpoint, and you tell it, hey, I want this file. Here's a URI where you can fetch it from the internet, and here's an expected hash. And then the remote, the implementation, the fetch service can then fetch it from the internet, store it in the content addressable storage, and give you back the digest. And then later on, you can actually read the data from the content addressable storage. So this brings me to the architecture of Assetfuse. You have Bazel or Bug2, and then you have this custom Fuse file system that Bazel can read from. This file system can talk to your Bazel remote cache, and the remote cache can fetch files from the internet. Assetfuse uses a manifest that just stores the paths that you want to exist in the file system, along with the expected hash of those files and their sizes. And then there are some ways to specify where to get the files from, so the source. Yeah, that brings me to the way that the file system works. So if the user space wants to read a file, it will send a read system call to the Fuse file system. The file system can then send a fetch request to the remote asset API. This will then ensure that the file exists in the remote cache by downloading it from the internet. And then we get back the digest. And then the Fuse file system can download parts of the file from the remote cache and return them to user space. And the other optimization is if we just need to get the digest of the file using the extended attribute, we can just load the blob in the background using the fetch API, but we can immediately return the digest back to the user space. So the file never needs to be downloaded to the local machine. So this brings us to some kind of comparison. So this is a bit like Git LFS on steroids. Git LFS allows you to store very large files outside of Git, and instead have a little manifest that describes the data using a hash and a source, and yeah, also the size of the blob. And then later you can download these files using some plugins to Git. And similarly, there's things like data version control that do the same thing in the end. You store the hash of the file and the source, and then later you can get the file. And they are not stored in Git. And with Assetfuse, you also have this manifest, so it's pretty similar in that regard. But it's different in another regard, which is Git LFS and DVC both need to materialize these files ahead of time. So you need to say, download all of these files and make them available locally. Whereas with Assetfuse, you just mount the file system and it happens immediately, and then the file contents get loaded lazily. So at the end, you have this structure where you have your build tool, Bazel or Bug2, connected to the remote cache, and you also have Assetfuse, the file system, that is connected to the same backend. And Assetfuse can preload the files into the remote cache, which are then available for remote execution. So this is the benefits are quite clear. When you have large files, they can be prefetched. And the files never need to be available locally. So you can work with very large files very quickly. Yeah, there are a lot of other Fuse implementations that are relevant. I'm running out of time, so I will skip over this a little bit. Build Barn also uses Fuse extensively, using for BB Client D, for example. So the ideas are not new, but we are remixing them in a new way. Then there are some other things we would like to do in the future, like fetching full directories, like tar files and Git repositories, improve caching, and using things like Git LFS as a data source or some other formats. And now the most important thing is, in practice, this is no longer relevant, because with Bazel 9, Fabian added the experimental remote repo contents cache, and this will make repository rules cacheable in a remote cache, so you don't need to use these hacks like a custom file system. So yeah, thank you very much, Fabian. It is still a very interesting experiment, but I would like to say this is a better solution. So thank you very much for the time, and yeah, that's my talk.
Cool. Next up, we have Jay Conrad from EngeFlow talking about lightning fast build file generation with Gazelle lazy indexing.
Hello, everyone. My name is Jay, and today I'm going to talk to you about a new feature in Gazelle, or a new optimization, really, lazy indexing. It makes Gazelle much faster when it's run on a single directory. So I actually want to start by going over a little bit of history. First, where did the name Gazelle come from? So within Google, there was a tool called Glaze. Glaze would generate build files for Go packages, one directory at a time. So you generally run Glaze. It would read all the Go files in a directory. It would read the package names and imports, and it would translate the imports to the the Blaze labels within Google 3, and then write out the build files. And it could do that very quickly because Google 3 had a very strong convention mapping import strings to labels. Like, things had to be in a certain place. So Glaze could actually run in about 50 milliseconds. And as a result, people would configure their editors to just run Glaze whenever they saved a file. As a result, a lot of Go developers didn't even think about build files. Like, they just never opened them. You'd just be able to write your code, save your files, run your build commands, see your test pass, and so on. Just like a whole layer you could just totally forget about. I'd really love Gazelle to get to that stage, but the world outside Google's monorepo is much more complicated, so we have a ways to go. So some more history. Gazelle was first introduced in 2016 by Yuki Sanada. It was used to fetch external Go projects. I've never met her, but I hope she's pleased with everything that we've done since then. I joined the Go tools team in 2017 along with Ian Cottrell, and we worked on Rules Go and Gazelle together to improve the developer experience for Kubernetes. At the end of 2018, I added Gazelle's extension interface, so we were able to pull protobuf and Go outside of the core and support other languages. And we got our first other language in open source in 2020, so adding BZL library targets. So thanks to Andrew Allen for adding that. In 2023, Gazelle gained support for Bzlmod, which is actually simpler than dealing with workspace, so I'm very happy for that. And this year, we have Gazelle 2.0 proposal and lazy indexing. So before we get to lazy indexing, I want to go over kind of a mental model of how Gazelle works. So you can run it either in single directory or across an entire repo. We'll just talk about single directory today. And so the first pass is it parses your build files, and it reads your source files, and it reads the configuration, and it figures out what rules it thinks should be there. And it merges those in memory with any existing rules in the build file. And as part of this pass, it also builds an index of all the library rules in the repo, and it needs to read all of the build files in order to do that. And so in the second pass, it does dependency resolution using this index. So it will map the import strings of each language into Bazel rules. It will set the deps attribute of each generated rule. It merges again, formats the build file, and writes it out. So I mentioned Gazelle needs to index all the build files in the repo, and yeah, as you might guess, that's kind of slow, and it seems really slow if you only edited one source file. You expect a small change to have a small impact. So it varies a lot. For Kubernetes back in 2018, it took up to 30 seconds. So this was obviously a source of friction for them. They didn't quite like Bazel because of this and a few other reasons. Computers are faster now. Gazelle is faster, but take that number for what it is. Within EngeFlow, we have a fairly small repo. It still takes about 800 milliseconds. Cockroach Labs, more optimized, larger open source Go repo, 150 milliseconds, not bad. Uber's monorepo, 25 seconds. So they have a very large repo and a lot of extensions. But obviously, it is a source of frustration. So why did we do indexing this way? Glaze didn't need any indexing at all. It could just look in a directory, didn't need any more context than that. But as I said, the world outside Google is complicated. So before Go modules, you could have Go vendor directories pretty much anywhere. So there wasn't a one-to-one correspondence between import strings and Bazel labels. And protobuf was even worse. So you could have your directory of proto files anywhere, but each proto file can declare how it wants to be imported, like what import string, what class name it should generate, and so on. So not only did Gazelle need to know something about the repository structure, but it also needed to read the file contents to see how something should be imported. So indexing solved that problem, full indexing solved that problem, and most open source repos were small enough that it was kind of an acceptable trade-off, only marginally so for Kubernetes. But we can do better, which leads me to lazy indexing. So most directories, most import strings have some structure. So even though we can't do a purely textual transformation, we can generally have Gazelle index a small number of directories when it sees an import string. So let's say we're in module example.com/m, and we're importing example.com/m/foo/bar. We would like Gazelle to just read the directory foo/bar and see if the library is there. Or say we're importing another package outside our module, example.com/p/q. Gazelle should look in our vendor directory. That's where we would expect to find that. So that's an easy case, the common case. What if you have a vendor directory with a non-standard name? So in Inflow, we have third-party Go, third-party Java, and so on. We can tell Gazelle about that with a Go search directive. So this just adds a directory to a search list. So now when we import example.com/p/q, Gazelle will look in third-party Go in addition to our vendor directory. What about something narrower, a little bit weirder? Maybe we created a fork of our dependency, example.com/p, and we put it in a directory that doesn't have the full name, fork/p. So this Go search directive can strip the prefix for you. So this says that if an import has the prefix example.com/p, then look in the fork/p directory without that prefix. So how does this work? Well, Gazelle needs some language-specific intelligence. So each extension needs to support this by returning a list of directories to index through this new rels to index field. That's based on the import strings that are seen in source files. So each extension can define a search directive like Go search. We also have proto search and CC search. They have a little bit different syntax that's better adapted for those languages. And once you have all this, then you can run Gazelle in a single directory with the flags index equals lazy and r equals false, and that disables recursion. And then Gazelle only indexes directories that it was told to update, plus the directories requested by extensions, plus their parent directories, because Gazelle needs to read some configuration out of the build files anyway. So that's a lot fewer build files to read than the entire repo. So this generally saves a lot of time. And in addition to this, as part of the optimization work, Gazelle now reads directory metadata in parallel with multiple threads, and it caches everything in memory. So we don't do a lot of redundant I/O. So thanks to Jason Bedard for doing that work. That's enabled whether or not you're using lazy indexing, and it sped things up quite a bit. So with those changes, Gazelle now runs considerably faster in most repos with very little additional configuration. So with a few Go search directives in Inflow, we got it down to about 100 milliseconds. And Uber went down to 352 milliseconds, a 99% improvement. So they're still working on this. There are more extensions to adapt to this, but it's very promising. I should add these numbers are with Gazelle run directly. If you run it through Bazel run, that adds 500 to 1,000 milliseconds of overhead. So take that into account. Well, why does this matter? Speed is really important to me. I'd like to convince everyone that speed should be important to you too. It's an important feature for interactive tools in particular. It changes how we use our tools, and it changes how we feel about them. It keeps us productive and focused. So if something takes 50 milliseconds, like Glaze did, you can just run it every time you save a file. You don't even have to think about this whole thing. And if it takes 10 seconds, well, you run it when you have to, like if you add a new file or something. If it takes 100 seconds, you'll only run it in CI to validate your changes, but you're going to do most of your edits by hand. And if it takes 1,000 seconds, well, it's probably not worth running at all. So if a tool is fast, you'll use it for more things. It's actually more useful. What comes next? Well, we'll add support for lazy indexing to more open source Gazelle extensions. So it's in Go, Proto, and C++ already. If you maintain an extension and would like to add this, whether it's public or private, talk to me. I'd love to help. We have some documentation on how to write an extension, and there's a section in there for lazy indexing. So that's in extend.md in the Gazelle repo. And I mentioned in the keynote that we're working on a proposal for Gazelle 2.0, and one of the proposals in there is to turn lazy indexing, turn that on by default. So hopefully you'll be seeing a lot more of this. So please try it out. Let us know how it goes. That's it. Thank you, everyone.
Thanks. Next is Juan Ortega from Bedrock Robotics.
Oh, is this somebody else's laptop? I don't know. Can I just use this? Can I use my own laptop? Yeah, it's me. Thanks.
Just give me 1 second. I'm gonna unmute your mic once I get back there.
Yeah. All right. Hello, everyone. My name is Juan Ortega. I work at Bedrock Robotics as a developer software platform engineer. And today I'll talk to you about multi-platform and sanitizer builds, all with one command. So over the course of my time in the AV, autonomous vehicle, and robotics industry, I find that there's a common theme. Everybody wants to be able to build for multiple architectures, multiple OSs, and then also maybe be able to do sanitizer, address sanitizer, threat sanitizer, CUDA, no CUDA, optimize, debug builds. And this is a common theme that we want to be able to do across all the companies I've worked at. So what's the old way that we do things is you typically do a -- platforms for the particular platform you want to build for. Maybe you add some compile option and link options for the sanitizer test. And if you want to be able to do both of those, you basically have to add all the flags. This is bad for a couple of reasons. One is that you have to run them in serial, so you don't get all the compiling, all the parallel compiling that you can optimize for. You also discard the analysis cache every time you do this, so that's another place that things are slow, as well as you'll typically overwrite objects or the final binaries for the different binaries that you're building for. So we took one out of my old series that I love, Lord of the Rings, that we want to be able to have one command to rule them all, right? We basically just want, the golden standard is basically being able to do Bazel build ... So, and then basically with that, we should be able to build all the different targets that we need. This is accomplishable using Bazel transitions, but Bazel transitions, I feel like, were pretty hard to adopt. They require building some special rules to be able to do that, and so forth. So there have been a couple of open source rules that have been introduced to make this easier. Today, I'm going to reference one that Fabian open sourced, which is with config. I found that this made it very easy to be able to wrap around another rule and basically add transitions to that particular rule set. But what I found with this rule was there was a lot of boilerplate code needed to transition over each one of these. So if you notice the talk that I had, the configs that I had before, I had 3 different configs, and then as I wanted to do additional things with multiple rules, I had to create different builders for each type of rule. So on the left column, I can see that I wanted to build for x86, and then or ARM64, and then I wanted to also build an address sanitizer rule, and then if I wanted to do one that had both of them, I would have to have a third row that basically configured it like that. And then in my build.bazel file, I'd have to load each test rule and instantiate it, which makes it not super easy to manage, as well as, and then I would have to like store all the sources and dependencies inside variables. So what's the ideal state that we want to be in? I wrote this rule called CC transitions. So basically, the idea is that I want to have one CC test macro that can really generate all these different targets for me. That's what I went out and did. So the idea is simple. Basically, we have a YAML configuration where you define what are all the different configurations and platforms you want to be able to create, and then you instantiate your module extension with that configuration YAML, and then load that particular CC test that got created. You define it once, and then there's these 2 new attributes, platforms and configs, that basically map back to your config YAML file, and Bazel will go off and create all the different with config boilerplate files in an external repository, and then create this macro, the CC test macro that you can call one time. What does this translate to? Using the same example that was in the previous slide, this basically creates a macro that has all these extra Bazel targets in them. So there's the standard Bazel test, the test target, which is basically for my host platform with no special compile options or link options. Then there's test.asan and tsan, which basically will add all the different flags that I want for those particular configurations. Then I can also do cross-compiling for Linux x86, cross-compiling with Linux x86 as well as asan and tsan, or for ARM64 as well. There are a couple of drawbacks for this. One is basically that you are compiling everything in parallel, so you're taking a lot more disk space, as well as your Bazel analysis graph is going to be a lot bigger. So I haven't actually done any profiling of the analysis cache, so I'd be curious to see what that kind of looks like. But this will at least allow you to be able to do Bazel build ... and compile everything all at once, test everything all at once. And then additionally, if you do want to not compile some things, each of them come with their own test tag filters as well. So you can basically add some configs to say, don't build these particular targets, and only do it when I specify specific test tag filters. I have open sourced a very small version of this. So I think that there will be more improvements to come over time, but people are welcome to use it, add feedback, as well as contribute with pull requests. That's all I have for today.
Next is Brad Zacher.
Hey, my name is Brad Zacher, and I'm a software engineer at Canva. Today, I'm here to talk to you about how we use Bazel and a new TypeScript flag to greatly improve our build performance. TypeScript type checks are not too dissimilar to build actions you get from statically typed languages like C or Java or Go. The main difference is that type checks aren't, they're meant to be pure validation actions. They don't have build outputs. We instrumented one of the core workflows that our developers use to type check their front-end code. This workflow takes the PR's changes, resolves into a set of reverse dependencies, and then runs those targets against RBE. The metrics showed that our performance was horrendous. Even in the P50 case, it took almost 2 minutes to type check a PR. And as the p-values grew, the runtimes grew exponentially as well, which led to a horrible DevX. One of the major problems with TypeScript performance is that it's single-threaded. There's not a whole lot you can do about this because it's a design limitation of TypeScript itself, but there are ways you can mitigate it. One simple way is to parallelize the build yourself. By splitting up your big targets into smaller targets, Bazel can orchestrate more instances of TypeScript, and thus you can get better performance out of your build. This works really great when using RBE as well, because you can distribute those extra builds across RBE for even better performance. At Canva, we went really hard in this direction, and we essentially have one build file and one tsconfig per folder. We have some custom in-house tooling. We don't use Gazelle. We have some custom tooling, which scans the source files and generates both the tsconfig and the build file at the same time. And for a point of scale, we've got about 105,000 TypeScript files and covered by about 40,000 Bazel packages. When we had a deeper look at the performance of our TypeScript build, we realized there's a big difference between implementation and module signature dependency graphs, and that's a bit of an implementation detail of TypeScript. TypeScript has two ways of representing any given file. There's the implementation, which is the code that the user writes, and there's the module signature, or the declaration file, which is just a representation of the externally visible bits of the file. For those of you used to languages like C, this will look a lot like a header file, with the main point of difference being that declaration files are generally not authored by humans. One major difference you can see between the two representations is that the implementation has a lot more imports than the module signature. When we throw away the implementation details, we can vastly reduce the size of the dependency graph. And this is a really important thing because during a type check, TypeScript does not use the implementations for the dependencies. It only uses the declaration files. The traditional Bazel dependency graph is based on the implementation dependencies. And this is fine if you're trying to do a build or you're trying to run the code. However, if you're doing a type check, this leads to a whole lot of problems in terms of including unnecessary files. All these unnecessary files lead to cache invalidations and just running actions that are completely and provably useless. Naively, you might just say, well, why don't we use the module signature dependency graph then? Unfortunately, it's not quite that simple. The reason it's not simple is because deriving the module signature is pretty hard, surprisingly hard. Here's a simple example to illustrate why it can be really hard. Here we just define a simple function with no return type, which is one of the things that TypeScript lets you do, is to skip annotations everywhere, and it returns a value that comes from a dependency. At type check time, TypeScript can scan the body of the function and understand what the return type should be, and then use that in its type information to type check the entire code base. However, when we need to derive a module signature for this, the return type it's unknown. We can't decide what that is without doing the full analysis that TypeScript does. And this leads you to knowing that, well, declaration files require a type check to resolve, which creates a huge problem. If we want to type check a target, we have to get the declaration files for all of its dependencies. But to get those to type check those dependencies, we need to get the declaration files for those dependencies, and so on and so forth. And you have type checks all the way down. Putting in terms of a Bazel action graph, the type check actions all take source files from the disk, but they also take the declaration files, and those declaration files are build outputs of the other type checks. If type checks are slow, this means you've got a slow and horrible critical path in your build, which just destroys your build performance. If only there was a way to generate the declarations without a type check. If we could break that chain, that would lead to so many build performance improvements we could unlock. Thankfully, recently TypeScript released a new feature called isolated declarations. Isolated declarations enforces that a file's module signature is statically annotated. When you turn it on, TypeScript will start to emit a bunch of errors for you. Anywhere that a skipped annotation cannot be trivially inferred, which means that if you've got a function without a return type or a variable that uses a dynamic value, TypeScript will enforce that you add an annotation explicitly in the code. All these extra annotations provide a really important constraint on the code. It makes the declaration file generation a single file, AST-only transform. Simply put, it means that we no longer need a type check to generate declaration files. This opens the door to a lot of really amazing improvements. First of all, declaration file generation can be much, much faster. In this simple example, I found a package in the Canvas code base which has about 20 files in it. I used the old typecheck method to generate the declaration files, and it took about 860 milliseconds. In this next run, I used TypeScript's own isolated declarations transform, and this ran in 340 milliseconds, which is over twice as fast. But a really important outcome is that now that it's a simple AST transform, third-party tools can really trivially introduce their own transforms. In this third run, I used OXC to do the transform, and it did it in just 5 milliseconds. That's 168 times faster than the old typecheck method. We can integrate this new tooling into our Bazel actions to vastly improve our build performance. At Canva, we introduced a new action which uses OXC to generate the declaration files. This action is a pure source file only action. It has no transitive dependencies, so it's really fast to execute and really fast to cache as well. And importantly, you can see that now our typecheck actions have no build outputs. They have no dependencies. This unlocks a major problem in our build in that now our typechecks are completely and utterly parallelizable, infinitely parallelizable. And our declaration generation as well, because it has no transitive dependencies, they're also infinitely parallelizable, which means that the critical path of the build is now at most 2 actions long, and both actions are fully and completely parallelizable. We can also use this new tooling in our build file generation to vastly reduce the dependency graph of our targets. Before, we used to just emit the implementation dependencies into our build files. Afterwards, by using OXC, we're able to emit both the implementation dependency graphs and the module signature dependency graph into the build files. When our typecheck action runs, instead of collecting the transitive dependencies using the implementation dependencies, instead we collect the transitive dependencies via the module signature dependencies. The result is that we can cull all of those useless files. All those useless actions that we had before are now gone. That means there's fewer action inputs per action, there's fewer cache invalidations that happen per run, and there's just fewer actions that need to be scheduled and tried altogether. At Canva, we spent the better part of 3 or 4 months building out the infra, and most of that time was spent code modding the code base. And we saw some really amazing results from this. First of all, the number of typecheck actions run per PR validation reduced significantly by 73 to 81%. In the P95 case, that's over 10,000 fewer actions that are run per PR validation. And this reduction in action leads to better build time performance as well. We saw a 53 to 60% reduction in typecheck times as well. Again, in the P95 case, that's a 10-minute reduction in typecheck times. And the P50 case as well is now under 1 minute. And these runtime improvements directly translate to developer happiness as well. We saw a 70% increase in the usage of the local typecheck runs. That means that people are relying less on CI and are relying more on the local, fast typecheck runs. It's worth noting that we're only about 90% of the way through our migration so far. There's still about 3,000 packages that we have to migrate to isolated declarations. So we expect even further build performance improvements as we get to 100%. Hopefully this inspires you to have a look at isolated declarations for your own code base. Thank you.
Next is David Agassi from Robinhood.
Hello. My name is David Agassi. I work on the front-end platform team at Robinhood, and I'm going to be talking about how we built our recent application, Robinhood Legends, and optimized for scale as we built out. So really quick, Legends, for those of you who may not know, is an advanced trader application that you can use directly in your browser, no downloads required. The things I'll be covering today are the size of the team and the code base, the design constraints that we placed on ourselves as we built out this application, patterns that we used to scale on a larger front-end code base, hurdles that we faced when scaling those patterns, and finally the outcomes. So as of last month, the code base is about 1 million lines of code, 8,000 files, 1,700 build files, spread across 30 web engineers. This doesn't include any third-party modules or the rest of our monorepo code. In terms of design constraints, we wanted everything to be within Bazel, including local development, which was definitely a challenge. We wanted to be ECMAScript first for JavaScript so that we were adopting the latest web standards. We wanted to make sure that we were meeting the expectations of web engineers and being ergonomic to the patterns that they wanted in terms of running scripts. And additionally, we wanted build files to be generated on behalf of the user so that there was no need for them to be writing build files by hand. So in terms of patterns, we came up with a dual macro pattern to scale. On the left, we have a source file pattern, which for any file that was used within the production code base, it would run through this source macro that handles image compression, type checking, transpilation, linting, some coverage logic, and CSS transformations. On the right, we have a test macro, which depends on the first one, and then additionally runs jest. This is going to be hard to see, so please look at the slides, but these are what the generic macros will look like, so you can look at them afterwards. Additionally, for Gazelle, the way we were able to accomplish this was using Aspect's JS Gazelle plugin with a couple of patches. So you can use that plugin with map kind on TS project, and in our case, we mapped it to the source macro, allowing Gazelle to generate build files on behalf of the user for source. And then you can, if you patch it, I think it might be supported now, add a test target, and for that, we passed it our test macro. That way, Gazelle manages both source files and test files. One little note here that I figured out, if you make a folder within your source directory and you do a map kind again within that folder, you can support multiple test types. So we also have playwright tests within our code base, but they live in their own subfolder. Lastly, in terms of compilation, we have a top-level RSPack target, which all of our dependencies ladder up to, given a single entry point. This is an example of that target. Again, please look at the slides afterwards so you can see a more readable version. So some of the hurdles that we faced. Not all tools understand Bazel. We found this specifically with Playwright, needed a couple of internal patches to make it support running locally. We initially had some slower development cycles than we would have liked until we were able to optimize the build graph and make running iBazel locally a lot faster. At first, Gazelle plugins didn't support tests, so as I mentioned, we patched that. Coverage was completely custom to gather coverage from across 2 different test runners with correct line syntax highlighting and going through the Bazel coverage reporter. We had a lot of issues with the broader JS ecosystem, not within Bazel, just having ESM forward modules. There was additionally issues with getting Playwright visual snapshot tests between macOS and Linux. Little heads up there, if you can build a container on macOS for Linux, you can schedule your Playwright tests in that container and take the output of that as your snapshot to have CI parity. And then lastly, build file generation was not smooth at first. We used a Webpack plugin to kind of prompt people to do what they needed to do until such time that we were able to start utilizing iBazel fix commands. So tips and strategies, we went with the put a build file in every folder. This may be different depending on your code base, but for us it was very helpful. We opted for Rust-based tooling as much as possible because of the speed benefits it provides. As to the prior talk, we also used isolated declarations and saw a huge improvement from doing that. On larger, heavier tests like Playwright, we needed a default sharding amount of between 12 and 15 just to avoid flakiness or noisy neighbor problems. And then specifically for Playwright, because we're using web bundles, we have to produce a production bundle, or the actual test time to start was about 30 seconds. So impacts and outcomes. On CI, we benchmarked this application versus our older web application that was on Rules Node.js, and it's about 55% faster, P95 and P50. Over the course of the production of the application, we were able to get build file generation down from 2 minutes to about 20 seconds. Now we have developers who can onboard with a single command, and they can make PRs same day without environment setup. We were able to get our flakes down to a manageable amount, about maybe 10 a week, and our cache hit rates are way higher than they were before. Also, developer satisfaction in the web community with Bazel has improved dramatically since this, as we have abstracted most of the Bazel problems from our developers. And that's it. I'd like to thank you all for coming.
And one more, Daniel Tegard from Twig.
Hi, everybody. This is Lights, Camera, Builds, building audio and video with Bazel. So on a normal day, Bazel builds software. And it builds it fast and correctly, and it aggressively caches its outputs to avoid rebuilding. But you all know that pitch already. So how does it do that? Bazel rules define actions on inputs and produce outputs. And under the hood, inside these rules, you have actions. And a rule will invoke something like ctxactions.run to call usually a compiler or any tool that's taking in inputs and transforming them into outputs. And so typically, in the simplest case, you've got code coming in, a compiler is processing that and outputting an executable binary. But what if we wanted to build audio files instead? So I've been, as a little side project for fun, working on a still unfinished Bazel rule set called Rules Multimedia that aims to do just this. But in order to build audio, we'd need an audio compiler that would play an equivalent role. And there's a great tool for that called SOX, which stands for Sound Exchange, the Swiss Army knife of audio manipulation. It's an open source tool that takes in audio, processes it, and outputs more audio, and can apply effects in the process. And so there's a huge variety of effects that you can apply. You can add delay, you can add reverb, you can automatically trim silence, you can also deliberately trim a certain amount of silence off the beginning and you can shift the pitch, you can shift the speed, you can shift the tempo, you can add reverb, repeat, dither. Dither should cause a little bit of worry. If you know about audio processing, what that's doing is it's mixing random signal into the audio file, which obviously is non-deterministic by default, which would break caching and wouldn't be particularly nice for a Bazel rule. Thankfully, there is a -R flag on SOX that sets a random seed. You can also turn off dither, and so through either one of these methods, you can eliminate that that source of indeterminate results and end up with something reproducible. And so beyond that, SOX is actually a suite of tools. So there's SOX itself, which manipulates audio files, and SOXy, which shows metadata about audio files, Rec, which records audio, and Play, that plays audio. And so for now, I've put together a tool chain for all of the multimedia tools that I'm using, and I'm just pulling them in through rules Nix packages right now. Maybe at some point I'll try and find a way that doesn't require dependency on Nix, but for my purposes right now, it means I've got a hermetic tool chain. Now, the fact that SOX takes in audio and outputs audio has some implications for Bazel rules. Typically, in a normal rule set, we'll see patterns like mylang library and mylang binary. that will each take sources and depths, because you can build up a dependency graph of libraries that are each outputting intermediate compilation steps and keeping track of them in providers. And you need to keep track of all of the transitive dependencies of your libraries until you can finally feed them into a binary. And so you're bringing in each of these targets, or in each of these rules in the targets you're defining with them, you are having to identify source files and also dependencies that are typically pre-built. Since our SOX audio rule is just audio all the way down, we just have sources, which can also include other SOX audio targets. And each audio file is fully self-contained, so we don't need to track depths. So the typical starting point is to get some audio together. And so you can invoke rec like this with Bazel if you want to, but you can just put audio files into a repository, into your Git repository, or use Git LFS if the files get too big. But you just want to get them into your Bazel workspace. And then you can start defining audio targets and that take those audio files and apply effects on them. And so here is, we take our piano file that we recorded and define a new target that takes that as a source and applies an effect to slow it down. And we're calling that slow. We can also define targets that take in multiple audio files and combine them in particular ways, adding effects in the process. But we can also define how we combine them. So by default, SOX will just concatenate the files one after the other, or the audio and the files, into a single audio file. But we can also mix that audio together. So we can mix it into multiple channels. We can merge it into one channel. And one cool thing that we're doing here also is that we can make the SOX audio rule executable. And so you can Bazel run that audio, and it will play it on the command line. And we do that just by, after doing the initial context actions.run to build the audio file, we can also write out a script that just calls play on the resulting output. We can also use the Soxy tool, which outputs metadata, as something to build automated testing on. And so when we run Soxy on an audio file, it will output a bunch of metadata that might be useful for us to check. And so the number of channels, the sample rate, the precision, the duration. And then we can write SOX tests that assert that metadata is accurate. The same, and we're not talking too much about video today, but you can do the same thing with video using FFmpeg, which is a very powerful tool for manipulating both audio and video. And so there's some overlap, and we can do things that SOX can't do, and we can also do some of the same things with video. And there are analogous tools to Play and Soxy, FFplay and FFprobe, to respectively play audio and video and print media file metadata. And so what we have here is, what we end up with is declarative audio and video editing. We can structure a graph of audio and video manipulations. Since SOX, when we set the right flags, is reproducible, we can cache intermediate steps and only recompute things when the underlying audio files or the targets have changed. And we can play back intermediate targets, and as well as the final results. And we can test that output media conforms to specifications. Can it compete with professional audio and video editing software? Of course not. But you can do cool things with it. And I think it's being able to structure a graph of audio manipulations is a fun approach that I don't know if it has been tried too much. And so last night in my hotel room, I decided it would be fun to make something really silly just to show this off. And so I just recorded myself saying BazelCon and then thumping myself on the chest to get the bass drum sound. I processed each of those components, and then SOX can also output, without any inputs, it can also, like, it has a built-in synth. And so you can synthesize audio. So I synthesized this weird synth sound from that. And then in the end, I combine it all, mix it together into a single audio file, and repeat it. Oh yes, and previously I'd repeated the bass drum, so we got the kind of like 4 on the floor type thing. And we can see if we can play it. I'm not sure if the playing will work. If not, you can trust me that it is quite stupid. But I think it does showcase that you can compose audio. Oh, sorry? Oh, one more time? OK. I guess not. Yeah, so this is just kind of a starting point. There are some other ideas that I want to incorporate into this. One is an aspect that can traverse your build graph and synthesize audio based on the shape of your build graph. And so I started to work on this. It works, but it sounds bad right now. I would like it to be something that both is somewhat informative, and you can actually hear the shape of your build graph and also sounds nice. I told a coworker today about this, and he said that most build graphs I imagine sounding like this. And I said that's pretty much how my aspect sounds at the moment. But there are some other things that I'm trying to add on. I want to be able to output waveforms in the command line or like when you add an output group, and so you can see the waveform of the audio in the process. So there are all sorts of little things, but I'm making progress, and I want to try and make some more meaningful audio, experimental music, something with this. And so we'll see where that leads. Thanks a lot.
OK, I guess that's it. And we have the reception in 1 minute.